porosity is increasing. We could also try to find some kind of scaling law in this case. This is a little video for you to show that if the mismatch in the two electrodes is very different, positive and negative electrode, look at how plating will evolve at the interface between the anode and also the polymer separator. On the right hand side, this mismatch has been very different. Those electrodes look very differently. You can see that plating signature is changing so differently. So I would like to conclude with one example at the end. I think I can still take 1 minute, right? Something like that. So in this case, when we change the porous electrode to a lithium metal, which is a planar electrode, it's not porous anymore, just a plain lithium foil. The key important aspect is there. This lithium plating can lead to different morphologies of this deposition. It may look like a very discrete phase, dense film, porous film, or fractal structures. These fractal architectures are very bad because that can poke through the other side of the electrode and that can create short circuit, and that's very, very undesirable. So what happens of electrode deposition morphology is very important. So at the end, when I look at the morphology, it's just nothing but 3 transport processes. One, electrolyte transport, ion transport to the electrolyte, solid state diffusion on the lithium metal, and electrical reaction rate. Those 3 process kinetic rates, they essentially control everything. I would like to conclude with 30 seconds with an example. Well, temperature is a big impact. Temperature is a kinetic healer. Temperature improves reaction rates. Temperature improves transport rates. Well, if that's the case, if we operate or let's say have a local uniform temperature field, that can create this morphology of the deposition, not like the dendritic, but it can sort of a stable and morphology it can create. So my point here is to tell you in the context of this conference is the temperature is the big kinetic healer that we have at our disposal, which has a tremendous impact on different transport rates. I would like to conclude by saying we could also create a design map. We would like to essentially create a rate between reaction rate and transport rate. We call it a BO number. In heat transfer textbook, you know what's the BO number. We have defined similar BO number called electrochemical BO number. And you can say you can like to operate essentially here. Fractals are bad. We don't want the dendrites to happen. With that, let me conclude here saying, hopefully, I have been able to give you an idea what mesoscale physics in electrostructures is, which essentially includes multimodal transport interactions, interface behavior, and of course, you have electrochemical reaction coupling. With that, thank you very much. These are my group of students when we all could go to the lab and take a picture, but nowadays we're at home. And with that, let me conclude. I would also like to stop with an announcement to the participants, students, or PIs, or faculty members. I am looking for a postdoc, computational physics expertise, and a couple of PhD students. So if you have bright students or postdocs, please share their information with me. Thank you. And I'm happy to take any questions.
Thank you, Professor Mukherjee. It was an excellent talk in the morning to start with. So now we'll keep the floor open for some quick question answer session. So with that, I will leave it open for the floor.
Thank you, Professor De.
Let's see. Okay, while somebody comes forward, I have some quick just an clarification. So this mesoscale calculations, these are I assume lattice-Boltzmann kind of calculation.
So Professor De, in this particular case of the discussion, you probably got the glimpse of this two-phase transport that we all do in a typical lattice-Boltzmann framework. In this context of mesoscale, we all solve these governing differential equations, all really coupled in that sense, still within the finite volume framework. But we resolve those electrode structures or morphologies, right, as is. So that means within our finite volume formulation grid, we also have a solid phase in the grid, solid phase voxel, or a pore phase voxel, and the interface. So I would like to call it a voxel-based approach in a finite volume modeling framework, and those voxels are essentially capturing your solid pore different structures, morphologies as is, as they may come from X-ray tomography image or stochastic reconstruction. So yeah, this is all kind of, as I showed, mostly all finite volume framework.
Okay, yeah, thanks. Yeah, let me see. So still nobody is there. So yeah, I have just another quick. It's more like an out of curiosity. So when you come to this porous media, so is it kind of model with typical Darcy's laws, or you are solving a governing equation there to take care of the both the phases in that porous tube?
This is an excellent question, as a matter of fact. So, I mean, that's a so in this particular case, we would like to call it a pore scale modeling. That means we are exactly as you already sort of rightly guessed. All of the different governing differential equations, such as the diffusion equation, reaction diffusion equation. If we have sort of a electric potential as a migration term, still some kind of a transport equation. So those are we are solving at each sort of voxel. That means we are essentially not averaging over the microstructure. We have the solid and pore phases intact in terms of my each voxel, and each voxel we may call it a some kind of a finite volume grid or finite volume element where we have the descriptions. You're correct. It's a pore scale as compared to volume average, which gives you the Darcy's laws expression in porous media volume averaging approach. Correct. So it's a pore scale as opposed to that.
Okay.
Yeah.
Yeah.
So that's
Thanks.
why we call it a mesoscale. Yeah.
Yes. So there is one participant who has raised their hands. Yeah. Please go ahead.
Yeah. Thank you, Professor Partha and Professor Ashok. And I'm thankful to Professor Amresh also for inviting me to this lecture. I think this was very, very informative. Informative lecture that Professor Partha you have given. It was very enlightening, and I also, I'm also interested in this kind of. Doing research in this kind of area with Professor Amresh. So my question to you is that this is a very interesting topic, mesoscale modeling of the porous electrode. I am working in the industry, right now, and I have this kind of always a conflict or kind of a challenge that how do we connect in real time, or how do we simulate in real time analysis the performance of the electrode and the performance of the system with respect to the battery or battery efficiency and all those. So imagine that if I have connected this electrode in a system level circuit or system level and a simulation model, and how do we still continue to resolve the mesoscale dynamics in the real time phenomena? That is my question.
No, for first and foremost, I would like to really thank you for this question. This is an first of all excellent question, and this is an excellent, I think, point. So I think it is clear that all of these different physical, chemical, thermal processes are all happening at the electrode scale, right? At the electrode particle level, everything is happening inside that porous electrode, which we may call it mesoscale. How that scales to a real-time sort of a system sense, where we are trying to say, well, control or try to understand the performance or the temperature ramp or charge and discharge anomaly and all of those things. That is correct. So I think I would like to probably welcome you to have a separate discussion with me. But let me tell you this way: the only way we can think of how to essentially upscale this information from mesoscale is some kind of creating a good range of correlational dependence that can go into your fast models or simulations, right? I am still not trying to say that those upscale information could run as fast as your real time, but they would be really fast in terms of looking into the resistance descriptors, looking into dependence of temperature and C rate and so on, and that can go into your fast upscaled model. And this is one of our active field of research, as a matter of fact, and we have several industry sponsors for that. They like our mesoscale work. They also like that we can try to link that scales. So this question, I would like to say, probably is one of the most intriguing, not only the important questions, but also it's so relevant. I mean, in many cases we don't see the appreciation. Well, we can control everything at the top. I would like to say that we control everything
Yeah.
down here at the electrode. What goes in between? So that's
Yes.
that we are essentially trying to work actively. We have
Yeah.
at least 2 or 3 this kind of work going on. So we
And
could I
Professor
probably
Partha,
welcome discussion.
yeah,
Yeah.
and Professor Partha, thank you so much for that, explanation, and it really helps. And it is always a challenge at the industry level that how do we connect the dots? We are very passionate about the resolving the microscale physics, but how do we again make it effective at the industry level in real time scenario? So I was
Absolutely.
also
Yeah,
doing that research,
yeah.
and thank you so much for your kind information. I really appreciate this lecture was very informative. Thank you so much.
Yeah, so
Thank you.
I would suggest all the participants, if they have further more doubt or anything, I will take the privilege of Professor Mukherjee that they can drop an email to him for further clarification, because we are a bit running out of time here. So further sessions are getting held up here in this particular room. So with that note, I would again like to thank Professor Mukherjee for this excellent talk, and obviously all the participants for turning up in a large number in this morning, and we look forward to further discussions with him. And okay, with that, I would
Absolutely,
like to.
absolutely. Thank you so much, Professor Day. Thank you, Professor Dalal, and also for the great question. And please do
Thank
send
you.
me a note. You can
Thank you,
find
Professor
information
Mukherjee.
from any of them.
Thank you, Professor Day.
Yeah.
Thank
So with that
Thank
note,
you.
I will conclude this keynote session. Thank you, everyone.
Thank you. Bye-bye.
Thank you, everybody. Have a good
Bye.
day. Bye bye.
Hello,
Hello, good morning. This is
morning.
Jyotirmoy.
Good morning, everyone. So, welcome to this session 4B in Hall 2. So, this session will be shared by Professor Jyotirmoy Banerjee from SV NIT student. So, I request Professor Banerjee to please start this session.
Yeah, Vijit, thank you very much. I hope, let me check how many participants are there, first of all. Paper number 101. Deepak Kumar.
Yes, sir.
Yeah, paper number 103. Paper number 105. Yeah, Abhishek Kumar. Yeah. Paper number 126. Yes. Paper number 128. Thank you. Paper number 129. Paper number 135. 135. 147. Thank you. So only 103 is not present.
Yeah, so probably he will join in the meantime.
In the meantime, okay. Yeah. First of all, I welcome all the participants to this session. I am Jyotirmoy. I would wish you to, this will be played on video. After that, I would wish you to respond to the questions which are being put up by the audience who are listening to you, and also by me. So please start the video for 101, paper number 101. I hope there will be some introduction.
Greetings to all. Myself Deepak Kumar. I'm going to present my paper on the topic MSD free convection of magnetite nanofluid in cooling of an electronic component. Content of my presentation includes introduction, application of nanofluid, electronic cooling, characterization of magnetic nanofluid, problem definition, visual discussion, conclusion, and references. In modern era, there is a need to increase the rate of heat transfer. Several research are recently focused on to improve the efficiency of the existing heat transfer processes. Different methods which have been adopted for this are either by increasing the temperature difference, or by increasing the surface area, or by increasing the heat transfer coefficient. Now the temperature difference depends upon the working condition, and the surface area depends upon the design of the devices. Now, in order to increase the heat transfer coefficient, as we know that the heat transfer coefficient depends upon the type of fluid used in the device. Now, Choi in 1995 suggested a new fluid known as nanofluid, which was having a better thermal properties than the conventional fluid like air and water. Nanofluid has shown potential to replace the conventional fluid in many engineering applications. Some of the applications are engine cooling, electronic cooling, solar water heating, nuclear system cooling, heat exchanger, heat pipes, domestic refrigerator, thermal storage, and many others. Advancement in the field of electronic in the electronic field has led to the miniaturization of the devices, and as we know that we are going through the phase of ELSI, which the each chip contains around 10 to the power 5 to 10 to the power 7 number of components. It has been found that 15% of the failure of the electronic component is due to higher operating temperature, and the failure rate it increases almost exponential with the operating temperature. There are several electronic packages that are under the external magnetic field. Hence, it is important to consider the effect of external magnetic field on the free convection of the nanofluid. Since our nanofluid is electrically conducting in nature, hence it contains free electrons. Now, when these moving free electrons come under the magnetic field, electric field is induced, which gives rise to the current density, as a result of which Lorentz force starts to act on the fluid element. Now, the derivation of the Lorentz force on the fluid element has been given here. The study contains an enclosure having an electronic component placed inside it. Now, the enclosure contains magnetic nanofluid, and the heat transfer is taking place by the natural convection. Now, this enclosure is under a constant external magnetic field which is inclined at some angle with the horizontal. Now, to mathematically model this study, certain assumption has been taken, and those assumptions are listed here. Governing equation for this study contains mass conservation, momentum conservation, and energy conservation equations. And in the momentum equation, along with the pressure force and the viscous force, Lorentz force is taken into the consideration. The boundary condition has been put here, and several basic properties of the nanofluid has been calculated using these following properties. Vorticity formulation
Vijay, there is a
eliminate the pressure term from the governing
issue with the sound.
The same vorticity formulation has been further converted into the dimensionless forms using the several dimensionless parameters.
There is an issue with the sound.
Listed here.
Yes, sir. Yes, sir. So some participant noises. So I'll mute it, sir.
No.
Although correlations are available to determine the thermal conductivity and viscosity of nanofluid. Correlations like Maxwell and Hamilton for the thermal conductivity and Brinkman for the viscosity have been used by many researchers. However, it has been reported in the literature that these correlations underpredict these properties, because of which, in this study, these properties have been determined experimentally. Initially, the nanofluid has been prepared by the two-step method, in which the nanoparticle is mixed with the base fluid along with the surfactant, and ultrasonication is done for 60 to 80 minutes. After the preparation, the thermal conductivity is measured by K2 Pro thermal property analyzer, and dynamic viscosity is measured through Anton-Par rheometer. And density has been also measured using the pigment. Experimentally measured properties have been listed here, and additional properties which are required for the numerical study have been taken from the literature are also listed here. The measured properties are then used for the numerical simulation of the study. Now, in numerical study, the governing equations are discretized using the second order accurate finite difference method. Now, the discretized equations are solved using the in-house developed code using the MATLAB program. Now, under relaxation technique has been used for the higher Rayleigh number. After the development of the code, the grid independence test has been done for the code, and it was found that the value of Nusselt number almost became constant after 81 cross 81 number of nodes. Then the code was validated for the benchmark problem with previous works, and it was found that the code was the result from the code was close to the previously published results. Code was further validated with the work of Ghasemi for different Hartman number. And as can be seen from the result, it was found that the isotherms and streamline was in close agreement with the published results of Ghasemi. Study has been performed for different Hartman number, and the streamline and isotherms for different Hartman number has been shown here. It can be observed that the core of the streamline uh, shift down in the downward direction as the Hartman number increases, which signifies that the buoyancy force by the convection get reduced. From the isotherms, it can be observed that the isotherms were were of high density near the hot and the cold wall for the lower Hartman number, and it whereas the density get reduced near the hot and the cold wall for the higher Hartman number. This shows that the convection rate is getting decreased at the high Hartman number. Of the average Nusselt number with the Hartman number has been shown here. It can be found that with the increase in the Hartman number, the average Nusselt number is declining. The decline is more pronounced for the higher Rayleigh number compared to that of the lower Rayleigh number. This happens because at a higher Rayleigh number, the velocity of the fluid is high compared to that of the low Rayleigh number, and the Lorentz force which hinders the flow of the motion of the fluid is proportional to the velocity of the fluid element. And as for higher velocity, the Lorentz force is high, which can be observed for the higher Rayleigh number value, and its effect is not significant for the lower Rayleigh number. Next, the effect of heater location has been studied on the natural convection. As can be found from this plot, that as the location of the heater is shifted in the upward direction, the value of Nusselt number decreases. Although this difference in Nusselt number is not observed for the lower Rayleigh number, like 10 to the power 3 and 10 to the power 4. This is mainly because at lower Rayleigh number, the heat transfer is mainly because of conduction, and that and for conduction, the location of the heater doesn't affect the Nusselt number much. But as the Nusselt number Rayleigh number increases, the effect has been observed for the different location of heater. And for Nusselt number 10 to the power 6, it can be clearly observed that for A is equal to 0.3, the value is higher than A is equal to 0.7. Next, the study has been performed for in different inclination of the magnetic field. Now, it has been observed that as the inclination of the magnetic field is increased, the value of Nusselt number increases for all the Rayleigh number. This is mainly because the Lorentz force, which is hindering the flow of the fluid, or which is declining the buoyancy force, depends upon the inclination of the magnetic field, and the effect of this Lorentz force is more pronounced when the inclination of the magnetic field is along the horizontal direction, and its effect gets reduced when it is in the vertical direction, and the same has been observed from the result. Now coming on to the conclusion. The position of the electronic component doesn't matter much for lower Rayleigh number, as a dominance of the diffusive mode of heat transfer over the convective mode leads to almost equal rate of heat transfer for all position of electronics component for the relay number. Increases the Hartmann number leads to the deterioration of the flow strength, which lead to the decline in the rate of heat transfer. Increase the Rayleigh number cause rise in buoyancy force when increase in heat transfer rate. And at last, the inclination angle of the magnetic field has almost negligible effect on the heat transfer rate for lower Rayleigh number. However, the rate is found to increase with the angle at higher Rayleigh number. Thank you.
Okay. Yeah, thank you very much. Who is the speaker? Who is present for attending the question answer session?
Yes, sir. Deepak.
Deepak. Deepak,
Yes,
you are a student?
Yes, sir. IIT Roorkee, I am the student, and NIT Uttarakhand, I am the faculty.
Okay. Part-time doctoral student?
Yes, sir.
Okay. Deepak, it's a good work done. I appreciate. I have a small question. Do you account for the slip between the particles and the fluid in your model?
No, sir, I have not included the slip. This is mainly because, sir,
it is a no slip condition. Okay.
Yes, sir.
If that is the case, then do you expect that there will be some amount of dissipation associated due to the slip between the particles and the fluid?
Yeah, if we include the slip, then obviously there will be some sort of dissipation.
Okay,
but
assume a no slip condition. You believe you need not account for the slip, did not account for the heat dissipation associated with the slip?
Yeah, I have avoided the heat dissipation because of the slip.
Okay. Do you believe that there is, in reality, the no slip condition does exist?
Actually, sir, in reality, some sort of slip occurs. But when we will the condition which I have taken is for extremely low volume concentration of nano fluid. So in that case, even if there is slip, it will be very much negligible. So in order to avoid some sort of complexion study, because since it is for 0.01%, the volume percent, which is very small. If you will take for 1% and 2%, then obviously we should consider the slip condition. But since it has been taken for a very
good.
So I have avoided.
Yeah, the other question that I have, Deepak, do you believe magnetic effect will have some influence on the properties of the mixture?
Yeah, this is the question, sir. If we will apply the magnetic field, then there are chances because the clustering of the molecules may takes because of the magnetic field. So the thermal conductivity and viscosity may change. But sir, the properties which I have taken, which I have seen from the literature, they are taking mainly for conductivity, the Maxwell and the Hamilton and Brinkman for the viscosity, which is not considering the effect of magnetic field. And moreover, even for the real case, without magnetic field also, they are not able to predict the correct. So although I have not measured the property using the magnetic field, this I agree. But at least the property has been determined experimentally. So the magnetic field effect will be there. I agree with this. This may cause some deviation of the properties. But because of the lack of the facilities, this has.
Do you have some experimental study available in this regard?
Yes, in literature there are experimental studies.
Okay, is there a possibility for you to check how close is your model to the experiments?
It is possibility, sir, but the issue with the experimental case is having that most of the studies have been done for the higher Rayleigh number, and what was my study was for the lower Rayleigh number, and it is very difficult to achieve a very low Rayleigh number. Although we are trying in our lab, we are trying to achieve that, and once it is done, then.
Okay, thank you, Deepak. I would wish some of the participants or the audience put some question to Deepak?
Hello.
Hello. Yeah, please go ahead.
Yeah, I had a question actually. Deepak, what type of boundary condition used for vorticity on the domain of the boundary in this domain?
Sir, vorticity, it was simply that I cannot see.
But you have used this 16% vorticity formulation to compute the solution.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay. So what type of boundary condition for the vorticity? I mean, it's too complicated, like for these types of flows actually. So what type of boundary condition?
It doesn't get complicated. 1 minute.
It is okay, Deepak. In case you are not able to answer, you can interact with him later.
Obviously, I will report this because I am having that in the words. It is difficult to express, but because the slide cannot be turned back, so it is in the mathematical form that can be.
Okay, can you interact with him?
Obviously, I will interact with him in this regard. Means what I have used for my case, I can because that is in completely mathematical form. So
yeah.
See, Deepak, one would expect to build confidence on your model, an order of accuracy analysis. So I believe you should do an order of accuracy analysis and show to the world that you are really correct in your model and your results can be relied upon.
Yes.
Okay. Thank you, Deepak. Thank you very much for attending the conference.
Any time, more time to ask one more question, sir?
Yes, sir. Please go ahead. Please.
Yeah, Ramon here from Honeywell. So, Deepak, when you mentioned that your volume fractions are very less for the nanoparticles, and that is the reason why you ignore the slip between the But is it not that if you have more particles, then the slip will be lesser between the two phases? Because one particle will have much more, it's easier to get dragged alone, right? And that is the slip that you don't have.
No, sir,
that is one thing. And second thing is, you are saying that your magnetic force, magnetic field is not very prominent at lower LA number. So is there any particular reason for that you can cite?
Actually, sir, the magnetic field which is hindering the force, which is hindering the motion, because at lower Rayleigh number the motion of the fluid is very less, because the buoyancy force is very low at lower Rayleigh number, and hence when the velocity is very less, then the effect of the magnetic field is not that much, because the magnetic field depends upon the V. Magnetic force, the Lorentz force depend upon the velocity. Now, if the velocity is very small, then the force is not that much effective. It is not of large scale. So the effect is not that much pronounced in the Nusselt number. So that's why at lower number we are not getting that. And the first part you are saying that for the low volume fraction. So since there are very less particle in the fluid, because whatever I have seen that till if we are having less than 1%, we can use the homogeneous model, which I have found from the literature. We can use the homogeneous model because the particles are very less, and we can assume that the total fluid is homogeneous. And the slip, which you are saying, obviously, if the particle will be more than the slip, the viscous dissipation, that will be more effective.
That's my point.
What he wants to tell is, since the particle volume fraction is low, the effect of dissipation will be negligible to be accounted for. That's what he wants to say.
So that was my point, that your slip may be more, but since your effect of slip on the main flow is very less because you have less particle, then you don't need. But you cannot say that slip is less because of less number.
No, slip is not less. Total effect is less, obviously. Yes, sir.
Yeah. Thanks, Deepak. Yeah, it's a nice presentation.
Thank you, sir.
Okay, let us move to the next participant. Is paper number 103 available? Is the participant for paper number 103 available?
Yes, sir.
Yeah, please start with 103.
Panel members, today I am going to present the paper titled the effects of spacing to diameter ratio and mixing characteristics of twin jets. Myself is Narendra Kumar. I am a research scholar from IIT Kharagpur under the guidance of KP Sinha Mahapatra, Aerospace Department, IIT Kharagpur. Outline of the presentation is like this: objective, introduction, literature review, geometrical models, numerical study, computational domain with mesh and boundary condition, validation, results and discussion, conclusion, and references. Objective. In this paper, the effect of spacing to diameter ratio and mixing properties of twin circular and elliptical twin jets are investigated numerically at 4 different S/D ratios. So the elliptical twin jet is studied in 2 orientation. One is along the major axis orientation and one is along the minor axis orientation. Major axis orientation is called as twin major. Minor axis orientation is called as twin minor. The numerical simulations are performed in the ANSYS 19.2 software with a jet Mach number of 0.8 using SST K omega turbulence model. Introduction. Since several years, the twin jet mixing behavior has been investigated experimentally and numerically. Understanding the mixing behavior of twin jets helps in developing the engineering and industrial applications. So this is the schematic flow structure of a twin jet. It basically consists of a 2 jets which are separated by a distance called S. When 2 jets are flowing from the exit to the downstream location, we can see the jet profile like this. Here XMP denotes the merging point location and XCP denotes the combined point location. U symmetrical denotes the centerline velocity of the 2 jets and UCL denotes the centerline velocity of the single jet. This twin jet profile basically consisting of 3 regions. They are called as converging region, merging region and combined region. From the past research, we understood that the properties of mixing and turbulent intensities are dependent of exit Reynolds number, nozzle topological change, and SID ratio between the 2 nozzles. Review. Several research have investigated the effects of nozzle geometry, Reynolds number, and spacing distance and twin jet mixing properties. So Miller and Cummings studied the mixing characteristics of plain twin jets at a particular spacing distance and Reynolds number. They reported that the exit, they understood the negative gas pressures and it is due to the pumping effect. Lin and Shu examined the impact of spacing on the emerging point of twin jets in the range of S/D less than 30 to measure the centerline velocity. In the mixing and combined regions, the authors reported that mixing rate and jet decay of twin jet from the combined point onwards is very rapid and intense. Nazar and Lai investigated the different Reynolds numbers on twin jet average velocity at a fixed spacing distance. The results showed that first distributions are independent of Reynolds number of a particular Reynolds number. Wilson et al. Evaluated the 3 turbulence models. They are K omega, SST omega, RSM in predicting the mixing properties of twin jets. They suggested that K omega and RSM has the closest approximation results to the experimental results. Nazar and Lai also investigated the ability of standard K epsilon, RNG, and RSM turbulence for models for 2D twin jet flows. They understood that RSM has the closest values to the experimental over other 2 methods, and remaining K omega, K epsilon, and RNG has the overestimation of experimental results. Urban et al. Investigated the spacing distance effects on circular twin jets at a fixed Reynolds number. It was noted that an incrementing spacing ratio between the 2 individual jets reduced the jet core spread rate and decrease in turbulent properties in the transverse direction. The geometrical models. So figure shows that circular profile, ellipse major, ellipse minor, and respective twin jets are given here. So twin circle, 2 elliptical jets are oriented in the major axis. They are called twin major, and 2 jets are oriented along the minor axis. They are called the twin major. Numerical study. This is the domain which has taken into consideration. In the XYZ dimensions are like this: 30D, 5.3D, 5.3D. These dimensions are taken from the literature review. The pressure-based coupled solver is used for steady-state transpilation. Area as an ideal gas is considered and viscosity calculation based on the 3-point Sutherland formula. SST K omega turbulence model is chosen. and results are iterations are iterations are continuously ran till the convergence is achieved. Convection terms are discretized by bounded quick scheme, and viscous terms are solved by second order central differencing scheme. Simplex procedure is followed for the pressed velocity coupling. Domain with mesh and boundary condition. This is the mesh structure that looks like. So I have taken the trigonal mesh structure. The inlet outlet far field boundary conditions are like this. Since the chosen Mach number is 0.8 and the corresponding pressures are given at the inlet location, and remaining outlet and far field is given with the atmospheric conditions. Validation has been done for the turbulence model and grid independent grid size. So 3 different turbulence models are chosen, and it was compared with the Anderson et al. Work. Out of the chosen turbulence model, SST omega model gives the exact results of Anderson et al. Work, and whereas K epsilon and RSM has the closest values in the near field, but in the far field they overestimated the Anderson et al. Experimental works results. Grid independency test with mesh size in million. Several mesh sizes are used for checking the grid independence. From 2.7 million onwards, the results are identical to each other. Hence, 2.7 million size of grid is used for the further simulations. Single and twin circular jets. Only circular jets are validated with the Anderson et al. Work for Anderson et al. Work. So validation of single circular jet, Anderson et al. Experimental work and Anderson et al. CFD and present CFD results are plotted here. So the present CFD results are well matched with the Anderson et al. Experimental work and Anderson et al. CFD in the near field, and in the far field the results are well matched till 20 x by d20. From 20 to 25 the results are slightly overestimated with the present CFD study. In twin jet case, in the near field, the present CFD study shows good agreement with the Anderson et al. CFD work. In the far field, the results are under predicted. Discussion. So these are the velocity contours of single and twin jet at Mach number 0.8. In the right hand side, velocity decay of single and twin jets are given. So from the single jet, we can understand that potential core length has been higher for the single circular jet alone, whereas for single major and single minor, there is a shortened potential core length due to the asymmetry in the x and y direction shapes of geometry. When it comes to twin jet profiles, all 3 twin jets shows a similar behavior, like they try to increase to an asymptotic value. Once they reach the asymptotic value, the nature of the flow behavior is rapidly increasing to a certain point, and there are not, it is rapidly decreasing to a certain value in the downstream direction as expertise is increasing. Spacing to diameter ratio on mixing. So yes, velocity contours of twin circle, twin major and twin minor at different S by D ratios at Mach 0.8 is given. So first picture shows the velocity contours of twin circle, and second one shows the velocity contours of twin major, and this one shows the velocity contours of twin minor. From the figures, it is clearly evident that for twin minor configuration, the potential core length is less as compared to the other two cases like twin circle and twin major. Whereas for twin major, the potential core length width is very less in the y direction, and potential core length in the y direction is more or less same for both twin circle and twin minor. These are the velocity contours of velocity decay for 3 configurations at S by D equal to 0.25 and 0.5. From the figures, it is understood that the merging point locations are within the limit of x by d equal to 2 for the s by d equal to 0.25 case, and for s by d equal to 0.5 case, the merging point locations are moved slightly from x by d equal to 2 as compared to the s by d equal to 0.25. Same behavior has been observed with the combined points also. We give for 3 configurations at s by d equal to 0.751. So here we can see the velocity variation for all 3 models at s by d equal to 0.751. From the figures, it is understood that the higher magnitude of velocity, like for s by d equal to 0.75, the highest magnitude of velocity is 0.6. For s by d equal to 1, the velocity magnitude is 0.5. The potential core length and merging point locations are given here. So for twin minor, the potential core length, merging point and combined point locations. From these, we can understand that twin minor has the lowest merging point and the conclusion. So from the conclusion, it is evident that as increasing the spacing distance, the merging point and the combined point locations are changing, and SST K omega turbulence model is able to predict the mixing properties. These are the references which I have.
Hello. Welcome to the presentation on geometry solver.
Hello. Vijit, can we have some interaction time with Narendra?
Yes, sir. Yes, it's a question and answer session.
Yeah, if there is any question from the audience or participants who are listening, let me get it first.
Hello, sir, Ramon. I have a question.
Yeah.
When you're
yes, please.
Minor different jets you have created, did you keep the center of them at the same location, or they were changed to maintain the gap same?
No, sir. Centers also same, and I maintain the distance between the 2 individual jets are same. Like I have chosen s by d equal to 0.25 to 1 level by increasing the distance between them 0.25. So the centers for all 3 models are maintained at same place. So, but when we see through.
Yeah, but if you keep the center same and major and minor axis same, maybe I have missed your something in your presentation, but the gap between the 2 jets will be different, right? That's what I think I saw in your contour plots also. That's what my understanding. Maybe I missed something.
No, sir. Like whatever the distance between s by d, like suppose 2 circles were there, the distance between them is 0. And this is maintained for the ellipse case also.
You mean to say the non-dimensional distance is same, but the physical distance will be different, right?
Yes, sir. Physical distance will be different.
Yeah, okay. So that might have some impact in your whatever results that you have shown here.
Okay, sir. Thank you. I'll look into more precisely.
Thanks.
Yeah. Any other questions?
Yeah, I have one question actually. Was the exit condition at the nozzle, was the flow fully developed for all the cases, or?
Yes, sir. It's fully developed. I have run the simulation till the convergence is achieved. Like I have run using.
No. The question is different. Not convergence. It is at the end. Can you say that you are certain that the fully developed condition is achieved at the exit?
Yes, sir. Yes, it is achieved.
But you have never shown in your result. This problem is tricky in terms of end condition.
Yes, sir. I believe that it's fully developed.
Yeah, I have a single question, Narendra. Why do you believe that among this low fidelity RANS model, K omega will be better for this problem?
Sir, K omega can act like K epsilon and K omega. For me, both near field and downstream conditions are more important. Like in the near field, potential core should be measured accurately, and in the downstream, the turbulence which I'm going to study in my further PhD studies is major. So
Do
in
you
that
have
case,
any idea about the scales associated, the lowest of the scale associated with the problem?
Sir, can you repeat the question?
Do you have any idea about the lowest of the scales associated with this problem?
Yes, sir. Like only default scales are taken into measure. So, but as far as literature is gone through, few researchers said we have to change the scales to get the better results. So these are the default scales I have taken.
The other question that I have is, when you are talking of Mach 0.8, can you can you say these are all isothermal flows?
Yes, sir. Yes, sir. Isothermal.
They are isothermal? Oh,
yes, sir.
They are non-isothermal. So at some point of time, you must show the density variation, the temperature variation as well.
Yes, sir.
And
Since I have taken downstream condition, there will be difference in temperature and densities also.
Is your solver is a coupled solver including the energy equation?
Yes, sir. Energy equation is coupled, included.
Oh. Okay. Okay. Thanks, Narendra. Thank you very much. I appreciate your presentation. Let me go to the next presentation, 105.
Hello. Welcome to the presentation on GMRS solver for interpolating MLPG method applied to heat conduction. I am Abhishek Kumar Singh from Department of Mechanical and Industrial Engineering of IIT Roorkee. First of all, outline of the presentation. We will begin with background, then MLPG formulation, and overview of iterative solvers, numerical results, followed by conclusion. Background is, most of the popular methods for analysis engineering are mesh-based methods, such as finite element, finite difference, and finite volume. And they require remeshing in the presence of large information, moving boundary, and with the phase change. And there is an issue with validity and quality of mesh for complex 3D geometry. There is an illustration of such problem. So this is the initial mesh, and after movement of the boundary, this is the mesh of the next stage, and we can clearly see that the mesh is distorted. So we have to do the remeshing, or we have to go for the mesh-free methods for the analysis of such kinds of problems. So a mesh-free method is criticized as a continuum problem without the use of predefined maps, and it employs a collection of discrete points or nodes in the domains. There are a variety of mesh-free methods available. The predominant ones are smooth particle hydrodynamics, SPH, diffuse element method, element figure method, RKPM, natural element method, and meshless local petroglycan method, also known as MLPG. And this work is based on these methods. Because MLPG is a truly meshless method. In this method, mesh is not required either for integration or for interpolation, and this is based on local weak form of governing equation. Computational steps of MLPG are computation of trial and test function, then numerical integration over the local weak form to get the local system of equation. Then we have to assemble them to form a global system of equation. And the last step is solution of discrete algebraic. So solution of discrete algebraic equations involve numerical methods. Now, the MLPG formulation leads to an asymmetric system of equations, and for large-scale problems, iterative solvers are only viable option, as direct solvers are not feasible due to their computational requirement and storage requirement. So there are basic iterative solvers such as Jacobi, Gauss-Seidel, SOR, which are based on relaxation of coordinates, and they are very easy to program, but their convergence is too slow. That's why they are rarely used alone as a standalone solver. They normally used as a preconditioner or a smoother for accelerated iterative solvers. So for solving a symmetric system of equations, there are Krylov-Suste solvers such as bi-CG-step, bi-conjugate gradient stabilized, or GMRS, generalized minimum residual. There are also multi-level or multi-grid methods, which are mostly used for mesh-based method, but this algebraic multigrid method can be used in case of meshless methods. And this multigrid method generally used as a precondition for the Kylo space solvers. Now, objective of this work. The objective of this work is the evaluation of GMRS solver in MLPD analysis. And in this work, we have implemented GMRS solver in interpolating MLPG method for 2D steady state heat conduction. And we have analyzed the effect of preconditioning, and we have compared the GMRS solver with BiCG. Now coming to formulation of the MLPG method. In this work, for meshless shape function generation, we have used interpolating MLS instead of standard MLS because it uses Kronecker delta property, and for stability we have used a shifted and scaled polynomial as a basis function. There are linear basis and quadratic basis, and here xi bar is xi minus xie over h, where xi is point of interest and h is nodal spacing. For further information, we can refer to this paper. We have used 4 other time weight function in this work, and for performing numerical integration in this local quadrature domain, we have chosen Gaussian quadrature schemes. So we have chosen local quadrature domain as a circle, and they are further mapped into square domains. Now the formulation of heat conduction. So our governing differential equation is K del 2 T plus Q equal to 0 and domain omega, and boundary condition are Dirichlet boundary condition on boundary gamma 1 and Nyman boundary condition on boundary gamma 2. And the weighted residual statement in domain omega q is K del 2 T plus Q V d omega equal to 0, and integration is performed for omega q where V is test function, and by applying the divergence theorem we get this form, and after solving this equation we get system of equation on, and after assembling them we get this global system of equation Kt equal to F, where T is the vector of unknown nodal temperature, and K is stiffness matrix, which is asymmetric, and F is the load vector. This stiffness matrix K depends on the position of X. If X lies, either X lies on gamma 1 Dirichlet boundary or inside the interior. Similarly, for the F, if Xi lies on Dirichlet boundary or Nyman boundary or in the interior. Now coming to iterative solvers. So we have given a brief overview of, or you can say outline of GMRS solver, BiCG step solver, and precondition used in. So GMRS solver is a trial of success solver. First we have to set a tolerance. In this case we have taken 10 to the power minus 8. Then we take initial guess T0. Then begin with the outer loop. GMRS is a 2-level scheme. Then we solve for R0. M inverse is the precondition matrix. Then we calculate beta V1. Then we begin inner loop. M is the number of subspace. M is the subspace size. Then we compute Zj. And again preconditioner is called in this step, mu equal to Zj. Then we compute UH, and we define select the VM n sem bar. Sem is Heisenberg matrix. Then end of this inner loop, and then we solve for Ym by solving this least square problem, and for getting Ym we calculate this Tm, which is T0 plus Vm Ym, and then we check for the convergence. If it's satisfied, we stop here, else we set T0 equal to Tm and go to first. For more information on GMRS solvers, please refer to book on iterative methods for sparse linear system by Sath. Now coming to BiCG step solver, it is also a Krylov success solver in which we compute R0, set R0 star equal to R0, some scalar values. Then we start the iteration loop, and we calculate rho and beta. And if I equal to 0, this vector Pi is equal to Ri, else Pi is Ri plus this relation. Then preconditioner is called for first time at this stage, MT hat equal to Pi, then we solve for Vi and alpha I, and in this step preconditioner is called for second time, MZ I equal to Si, and using this Zj, Ti and omega is calculated, which are further used for calculating Ti plus 1. We again check for convergence. If it is converged, we stop. Otherwise, we go for the next loop. Preconditioner. In this work, we have used Jacobi and SOR preconditioner. So for Jacobi preconditioner, preconditioning matrix is diagonal of matrix K, and we have used SOR preconditioner where a very small value of K are used. So for testing, we have solved steady state heat conduction in a square domain where all edges are kept at 0°C, and internal heat generation is 10 to the power 6 watt per meter cube. Thermal conductivity is 400 watt per Celsius. These are the solution parameters, and we have taken 36 Gauss points in the local quadrature domain for the integration, and number of nodes in support domains are put in. And this is the exact solution, and our solution is validated by this solution. And this figure shows solution error dependence on grid size, and we can see that error is decreasing with increase in grid size, or grid size is referred as a node. So these are the convergence relative error and MLPG solution error. We have used GMRS solver without preconditioner and with Jacobi preconditioner, and for 1000 nodes, CPU time is 0.41 second without preconditioner, and for 14,400 nodes, this is 0.73 second. They have also played with subspace size, and this table is presented for optimum subspace size. When we use Jacobi preconditioner, computation time is reduced from 0.41 to 0.27 second for 10,000 nodes, and from 0.73 to 0.48 second for 14,400 nodes. We have also used SOR preconditioner with GMRS solver with K equal to 3, 5, and 10, and optimum value is obtained at K equal to 5 and omega equal to 1.4 for 10,000 nodes, which is 0.24 second, and at the K equal to 3 and omega equal to 1.5 for 14,400 nodes, which is 0.44 seconds. Then for comparison, we have performed Jacobi preconditioner with bi-step solver, and the computation time is 0.28 second for 10,000 nodes and 0.5 second for 14,400 nodes. We have also used SOR preconditioner with bi-step solver for similar K equal to 3, 5, and 10, and we played with omega. And here for 10,000 node, optimum value is 0.2 second for 27 seconds for omega equal to 1.7 and K equal to 5. And for 14,400 nodes, optimum time is obtained at K equal to 5 and omega equal to 1.6, which is 0.47. And we have shown comparison of all the solvers, and we can see that best time is obtained at GMRS solvers with SOR preconditioner, which is 0.24 second for 10,000 nodes, and in case of 14,400 nodes, 0.44 second for GMRS with SOR. Now the convergence behavior, so we can clearly see that there are spikes in case of bi-step solver, and GMRS shows very smooth convergence behavior. So let's come to conclusions. Results demonstrate a significant effect of preconditioning in GMRS solver, and GMRS solver takes about 6 to 8% less CPU time than the bi-step solver, and its convergence is much more smoother than the bi-step solver. So our results show the suitability of GMRS with the MLPG method for large-scale problems.
Yeah, thank you, Abhishek. This is Abhishek, no? Abhishek is present here.
Yes, sir.
Thank you, Abhishek. Are you developing these codes on your own?
Yes, sir.
Okay, that's good. I appreciate. Now, how good is your GMRES solver in capturing singularity in a problem?
Sir, I have not studied singularities in the problem.
Because I think you are in the beginning of your work, correct?
Yes, sir.
Even the problem you have taken as a linear solution. I think you must test it with a lot of non-linearity, singularity in the problem.
Now I'm working on complex problems, and at that time I have chosen only a very simple problem with exact solution available. So now I'm working on complex problems.
Why do you believe these preconditioners are required?
Preconditioners are required because this Krylo solvers basically depends on preconditioner. It means their behaviors are this choice affects the convergence rate and overall computation time, because there is a matrix vector product involved. So number of operations required drastically affects on overall computation efficiency. So these preconditioner actually reduce that calculations.
Do you know what is the basic trouble with a conjugate gradient solver?
One thing is stability issue with conjugate gradient solvers.
Yeah. Can you highlight on stability?
So I have not done any stability because my work is not on conjugate gradient. I have just compared because someone previously have worked on conjugate gradient. So I have compared my result with conjugate gradient. I'm working on geometry.
True. Any questions from the audience or participants? Other participants?
Jyotirmay?
Yeah.
This is Atul. Yeah.
Yeah.
I have a question. You started with the presentation about the meshless method. I was wondering, you talked about applications where it will be more advantageous. Although you had not presented such results, whether you are planning, I just wanted to know which problems will highlight. Yeah.
Yes, sir.
Abhishek, you are able to hear me?
Yes, sir. Yes, sir.
You started with meshless method, highlighting its advantage over other methods.
Yes, sir.
Although you have not demonstrated in your presentation. Am I right?
Yes, sir.
So is there any problem that you are planning in future where you can demonstrate effectiveness of the meshless method as compared to other methods?
Yes, sir. Sir, actually, I'm in initial stage of my work. So these are the future aspects, my problems. I will go for
You are a doctoral student?
Yes, sir.
Okay. Fine.
Okay.
Good. We shall be willing to see how you progress.
Yes, sir. Thank you, sir.
In future, take up some complex nonlinear problems with singularities if possible.
So I'm working on complex geometry problems. Heat conduction in a complex geometry like flywheel.
Good.
Good.
Thank you, sir.
Okay. Any more question? In that case, we can move to the next presenter. Avijit, please start 126.
Good morning all. This is Sanmesh Prabhu Suligavi from FMFP Surat. Here I am going to present electrolytic droplet detachment from the hydrophobic surfaces. As the name suggests, electrolytic is the process of controlling wettability using electricity. Here, figure shows a droplet resting on the hydrophobic surface. When the system of droplet and surface energy is subjected to a potential difference, surface energy increases. In order to maintain sigma constant, contact area increases, thus flattening the droplet as shown in the figure. Here is a small video graph showing the phenomenon at work. Droplet detachment is of high interest in many industrial processes, natural processes, and in condensation heat transfer applications. For example, wind cleaning in cicadas, fungi, wiperless windshield are to name a few of them. Liquid condensing on the surface has formed liquid film, which hinders the further condensation heat transfer. Hence, it is required to remove it frequently. In history, various methods have been proposed for the removal of the liquid from solid surface. One of the popular and early technique is used to coat the surface with the hydrophobic material, which forces the liquid to condense as droplets rather than the film. Traditionally, gravity and vibrations were used for the droplet detachment, but they have limitations like system orientation and integrity issues. The recently introduced technique coalescence induced detachment works due to the release of the surface energy of the droplets on colliding. Major issue with this technique is lack of human control. In order to overcome all these limitations, the concept of the electrowetting can be used for the droplet detachment. This technique gives better control over the phenomenon, and the droplet can be detached at any orientation of the surface. Having this advantage, electrowetting induced droplet detachment shows a great requirement for its study. Hence, our research is focused to understand the phenomenon in depth and thereby try to enhance its performance. Present study has been carried numerically since it provides a better scope for the understanding internal dynamics of the process. In electrowetting induced droplet detachment, the process divided into three cases just to understand the phenomenon in easy and simple manner. First, the droplet stretching. First, the system is subjected to potential difference in which it stretches and flattens the droplet over the hydrophobic surface. Second, droplet recoiling. When the droplet reaches to its new position, the voltage source is turned down instantly, forcing the droplet to attain and recoil back to its original state. Third one, droplet detachment. The voltage drop is high enough to break the adhesive force between the droplet and the surface. The droplet gets detached from the surface. A table is shown here which demonstrates the literature on electrowetting induced droplet detachment. The work being followed here is experimental work conducted by Lee and his co-workers and the previous numerical work done by the Islam and Tong. For validation of in-house developed code by us, we have considered these two previous papers. The models and the methods used in this numerical methodology are: the Navier-Stokes equation is solved using semi-explicit method with the help of Flick-VOF algorithm, and the dam break flow problem is validated. And the continuum surface force model is used for the contact angle problem, and the K8 kernel is used for modifying the concentration with the spurious velocity of 0.05376 meter per second. A static contact angle model is used to simulate the effect of change in the contact angle. Here is the schematic of the experimental setup used by Lee and his co-workers, and the corresponding computational setup used in the present study can also be seen here. In the experimental setup, Teflon was used as the hydrophobic material and tungsten was used as the electrode, and parallel C dielectric layer is used to avoid the electrolysis of the droplet at higher voltages. Symmetry of the problem about the vertical plane is exploited to minimize the computational time, and the boundary conditions for the left is considered as the symmetry, and the top and right it is considered as the pressure outlet. But there is an ambiguity in choosing the boundary conditions for the bottom of the domain. So to our notice, this ambiguity exists in the literature also. So we select the boundary conditions for the bottom boundary by trial and error method. Numerical method for the droplet actuation is simple and straightforward. During electrowetting, contact angle is reduced for a stipulated amount of time. The magnitude of the reduced contact angle can be calculated from the equilibrium contact angle, and the Young-Lippmann equation is given like this. Electrowetting induced droplet depends on the various parameters like density, viscosity of the fluids, volume of the droplet, voltage applied, type of the pulse wave, and the pulse width, etc. A single square DC pulse is used in the present study. The grid independent study has conducted to make the numerical model independent of the grid size. Current model is checked for the mesh independence by studying the topologies of droplet at different time intervals and at different grid sizes. Study was conducted at different 5 grids. It was observed that the droplet shapes during the stretching and recoiling are approximately same for all the size of grids, whereas during detachment, droplet shape was found to depend largely on the grid size. So 60 by 120 grids are taken as the final grids. As we all know that contact angles play a dominant role in the electrowetting induced droplet detachment. So both intrinsic contact angle and electrowetted contact angle are considered. A small uncertainty in their measurement leads to a greater ambiguity in the numerical results. Hence, study of such uncertainties are very important. The intrinsic contact angle 116 degree measured by the Lee and his co-workers, which consists of uncertainty of 3 degrees, is considered for the study. The temporal variations of the base radius plotted as error bars at input 135 volt and is compared with the previous numerical work conducted by the Islam and Tong. Variation of the base radius for 3 different contact angles 119 degree, 116 degree and 113 degree are considered for the plotting the error bars. As we earlier said, the boundary condition for the bottom boundary is decided by the trial and error method. So here we have considered the no slip boundary conditions at different voltage input. That is, velocity of the real and imaginary cells are equal and opposite in direction. Now here we have used the slip boundary conditions at different voltage input. That is, velocity of imaginary cell is 0. At last, we have used the free slip boundary conditions at the bottom boundary of the surface for different voltage input. That is, velocity of the imaginary cell and the real cell are same. It can found that intrinsic contact angle equal to 119 degree with free slip boundary conditions is giving a result which is in good agreement with the experiment. During the stretching stage, all the configurations are found to give satisfactory agreement. It is during the recoiling stage where the deviation between the configurations starts to appear. Till the mid of the recoiling stage, all the 3 contact angles almost overlapped on each other. But at the end of the recoiling, intrinsic angle equal to 113 degree and 116 degree are severely deviated from the expected curve. All the configurations except intrinsic angle equal to 119 degree with the free slip boundary condition fail to show the detachment. Hence, intrinsic angle equal to 119 degree is used as the intrinsic contact angle for the further simulations. When the fluid sessile droplet starts moving in a particular direction, the static contact angle increases at the leading edge and reduces at the trailing edge. But it is important here to note that the motion due to electrowetting is slightly different than the normal motion of the droplet. In electrowetting induced droplet actuation, deformation at the contact line drives the droplet. So due to the inertia, droplet falls back in the opposite direction of the motion. The contact angle at the leading edge is called as the advancing contact angle, and the contact angle at the trailing edge is called as the receding contact angle. The difference between the advancing and receding contact angle is called as the contact angle hysteresis. Thus, the advancing contact angle is always less than the static contact angle, and the receding contact angle is always greater than the static contact angle in case of the electrowetted induced droplet actuation. In the present study, 116 degree and 125 degree are considered as the advancing contact angle and the receding contact angle, respectively. To study the contact angle hysteresis in detail, 4 cases are considered. First one, accounting no hysteresis. When the hysteresis is not considered, droplet gets spread to higher radius than the usual, and there is a delay in the detachment. Second one, accounting only advancing contact angle. When only advancing contact angle is considered, spreading radius of the droplet found satisfactory, but there is no detachment. Third one, accounting only receding contact angle. When only receding contact angle is considered, model shown a higher spreading radius and droplet detachment took earlier than the expected. This is due to extra surface energy gained by the droplet during the spreading. Fourth one, accounting both advancing and receding contact angle. When both advancing and receding contact angle are considered, the results are excellently matching with the previous numerical results of the Islam and Tom. After all the parametric study, the results are used to compare with the experimental and the previous numerical results to check the degree of affirmation between them. The qualitative comparison between the experiment and the current study is first made to check whether the developed model is capable of capturing the right phenomena or not. By observing the droplet topology during the electrowetting induced droplet detachment and its comparison with the experimental results at different times found satisfactory till 7.8 milliseconds and later on diverted. The presence of the electrode is the main cause of the difference between the experiment and the current study with respect to time. For quantitative benchmarking validation, a plot of base radius of droplet versus time is obtained and compared with the similar plot given by the previous numerical paper and the experimental paper given by the Lee and his co-workers. Current study shows the excellent agreement with the previous studies till 12.8 milliseconds. Numerical results of both current and previous are found to deviate from the experiment later on, and the current study maintains its agreement with the previous numerical study till the completion of the process. In the experimental study, detachment time is reported as 19.6 milliseconds, whereas the current model predicted to be 18 milliseconds, which agrees with the previous numerical study. This detachment time difference is only due to the presence of the electrode in the experiment. Here, after working on the current study and comparing our results with the previous numerical as well as the experimental papers, we came to some of the conclusions, and those were uncertainty in contact angle measurement reported by Lee and his co-workers is studied to observe its effect on numerical result. And intrinsic contact angle 119 degree model is found to give satisfactory results. The effect of the boundary conditions for the bottom wall domain is analyzed and is finally concluded that free slip boundary condition suits best for the hydrophobic surfaces. And it is observed that when the contact angle hysteresis is considered, results of highest resemblance are observed. Thank you.
I request questions from the audience or the participants or who are listening to this presentation. Yeah, any question from the participants? Hello, am I audible?
Yes, sir, you're audible.
Yeah. Any question from the audience? No? Sangmesh, then I have a single question for you. How do you believe the dynamic contact angle model will make difference to the results that you have obtained, particularly at time levels beyond 7.5 milliseconds? Hello? Yeah, Sangmesh, am I audible?
Yes, sir. Am I audible?
Hello?
Hello?
Yeah, Sangmesh, could you listen to my question?
Yes, sir. I have listened.
Yeah.
Am I audible?
How do you believe the dynamic contact angle model may help, particularly for the results beyond 7.5 milliseconds?
Sir, right now we have studied only the static contact angle, but the dynamic contact angle model is being carried out by authors, and the Cox dynamic contact angle model is going to use. So I'm not sure whether how it changes the.
Your voice is not is very feeble, Sandesh.
Hello.
Yeah, your voice is feeble. Please speak loudly.
Sir, okay. Sir, right now we have only studied the static contact angle model, but the dynamic contact angle model is being carried out by the authors. So in dynamic contact angle, Cox dynamic contact angle model is going to use further. So I'm not sure whether how the results will vary after 7 point something milliseconds.
But is there any literature that suggests usage of dynamic contact angle model?
For right now moment, I am not able to remember, sir.
Okay. Okay, if there are no further questions, shall we move to the next presentation? 128.
Yes.
Good morning, everyone. I am Biswaranjan Behra from NIT Rourkela. Today I am presenting here about natural convection heat transfer from an open cylindrical cavity. Introduction. We know natural convection heat transfer is quite fascinating as the flow is buoyancy driven. Natural convection is convenient and noise free, so it is widely used. Heat transfer from open cavity is broadly studied due to its practical applications. These are some of the applications where cylindrical cavity is used. Cooling of nuclear reactor, solar thermal receivers, cooling of electronic devices. These are some of the papers on which literature review has been done. Coming to objective, the literature survey discloses that thermofluid characteristic of natural convection heat transfer in cylindrical cavity have not done adequately. So in this study, a detailed investigation is carried out on a 2D open cylindrical cavity. The parameters like relay number, L by D ratios are varied to analyze the thermofluid characteristics of an open cylindrical cavity with natural convection. Geometry. Figure 1a shows the 3D view of an open vertical cylindrical cavity, and figure 1b shows the schematic diagram of 2D axisymmetry geometry on which numerical analysis has been done. The parameters used in the numerical analysis are relay number, which is varied from 10 to the power 3 to 10 to the power 8. Surface temperature is maintained at constant 308 Kelvin. Ambient temperature is taken as 300 Kelvin. Air is taken as the working fluid, and L by D ratio varied from 2 to 10. These are the governing equations that have been employed in the numerical analysis. This is the continuity equation. This is the momentum equation in x direction. This is the momentum equation in y direction. And this is the energy equation. Boundary conditions. At the axis, there is no variation along y-axis. The variation along x-axis has been taken. At the surface of cylinder, constant temperature is maintained. At the computational domain, atmospheric pressure and temperature conditions are employed. These are the expressions for Rayleigh number and Nusselt number which has been used in the analysis. Validation of the present computation has been done with the Macadam and Churchill relation, and it shows good agreement with both the relations as it has been shown in figure 2a. And figure 2b shows the variation of total heat transfer with number of cells. It can be seen that for cells greater than 95,000, heat transfer is almost constant. So we use 1,05,000 cells for our computations. And whenever L by D is changed, we perform identical grid independent tests. Now coming to the results and discussions, figure 3 shows the variation of Nusselt number with Rayleigh number for different L by D ratio. As we can see from the figure that Nusselt number rises with an increase in Rayleigh number for a given L by D ratio, and for a specific Rayleigh number, Nusselt number increases with increase in L by D ratio. The Nusselt number computed here is only for the outer surface of the cylindrical cavity. Figure 4 shows the static temperature contours for different L by D ratio. Here L by D is varied, keeping the length of the cylinder fixed and dia is changed. Rise in L by D ratio signifies a decrease in diameter, as we can see in the contour. As the temperature of the cylindrical wall is fixed and it is higher than the ambient temperature, the air which comes in contact with the cylinder gets heated, so it becomes lighter and moves in upward direction. It is observed that temperature is maximum near the wall of the cylinder, okay, and it decreases in the vertical upward direction. When L by D decreases, right, the area inside the cylinder increases. For higher L by D ratio inside the cylinder, the temperature inside the cylinder is more uniformly distributed. Whereas for smaller values of L by D, a variation in temperature inside the cylinder is noticed. Variation of temperature with the axis of cylinder is shown in figure 5. It is noticed that temperature first increases, reaches maximum, then it starts to decrease. As from the temperature contours, it can be seen that temperature is maximum inside the cylinder. The same thing we observed in this case of temperature variation along the axis. Figure 6 shows the variation of Nusselt number with the fall distance. It is essential to mention that a sudden fall in Nusselt number is noticed. Again, Nusselt number rises and reaches a saturation value. At a given wall distance, we can see Nusselt number increases with rise in the Rayleigh number. Coming to the conclusions, these are the following conclusions made from the results ahead. The Nusselt number increases with increase in Rayleigh number as well as L by D ratio. The static temperature contours show that the temperature is maximum inside the cylinder and near the wall, and it gradually decreases in the vertical upward direction. The temperature is found to be maximum on the axis of the cylinder when the temperature is plotted as a fraction of axial distance. These are the references.
Thank you, Bismay. Bismay, you are present, no?
Yes, sir.
Yeah, Bismay, what model have you used to couple the flow with temperature?
Sir, again?
what model have you used to two-way couple the flow and temperature?
Sir, we use the simple algorithm.
No. For coupling the flow and temperature, is it the Booz-Nix approximation that you have used?
Yes, sir. Booz-Nix approximation.
Okay, Booz-Nix approximation. Okay. What are the drawbacks with Booz-Nix approximation?
Sir, it is means the density is means constant every in that in this everywhere except in the gravity. So it varies in gravity.
How good is Booz-Nix approximation at higher values of Rayleigh number? Okay, any other question from audience?
Hello.
Hello, yeah.
Yeah, I have one question that how accurate is this Booz-Nix approximation is?
Yeah. Bismay, can you respond?
Yes, sir.
Yes. Yeah.
Now, sir, I am actually studying deeper into this, and I will look forward to it, sir.
Okay. Okay, then, if there are no further questions, let us move to the next presenter. Please start 129, paper number 129.
Hello, I am Dr. Ashok Kumar Barnwal from Department of Chemical Engineering, BIT Mesa, Ranchi. I am presenting on topic free convection from two cylinders of different diameters in a square duct. My presentation contents are these: introduction, schematic representation of domain, governing equations, numerical solution methodology, validation, results and discussion, and conclusions. Follows the Newton's law of viscosity is called Newtonian fluid. According to Newton's law of viscosity, shear stress is directly proportional to shear rate, and proportionality constant is called viscosity. Shear stress versus shear rate looks like a straight line passing through the origin. In power law fluid model, shear stress is m times shear rate to the power n, where m is consistency index and n is flow behavior index. When n is equal to 1, the power law fluid model is converted to Newtonian fluid. Example for Newtonian fluid is water, oil, glycerin, etc. Now, schematic of flow domain. Present study considers bigger hot circular cylinder and a smaller cold circular cylinder within an isothermal square cavity. Cartesian coordinate is on the center of a square cavity. There is Newtonian fluids in annulus between a square cavity and circular cylinder. Square cavity is at the same temperature as a smaller circular cylinder, and bigger circular cylinder is hot at theta is equal to 1. Initially, fluid is also at the same temperature as a square cavity. Bigger hot cylinder is surrounded by cold fluid and a smaller cold cylinder. So heat is released by bigger circular cylinder is received by fluid and cold circular cylinder and a square cavity. Three triangular elements with non-uniform spacing have been used to mesh the computational domain as shown. For solving this problem, assumptions related to fluid properties and flow are as circular cylinder and a square cavity is long enough in z direction, so we assume two-dimensional steady and laminar flow. In compressible fluid, except for the body force term, thermophysical properties are independent of temperature. Viscous dissipation effects are also assumed to be negligible. So this is the during this presentation, we will see the effect of kinematic and geometric parameters on momentum and heat transfer characteristics. So based on these assumptions, non-dimensional governing equations are as follows: equation of continuity, momentum equation, and energy equation. Dimensionless number appearing in the non-dimensional governing equations are these Grashof number, Prandtl number. These are the boundary conditions. These are the dimensional boundary conditions, and these are the non-dimensional boundary conditions. So at the surface of circular cylinders and cavity walls, boundary condition for flow is 0. That is no slip boundary condition. And non-dimensional boundary condition for temperature is 0 at a smaller circular cylinder and cavity walls. And theta is 1 for bigger circular cylinder. The governing equations are made dimensionless by using the scaling variables like theta for temperature, L for length, UR for reference velocity, rho c UR square for pressure, mu times UR upon L for stress components. To measure the variation of density in Y momentum equation, Boussinesq approximation is used for the density variation in body force term, where beta is coefficient of volumetric thermal expansion of fluids. Governing equations with non-dimensional boundary conditions have been solved numerically by using finite element method based solver COMSOL multiphysics. For the present study, using Paradiso scheme with two-dimensional steady laminar flow module and relative convergence criterion for the equation of continuity momentum energy is 10 to the power minus 5. Present study covers the range of dimensionless parameters Rayleigh number from 10 to 10 to the power 6 at Prandtl number 0. The accuracy of numerical results are strongly influenced by the choice of numerical parameters like quality of grid and convergence criterion. It is thus essential to choose an optimal grid for the numerical results to be free from such numerical artifacts. Both the momentum and the thermal boundary layer are expected to thin with the increasing the value of Rayleigh number. So based on this consideration, grid independence test has been carried out at the maximum value of Rayleigh number. As move from grid G2 to G3, relative error is very small, less than 1%. So grid G2 is taken for further study. Before presentation and discussion of the new result, it is desirable to establish the accuracy and reliability of the solution procedure. So in order to validate the accuracy and reliability, comparison of distribution of local Nusselt number along the surface of the square cavity have been compared with Park et al. And this is a very good agreement. For different value of Rayleigh number, the velocity and temperature fields are represented as the streamline and isotherm contours. For heat and momentum transfer, the diffusive and convective transport are the main mechanism at a smaller and higher values of Rayleigh number respectively. Even at low values of Rayleigh number, 4 recirculation zones are seen to form, 2 above in opposite sense of orientation and 2 below the cylinders. The recirculation edge in the top part of the cylinder stretches due to enhanced convection at higher value of Rayleigh number, while the size of that at bottom part of cylinder decreases. Due to availability of spaces in the vicinity of bigger cylinder, the streamlines and isotherm contours are seen to be more crowded in between the wall of a square duct and hot cylinder than in between the cylinders. The velocity and temperature gradients are sharp in a smaller space available at the surface of the bigger cylinder in the side of wall of a square duct. Streamlines and isotherms are seen to be symmetrical about the horizontal center line of a square cavity at the low Rayleigh number, whereas this symmetry is lost at higher value of Rayleigh number. Further, thermal plume formed at the top part of the bigger cylinder becomes stronger as Rayleigh number increases. Heat transfer characteristics are generally examined in terms of the distribution of Nusselt number. Figure shows the distribution of local Nusselt number. As Rayleigh number increases, local Nusselt number also increases for higher values of Rayleigh number. Effect of Rayleigh number is more pronounced in between 60 degree to 200 degree. At Rayleigh number 10 to the power 5, the peak value of the local Nusselt number at 0 degree is more than that of at the 180 degree, because isotherms are more crowded at 0 degree than that of at 180 degree. Now at Rayleigh number 10 to the power 6, buoyancy currents increases dramatically, such that peak value of local Nusselt number at 120 degree is same as that of at 0 degree. At low value of Rayleigh number, effect of buoyancy is less with respect to effect of availability of species, while these effects are comparable at higher value of Rayleigh number. This is the variation of surface average Nusselt number for bigger circular cylinder. Figure shows clearly that heat transfer rate increases clearly with the increasing value of Rayleigh number. Now, conclusions. Due to the gradual thinning of the thermal boundary layer, the isotherm contours are crowded in the limit of high Rayleigh number. At low value of Rayleigh number, effect of narrow gap dominated over the effect of buoyancy, while adverse effect is seen at higher value of Rayleigh number. The average Nusselt number value on the surface of the bigger cylinder and wall of a square duct increases as compared to when both cylinders of same dimension as larger diameter. Average Nusselt number value on surface of hot cylinder increases due to decrease in diameter of cold cylinder as compared to diameter of cold cylinder taken by Park et al. These are the references which I have used in making this presentation. Thank you.
Yeah, any question from the audience? Dr. Barnwal, thank you very much for your presentation. I would request some questions from the audience. Any question from the audience? Yeah. Dr. Barnwal, did you vary the diameter of the cylinders as well?
Sorry, sir.
Did you vary the diameter of the cylinders as well? The gap also?
No,
accordingly?
sir. No,
No.
sir. Both
It was
cylinders
all
are
for fixed cylinder diameters, correct?
Yes. Yes, sir.
Yeah, I would have been happy to see some kind of flow current to really visualize the buoyancy driven effect, correct? How the cylinders contribute to the buoyancy effect. So you have only shown temperature contours, no velocity profiles.
No, sir. A streamline is shown here.
Yeah, there is a plot for the streamline as well.
Yes.
Yeah, okay, okay. So what is your observation in terms of this? What will be your observation in terms of the cylinder diameter? If the diameter of the cylinder is reduced to a very small one, what do you expect?
Yes, sir. Heat transfer is increasing.
Or when you reduce the cylinder diameter?
Yes, sir. If we reduce the cylinder diameter of cold cylinder, then a hot cylinder is of bigger diameter, so heat transfer increases.
Okay, why do you say so?
Because, sir, heat transfer is increased. Surface area of a cold cylinder is decreases.
Okay, that is why. Okay.
Yes.
Okay. Okay, thank you, Dr. Barnwal. Let us move to the next presentation.
Thank you, sir.
Hi, greetings to all. My name is Shiva K. Battina, working with Professor Sudhir Siddhap Reddy from Indian Institute of Technology, Dharwad, India. Today I am going to present a study of fire and evacuation simulations of Kumbakonam school fire accident. The outline of the presentation is motivation and object of the study, discussion of the Kumbakonam school building, numerical simulations, resultant discussions, conclusions, and references. With the growing number of high-rise buildings as well as the gradual aging of existing buildings, all kinds of hidden danger of accidents are also increasing, especially in building fire, which are at great risk to strike. It is quite remarkable that in building fires, many people get choked due to failure of evacuation timely, thus increasing the huge loss of life and property. Experimental studies in evacuation scenarios neither practical nor impossible or economical. Numerical fire evacuation studies might be a substitution of real-life fire evacuation experiment up to a great extent. Also useful to improve the fire safety standards in such buildings. In this work, fire and evacuation simulations are performed to validate the tragic Kumbakonam school fire accident. Before going to the details of the study, I would like to give the brief details of Kumbakonam fire accident, how it was done. Kumbakonam school fire accident happened in a school in Kumbakonam town in Tanjavur district in the state of Tamil Nadu. The students of the primary section of the Krishna English medium school were burned to death in their classroom. The incident occurred on 16th July 2014. The cause of incident was thatched roof that caught fire. The accident was one of the 4 major accidents and large school fire accident in Tamil Nadu, and second in terms of casualties of school fire accidents in India. A geometrical building model is prepared to replicate the real-life fire accident. All the details of the building are taken from the data available over the internet. The red color portion of the building are representation of thatched portion of kitchen, cycle stand and classrooms. The figure shows the whole building and second floor of the building. In this, dry gas was used as thatched material for the building roofs, and material properties were taken directly from the validation example file. The other walls are simply kept as inert. Coming to the doors and windows information, 2 doors have been used on the second floor, 1 in each staircase for the exit. Similarly, 4 doors are used on first floor, 2 in each staircase, 1 door for entering and another door for exiting. Similarly, 4 doors are on the ground floor. Although there is one main exit door on the ground floor, a person who crosses the main exit treated to be safely evacuated from the building and removed from the calculations. Coming to the windows information, there are 21 windows on the ground floor, where 2 windows are placed in the kitchen and other 19 are there in the classrooms. Similarly, 13 windows are there in each floors. All are placed in the classrooms, and there are 2 other holes made on the first floor which were used as doors. The staircase information, 2 staircases are there, one inside the building and other one just near the main exit. And there are 750 agents have been placed inside the building, where 300 agents are there on each first floor and ground floor, and remaining 150 are there in second floor. All the agents are treated as children, and their properties have taken as default values in FDS and evacuation. And the simulations are run in for 1500 seconds, which is 20 minutes, which is estimated time that takes for children to get out from the building. In the present work, fire dynamic simulator is used for simulating the fire and evacuation scenarios. FDS is a CFD code. It consists of large FD simulations and direct numerical simulations as models. In the present work, LES large FD simulations are chosen since it offers less time demand than the direct numerical simulations. Some of the default features of the fire dynamic simulators are given here. Those are, it works with low Mach number flows with LES, and it uses explicit second order energy conserving numeric with the structure grids, and the species are treated as a lumped species approach. Mainly it has 3 lumped species. One is air, product, fuel, and the turbulence is treated with Dierdoff-G viscosity closure, and constant turbulent and Schmidt Prandtl numbers are used. Combustion is treated for infinite frost chemistry between the fuel and oxidizer, and the radiation is treated by default gray gas radiation with finite volume solution to the radiative transfer equation. Computational setup and boundary conditions. The simulation domain of 160 by 56 by 48 as length, breadth, height is considered. The fire vent was placed in the kitchen having 1.5 meter square surface area. The cellulose was used as a fuel having heat of combustion 15,600 kilojoule per kg, and the soot yield of 0.02 is considered. Heat released per unit area is prescribed as boundary condition, which was assumed to be 1500 kilowatt per meter square, and this value was taken from the validation file. For evacuation scenario, the simulation domain was 210 by 80 by 1 as length, breadth, height is considered, and the simulation is run for 1500 seconds, that is 25 minutes. Resultant discussion part. In this figure, movement and evacuation of the children is shown with respect to time. For example, t equal to 600 second and t equal to 1300 second. Agents are shown in blue and gray color. They are just 250 agents on the ground and first floor, and 150 agents are there on the second floor. They have just started running at time equal to 8 seconds, whereas many students have evacuated from the building by time equal to 600 seconds. From the results, it was obtained that 426 agents evacuated at t equal to 600 seconds, whereas 61 agents were dead. A total of 439 agents have evacuated the building and 150 were burned to death by 1300 seconds. Resultant discussions are continued. In this slide, a video is attached to show the movement and evacuation of the agents with respect to time. I am playing this video. In the previous slide, movement and evacuation of the agents are discussed. The movement and evacuation of the agents are directly related with suit density. It takes at time equal to 8 seconds, the suit started occupying the building. It took around 1 minute to fill the whole building with soot. Around half of the ground floor is filled with smoke within 8 seconds, whereas soot has fully engulfed the building at time equal to 600 seconds. Similarly, the building is full of smoke, which is shown in figure at time equal to 1300 seconds. Soot density at a time equal to 8 seconds is very high in the fire vent area where the fire began. Then it started increasing the other regions of the fire, other regions of the building with an increase in time. From the soot pattern, it can be analyzed that soot density is high near the wall because it doesn't get path to get escaped from the building. Hence, there should be enough vents available in a building for smoke to escape out the building when the fire accident occurs. In the previous slide, soot density is discussed. In the current slide, soot visibility. Soot visibility is depend on the soot density inside the building. So, wherever there is a high soot, visibility will be less and vice versa. At t equal to 8 seconds, soot visibility is low only in the fire vent area, whereas at time equal to 600 second and time equal to 1300 second, not represented here 1300 second, soot visibility is very low in the whole building since the building is full of smoke. Low visibility prevents the students to evacuate from the building and their running speed decreases, which results in death. Results and discussions are continued. Fractional effective dose. It is a measure of airborne contaminants absorbed by an occupant. If the fractional effective dose is more than unity, the person is treated as incapacitant. The overall fractional effective dose change is found to be linear as shown in the figure. So, from the figure, it can be seen that FED value first exceed unity at time equal to 72 seconds. And also first death also happened at the same time. So it can be seen that FED is responsible for death happening inside the building. Evacuation of agents from the main exit. The figure shows the overall evacuation of the agents with respect to time. A linear evacuation is seen until 460 seconds, and after that the evacuation is steady state. At time equal to 460 seconds, the total number of evacuated students are 422. At time equal to 1300 seconds, 439 students have evacuated from the accident. Very little change after 430 seconds because of the smoke and fire have already occupied the whole building. So evacuation is near to impossible. Conclusions. The present study concerns the validation of fire and evacuation simulations of Kumbakonam fire accident. The conclusions can be drawn from the present study are 439 students have been evacuated and 140 were died. The rate of evacuation is 1 person per second from the main exit. A total 94 students were burned to death in the actual incident, but in the simulations there were 140 were dead. So 48% of deviation in the deaths from the real incident. The reason for the deviation might be assumptions made in the simulation parameters like selecting the fuel, and the fuel is directly depends on the suit, and the suit is directly dependent on suit density and visibility. And also the deviation might be representing the aged building in the simulation as leak proof walls, and roofs also represented as leak proof walls. So in the real life incident, the Kumbakonam school is aged building, and it might be there may be a holes in the walls and the openings in the roofs, and the roofs are represented attached. So more simulation should be done with different fuel to replicate the real life fire accident. These are the references cited in the present work. Thank you.
Thank you, Shiva. It was a good presentation, and I'm happy that you could also keep yourself in the presentation while speaking. Shiva, I have a basic question. How did you model the suit formation? Hello? Hello, am I audible?
Yes, sir, you are audible.
Yeah, Shiva, how did you model suit formation?
I think he's not here in the.
Oh, he is not there?
Yes.
He is not there at all? So there is no one to take the questions?
Yeah, maybe if his co-authors are there, maybe they can answer this question.
Anyone else is there to take it up? Okay, in that case, we move to the next presentation, 147.
What? Sound better?
Hello everybody, myself Saurabh Joshi. I am a PhD student in the Department of Mechanical Engineering, IIT Madras, working under the guidance of Dr. Kameshwar Anapindi and Professor BVS. Today my topic of presentation is the simulation of flow over 3 side-by-side circular cylinders. The objective of the present work is to investigate the wake characteristics, turbulence anisotropy in the wake, that is to determine the directional dominance of turbulence in the wake, then the process of energy cascading, that is transfer of energy from larger eddies to smaller eddies, then the mechanism for the momentum transport for the flow over 3 side-by-side circular cylinders. The above objectives are achieved by studying turbulence statistical quantities, Lumley triangle, energy spectrum, and the phase averaging technique respectively. Then geometry and the computational setup. The schematic shows the computational domain with front and the top view. In this figure, the 3 cylinders are kept side by side with a distance of 1.5 d. D is the diameter of the cylinder. The coordinate system is placed at the middle of center cylinder, and the inlet was kept 10 d upstream, and the outlet was kept at the 30 d downstream. This front and this top and the bottom plane were kept at the distance of 15 d, and this is the flow direction. This view shows the top view in which this front and this is the back plane and were placed at the distance of 5 d. The cylinder was defined with this is cylinder and was defined with the no slip condition. This table shows the boundary conditions I have applied for this computational domain. The velocity at inlet was defined with the directly condition, and the outlet was the nymon. This cylinder was defined with the no slip condition, and this front and back plane was defined as a periodic, and this top and this bottom were defined as the symmetric plane. For the pressure, inlet was defined as a zero gradient and outlet was defined as an advective to avoid the reflection of pressure wave inside the domain. Like a velocity boundary condition, pressure boundary condition for top and bottom was also defined with the periodic and this front and back as a symmetric plane. Now results. The grid sensitivity test and validations are presented here. This picture shows the grid I have used. I have used non-uniform grid in which the grids are refined very fine near to the cylinder surface. And away from the cylinders, where the flow is not too much chaotic, I have used a larger grid. And this inside view shows the grid near to the cylinder. Here we can see the dense mesh near to cylinder, and away from cylinder is forcers. This figure shows the validation study for Reynolds number of 5800. The grid sensitivity test was started with the 2.7 million cells and increased up to 3.91. Here we can see that the difference between 2.76 and 3.33 million is quite, there is a little bit difference, but in the 3.33 million and 3.91 million cells, it is getting overlap. Though all three curves are getting overlap up to y by d equal to plus minus 2.5, but there is slight difference between the 2.76 millions and 3.33, but there is no difference in between 3.33 million and 3.91 million cells. So throughout the simulations, I have used 3.91 million cells as my final size, and I have used this mesh for the all simulations. Also, the mesh validation is performed for the highest Reynolds number, so that's why same mesh was applied for the lower Reynolds number also. In this figure, we have compared the present simulation results with the experimental result of Zhang et al., in which we can see the good match in between y by d plus minus 2, but there is slight deviation after which. This is because away from the cylinder, I have used coarse mesh, so that's why results are deviating. But at other places, it is well matched with the experimental result. Then the variation over cylinder surface. These two figures show the variation of coefficient of drag and lift for top and bottom cylinder. In this figure, the coefficient of drag is shifted by 0.16, which means if we subtract the value of 0.6 from this value of curve, then we will get the actual value of coefficient of drag. So you can see that the coefficient of lift for middle cylinder is 0, but it is not the case for the top cylinder, because for middle cylinder the forces acting from top and bottom cylinders are getting nullified, causing the mean coefficient of lift to be 0, which is not the case for top cylinder. The computational error I have observed for the this mean cylinder, this coefficient of lift for middle cylinder is 0.08% for the highest Reynolds number considered, that is 5800. Then this figure shows the time average wall shear stress for top and middle cylinder. Here we can see that as increase with the Reynolds number, the value of maximum shear stress is also increasing, because with increasing Reynolds number, the boundary layer thickness is getting decreased, which causing the increasing the gradient of velocity and results in the higher shear stress. We can see that the difference for the maximum value of wall shear stress at the lower Reynolds number is low, but as the Reynolds number increasing, the difference between the peak value is also increasing. This figure shows the zoom view of the point of flow separation for different Reynolds number. Here you can see that the point of flow separation is not the constant, but varying slightly, which is varying from 78 degrees to 33 degrees for the top cylinder and 98 degrees to 102 degrees for the middle cylinder. Unlike this point of flow separation, we can see that the angle at which the maximum shear stress is occurring is constant for all the Reynolds number, which is observed to be 39 degrees for the top cylinder and 65 degrees for the middle cylinder. Then the turbulence anisotropy map was also studied to determine the directional dominance of turbulence stresses in the wake. These three figures are plotted over these three lines. First figure along line A, second is along line B, and third one is along line C. We can see that in this figure the positive zeta indicates that the turbulence is dominant in the one direction and other two components are vanishing. This negative zeta line indicates the two directional dominance and third direction is neglecting, means very small value. And if the points are near to this origin, then it shows the isotropic, means all three components are equally dominant. So in first figure we see that the most of the data are located near to positive digital line, and the very small data is near to inside the triangle or near to origin, because we can see that the line which is lying inside the recirculation zone have the turbulent flow. That's why small portion is near to the origin, but the most of the portion of this line is is staying away from the recirculation zone, over which the string-wise component of velocity is dominant over the remaining two. So that's why this means only one component is dominant. That's why most of the data is lying near to positive digital line. We can see that in this figure most of the data is lying in between the. It is also near to one positive zeta and negative zeta, and also lying inside the triangle. This is because this line is passing through the recirculation zone, which is the portion of highest turbulence, because after the flow separation from the cylinder, in this portion the flow is highly turbulent, highly curved. So that's why most of the data points are lying randomly, which is neither near to any curve. But the line C is after the recirculation zone, which means at this portion only one directional velocity. So that's why most of the data is staying near to the positive digital line, but there is small portion which is over the negative zeta, because at the end of recirculation zone, because of vortex shading, the transfer velocity is also dominant. So that presence of transfer velocity we can observe in the in terms of small portion of data lying near to the negative zeta line. Here, the process of energy cascading was studied with the power spectrum distribution. In this, for this, we have collected data over three locations. The first one is located behind the top cylinder. Second one is located behind the middle cylinder and inside the recirculation zone. And third one is located outside the recirculation zone. We can see that at all the locations, the energy contained in a number of 100. The locations, energy contained for the real number of 1500 is smaller. Also, we can see that the process of energy cascading starts at the at all the locations. We can see that the slope of -5/3 indicated in all figures, which means in the present simulation we are able to capture the inertial seepage, which gives the correctness of our computational domain and also the discretized computational domain. Then in our present simulation we have observed multiple frequency of oscillation. One is higher and other is lower, as there are for top cylinder and one big one for the middle cylinder. So this higher frequency of oscillation is for the two smaller recirculation, smaller wakes, and lower one is for the bigger wake, which is behind the middle cylinder and after the merging of all three vortices. Between the higher compared to difference between the 1300 to 5000 Reynolds number. That's why this Reynolds number is called as a lower Reynolds number. So conclusion from this my study is that the maximum wall shear stress is less for middle cylinder compared to the top and bottom cylinder, and the difference between this maximum wall shear stress is proportional to the Reynolds number. The angle of maximum shear stress and the flow separation do not vary too much with the Reynolds number. For all Reynolds number, it is nearly same value we have obtained, and it is not varying too much with the Reynolds number. The anisotropy study shows that the flow is highly three-dimensional just in the vicinity of cylinder, and away from the cylinder, each string by component is dominant over the other two. Then from the study of energy cascading, we have observed that there are more than one frequency of oscillation. One is higher and one is lower, and the higher frequency of oscillation is corresponding to the lower recirculation zone behind the outer cylinders compared to the inner cylinder. The phase average results show that highest turbulent kinetic energy and the strong vortices are generated at the smaller recirculation zone, and they are getting with the full stream flows, and as the flow gets advances. Thank you.
Hello?
Hello, yeah, am I audible?
Yes, sir, you are audible.
Yeah, Saurabh, are you there?
Yes, sir, I'm here. Yes, sir.
Yeah, Saurabh, you have done an alias simulation, am I correct?
Yes, sir, alias simulation.
Then what kind of a subgrid scale model you have used? Because the wall shear will significantly depend on the subgrid scale model. Yeah.
Yes, sir, yeah. I have used a scale model.
Oh.
We didn't got a good result with the K equation model.
And what level of delta T you have used for your simulations?
I have used adjustable time step, means based on a Coron number, it will automatically adjust the time step. So I have to give the criteria of Coron number to be less than 1. So based on that, it will automatically vary the delta T.
Yeah. Hello, Saurabh.
Yes, sir.
Yeah. What was the delta? Huh?
Can you hear me?
Yeah. What delta T have you used?
Yeah, it depends on Coron number. Means I have used.
Okay. Okay. So
I
yours
define
was
Coron number to be less than 1. So automatically that it will adjust the time step.
Okay. Then how did you average? What level of averaging you have done? How did you average the value? Time averaged over what time period?
Yeah, actually there is one paper which is stating that means that gives the minimum criteria. It says that there should be minimum 40 number of cycles we have to average. But for present simulations, I have considered 60 cycles.
Okay. Okay. Thank you, Saurabh. We are anyway running out of time. Thank you very much. It was a good presentation. So I thank all the participants, all those who are present here, who have been listening, and thank the organizers also for having this nice conference done on virtual mode. Thank you very much. I leave here. Thank you all.
Yeah, thank you, sir.
Thank you.
Thank you.
So with this, we come to the end of this session. So thank you, Professor Banerjee, for your valuable time and such a smooth sessioning of this session. So we will take a tea break for 15 minutes. We will assemble here again at 11:45 for a plenary lecture by Professor Franz Durst. Thank you.
पूरा लेके जाइए पूरा लेके जाइए
ओके
तो
क्या है इसका आवाज बंद कर दिया जस्ट अच्छा इसका आवाज बंद कर इसका आवाज
आ रहा है
Vous allez l'écrire à l'instant.
Tu es trop grand pour comprendre des choses aussi petites.
So in the mid region of plane B, you can see a higher dissipation rate. And this is much clearly seen in the frame D. You can see that the LSC is marked by the diagonal line, the dashed line. And on the opposite side, there is a top right corner and the bottom left corner. There are regions associated with high dissipation rates. So these are due to the interaction between the two corner vortices, the counter rotating vortices of the four-roll structure. Now, yeah, can you please move on to the next slide? So with this, I wind up my presentation. So these are the main conclusions of the study. We have been able to identify, we have been able to attain a very high Rayleigh number regime, and in which we have identified the LSC and the four-roll structure in different planes. Then we have quantified the vertical velocity in the LSC and non-LSC plane, and also seen how it varies with increase in Rayleigh number. So as the Rayleigh number increases, the strength of LSC increases. It becomes more dominant and wall bounded. Then finally, we have studied how it affects the boundary layer and the dissipation rates. To get more information on this study, you can always refer to our recent paper in Physics of Fluids. So thank you.
Thank you for the presentation. So if anybody has any question, please ask. Okay, so if nobody has any question, thank you very much to the presenter. Then I believe this session is finished. Then we can, the next session can be started basically.
Okay.
Sir, we are extremely sorry for the glitches you found during this, and for the participants, it was quite difficult to do that. So we apologize for that.
Not a problem. Thank you very much. So I appreciate actually participants or presenters. Yes, they have quickly actually finished their thing and make up the thing basically at this moment. Thank you all.
Okay, thank you, sir.
Okay. Thank you very much. Thank you very much, Professor.
Okay, thank
you.
So then I'm leaving. Okay.
Okay. Thank you, sir. Good morning. Hello, Professor Talukdar.
Good morning. Good morning.
Good morning. So can we start the session of Professor Drush?
Yes, I'm ready.
Okay, sir, you can introduce about Professor Drush, then we'll start the video.
Sure. Good morning, everyone. A very hearty welcome to Professor Drush, organizers and participants of FMFP. It gives me immense pleasure to introduce Professor Drush and sharing this session of FMFP. Thanks, Professor Dalal, for giving me this opportunity to share this session of Professor Drush. It's not easy for me to introduce Professor Drush with a few sentences. I met him back in 2002 at IIT Guwahati, just in front of the guest house, which was used temporarily as a conference hall at that time. I came to know about this person a lot when I worked with him at his institute for a longer period of time. He headed this institute of fluid mechanics with more than 80 staff, out of which probably about 50 plus people were basically PhD students, postdocs, and many guest professors. More interestingly, there are always a lot of Indians in his institute at any point of time. If you see any of the old IITs in India, you'll find at least 2-3 faculty who worked with Professor Drust at some point of time. If you see, he's a professor full of ideas, full of enthusiasm, extremely hardworking, and one of the renowned person in fluid mechanics in Europe. A brief bio about him. Professor Drust studied aeronautical engineering at the Technical University of Stuttgart in Germany and completed his MSc and PhD degree at the Imperial College of the University of London. Afterwards, he worked as a special research center at the Technical University of Karlsruhe, Germany, before he became a full professor at the University of Erlangen-Nuremberg, also which is in Germany. After retirement in 2007, he opened up his own company, FMP Technology, as a CEO, where he is still active. He continued there his research work in fields like laser Doppler anemometry, laminar and turbulent flows, extended Navier-Stokes equations, microchannel flows, coating and drying equipment, etc. For his work, he obtained various national and international prizes and is a member of 5 scientific academies. I request Professor Drust to start his lecture, which is Solutions of Some Unresolved Problems of Fluid Mechanics. Professor Drust, please.
Thank you. Good morning, everybody. Welcome to my presentation on solutions to some unsolved problems of fluid mechanics. I'm glad you could come. Usually I see in the audience whom I am talking to. That's now not possible, but I hope that quite some people will listen to this presentation. Let me start out to thank Professor Dalal and the organizing committee to invite me to this presentation. And I was hoping that I can use the conference as an excuse to visit India once more and meet many friends here who usually come to this meeting. Let me now briefly explain what I mean with solutions and unsolved problems. But before I do this, let me show you some historical picture here. I have drawn here on this picture the names of the various contributors to fluid mechanics. As you can see, it is quite a number of people who have contributed to the development of fluid mechanics. Usually we start out with Leonardo da Vinci, up here, and go then down through Bernoulli, through Euler, through Laplace. But I think the major contributions and the ones most important for my presentations is Navier and over here Stokes. They derived the Navier-Stokes equations, and we are using them these days for getting solutions to fluid mechanics problems. I'm asking whether they are really problems. Are they not just tasks which we can now solve with these equations, and we can solve them with numerical methods, analytical methods, and experimental methods? We are in this time now where the necessary methods for measurements, methods for computations have been developed. The golden age of fluid mechanics exists, but as you will see, there are still some problems we cannot solve properly in fluid mechanics. Let me start out to explain the kind of problems I would like to tackle, at least to introduce you to some ideas about these problems. A problem does, in my opinion, not exist if you can solve it analytically, if you can solve it numerically, or investigate it experimentally. That is a fluid mechanics task, and we can get a solution by these methods we have available and the suitable equations or the test equipment. But a real problem is in fluid mechanics if we get theoretical solutions by solving the Navier-Stokes equations here, the continuity equations and the energy equation. And if you then investigate the flow experimentally and there is a difference. And now you have to decide what is the problem. You have two solutions. Both solutions are correct, but there is a difference. That are the kind of fluid mechanics problems I would like to talk about. Here now, one of these problems, microchannel or microcapillary flows. Here you see on the right, on the left-hand side, the results of Maurer for mass flow measurements, the mass flow through the microchannel. Theoretically, solving the Navier-Stokes equation, we get this solution, a parabolic velocity profile. If you go to smaller and smaller channels, and of course, higher and higher pressure differences, as you can see here, you find you get a difference between the solution to the Navier-Stokes equations and the measurements. This is now the kind of problem we have. And of course, we can not solve this problem really by modeling, because we would have to model the molecular interaction with its rough surface. So here is now the kind of problem I think we have and we need to solve somehow. You get a higher mass flow rate through a small channel than you should get solving the Navier-Stokes equations. Now, very often we think this is a microchannel flow problem particular to this flow. This is not the case. Have a look here. There's no channel. You have an obstacle in a supersonic flow and you get a shock. And this shock wave, as it's called, has now an ideal solution, which is this line here. So the pressure, the density in this case changes at this location. Experimentally, you find a change given by these points. And the line is the solution coming from the Navier-Stokes equations. The difference is there between experiments and theoretical solutions of the equations. And of course, now we have the kind of problem we would like to solve. There is a third problem I've indicated. This is a flow through a pipe. The flow is turbulent and it is heated from the wall. You can see this from the temperature distribution. Of course, as you go downstream, what you have is the velocity U increases because of the expansion of the flow, and also the temperature increases because the flow is heated from the walls. And again, you see now the theoretical solution and the experimental findings disagree. Of course, here now it can be that the K epsilon equation is incorrect, but some hints are also there that we have a similar problem to microchannel flows, and this is what I would like to explain to you. Have now a look at the equations. See if the equations, the predictions are not agreeing with the experiments, and we have the initial conditions and also the boundary conditions correct, then there must be a defect in these equations. And this I would like to point out. Let us start out with the Navier-Stokes equation. You have here on the right-hand side, you have the molecular transport of momentum. Don't call it friction. It is the transport of molecules of momentum. Similarly, you have in the energy equation the molecular transport of heat, of energy. But have a look at the equation here of the mass. There is no molecular mass transport in these basic equations of fluid mechanics. This is the major reason why we get these defects in some of the flows. Some of them I have indicated. So with a conventional Navier-Stokes equation, we have no mass diffusion. And if we now introduce this mass diffusion, we get the extended Navier-Stokes equations. And I will use these shortenings here to explain which kind of equations I'm using. Here now, the explanation for the missing term of diffusive mass transport, so molecular mass transport. Have a look at this checked area. Through this checked area, this can be the area of a cube. Through this checked area, you will find that molecular motions will transport mass. So there's a mass transport from here to through the checked area. It's indicated at that point. The last time the molecules interact with other molecules is one mean free path away from the checked area. So then the properties um and rho at this location are transported up. There's also a transport of the molecules down through this, from this upper area. And this is now that combination of properties that enters the mass transport by molecules. Minus if the transport is downwards, plus if the transport is upwards. is given here for. You can now take series expansion, and then you will end up with these terms. And you can now build the products between these terms, and when two terms are different, have these different operators in them, we take them out, being smaller than the terms that consist of these terms here, or combinations of one term with a gradient. At the end, you end up with this mass transport by the molecules. And you can see it depends on the mean molecular velocity and the mean velocity of the molecules and the gradient of density, or the density and the gradient of the velocity. So you end up with this equation. Now you can use the ideal gas law and get now the correct derivations here, expressed once in density and temperature and once in pressure and temperature. Out comes two terms. This is fixed mass diffusion term. And then the temperature term here is Sore's mass diffusion term. So both terms are known, for example, in physical chemistry. And they are used there, but we are not using them in the mass transport equations of fluid mechanics. If there is mass transport, there is also energy transport, heat transport. So we can now do the same thing. There is heat transport from the bottom, there is heat transport from the top, and this is the top one down, and this is the bottom one up. And you can again take the difference, and then you get the diffusive transport of heat by molecules. Again, you can now derive this expression, and you might see that this is the mass transport, and multiplied by Cp times T gives you now the additional heat transport there is. This heat transport comes from the mass transport, which we are missing in the in the mass transport equation. And at the end, you get an expression here for the ideal gas, and you can do it also for the ideal liquid, as I show later on. As a last term, we have the transport of momentum. Here you can see the transport of momentum we usually have. It's This is very important. And then you have now again, due to the mass transport, which we are missing in the continuity equation, times uj and ui, that are the momentum transport terms that you get additionally in the Navier-Stokes equation. So we have different equations, and they are now shown here. And you can they are very similar, but in this velocity you have now the convective velocity and the diffusive velocity. Here also. And this is now the tau ig term, which is also expressed in terms of total velocity. If you now put in the ideal gas law, you get this equation. And then you end up with a full set of equations you can also solve, but for total velocity, you get the convective and the diffusive velocity. This is the diffusive part, or this is the diffusive. For an ideal liquid, this is the equation. The T here should be an XI, so I'm sorry for this. Now, let's take now these extended Navier-Stokes equations and solve it for microchannel flows. What you get now is this solution for the pressure difference Maurer used. And if you now do the computation for that pressure difference, you see that the numerical solution goes, also the analytical solution, which is possible here, goes directly through the data of Maurer. We do not need any modeling. We do not need to take care of this complex structure of the wall in order to get slip flows introduced. I can also not imagine how you can deduce slip flows from this kind of a rough wall interacting with molecules. Now, let's look at the shock wave. Here you see the Navier-Stokes equations. That's the ideal gas without any viscosity you would lie here. Then if you take the solution by the conventional Navier-Stokes equation, you end up with this line. So there's a difference between the experimental results and this numerical solutions to solve shock waves. Of course, you can now model again what I have done here with a combination, but you don't make it quite. But if you now solve the extended Navier-Stokes equations, the line goes straight through the experimental results of Maurer. Here now let's look at the turbulent case. The dark points are the numerical solution with a classical K omega model. The points here, the circles, these large circles, are the experimental results. And if you now take the extended equations and you solve it with the K omega equation, you get some improvement. Of course, it's not perfect. Part of this might be due to the modeling of the K omega equation, which is the conventional one, and it should possibly be modified to when you use the extended Navier-Stokes equations. Nevertheless, you get an improvement, and more work is needed in this field in order to see how one can get better predictions when high temperature gradients exist in heated pipe flow. Let me now come to a second problem. In the first problem, basically there was a defect in the Navier-Stokes equations, and I explained this, and I showed that you can overcome this defect. We can extend these equations. I'd say, why did nobody else find this? The reason is, in my opinion, quite simple. We have a tendency to believe these equations and then find outside of the equation reasons for the discrepancies, which I have shown you on microchannels, channel flows, on supersonic flows, and strongly heated flows. The other problem I would like to tackle is indicated here. It's the laminar pipe flow. Here you see the pipe. Inside of the pipe, you see parabolic velocity profiles. And we know from many theoretical investigations that these parabolic velocity profiles are inherently stable. So you can knock them, but the viscosity will damp this disturbance out. An excellent summary of the existing work is provided by Schlichting. And if you look at this work and also some additional publications in the literature, you get these results. On this side, you get the critical Reynolds number, and at the bottom, you have the diameter of the pipe. And you can see there is not a single critical Reynolds number coming out, but a whole set of Reynolds numbers. And you also find the bigger the pipe, the higher the critical Reynolds number you can get. So if you want high Reynolds number, stable laminar pipes to be investigated, take big pipes. Of course, then you need big blowers and you need all kind of big apparatus. But nevertheless, this is what the literature presents. Now, why is this so? So there is definitely a discrepancy between the theoretical results here and the experimental findings. So we have a problem in the sense I have said I will consider them in this presentation. Here now, once again, what do we compare? We compare a pipe flow, which is infinitely long in the theoretical treatments. It has a set parabolic profile. And now we disturb this velocity profiles and the disturbances are damped away. And we compare this with a blower, which provides the flow through this test rig. It has some flow control, a diffuser, plenum, chamber, and nozzle. And then it has a long pipe, and the length is different from one experiment to the other. There's also equipment, measuring equipment, associated with this test rig, and we blow this air into a laboratory of different size. The laboratory walls are indicated here, and it's quite clear the differences which you have just seen here in Reynolds number come from these differences in the test equipment employed by the different investigators. Let us have a look at the cause of these differences. I start out with a blower. This is a blower which you have on one side of the test rig, here, and it provides the flow through the pipe. Now, what property must this blower have to get the laminar to turbulent transition of pipe flow investigated? Here you see the friction factor of this blower is going down. At the point where the transition occurs, the friction in the pipe must go up. And this, of course, there's no means to do this. So basically, you can expect flow jumps. It finds now out it should increase the pressure, but this blower cannot do this for this flow rate. So it will go back, and at the end, you get all kinds of disturbed flow, but not the kind of disturbance you would like to have to go from this low point here up to the upper point. This is now the result. You have a laminar flow, and if you now increase the velocity by increasing the power output of the blower, you find that the flow finds, well, I should go turbulent. But then the conditions of the blower are not there to do this, so it jumps back. And this happens, and basically you get these kind of flow phenomena that are called in the literature slugs. Puffs are also there. They have a very similar behavior. Now, if you want now to study what really happens here, you must build up a test rig of this kind. In this case, we are using here a mass flow controller. So this mass flow controller can allow us to blow out air, and you use the increase on the high pressure side, the increase of the pressure, to increase the flow rate here. In this case, it is a slow process, as slow as our blower. You can, however, have another means to control this mass that is faster, so it can react very fast to the requested change in pressure or in flow rate. That's the plenum chamber. I will say something about that plenum chamber. And here you have an iris diaphragm where you can disturb the flow. We know if you don't disturb the flow, it will not turn turbulent. So since we want to study transition to turbulence, we must have some kind of a disturbance here. We have chosen this iris diaphragm to get the disturbance generated. It's automatically controlled, so you can close it, so put in a disturbance, remove the disturbance, and in this way get short disturbance, and we can see how these grow in the pipe. We used pipe between 0.5 and 8 meter in length, giving us longer times to observe these disturbance-caused flow disturbances. Everything was controlled by a computer, and we recorded everything and evaluated the data afterwards. And here's now the test rig. The test rig is, here is the test rig is quite normal apart from this disturbance element here. So what you now see is this mass flow controller. This I would like to explain here. The flow goes in the test rig here. In these sketches, I have drawn it in this direction. You have here a 3 millimeter closed ball, and this ball can be opened so that a pressure increase or a pressure can be used here to get force flow in this direction. If you increase this pressure, more flows goes. And this mass flow rate is now depending on this pressure change. If you change pressure, it is a slow change of mass flow rate. However, this mass flow control can also be operated by changing the position of this ball. This ball is the same as here. So if you now leave this pressure constant, you can open and close this fast and therefore control the mass flow rate by this area change. And this allows us now to see what the blower or the airflow generator is causing in terms of transition. Now, this is what happens. You open and close this device, and then this disturbance grows, and I show it here for the 8 meter long pipe. Over the distance, here you open and closed the, let's say this iris diaphragm, and then afterwards the flow or let's say the flow grows in length, and at this point it leaves the pipe. So we only measure at the end of the pipe, and then it leaves the pipe. Before and after, the flow stays laminar in spite of these disturbances. So the laminar flow is there for the parabolic velocity profile, but there is a region where we can force the flow to become turbulent. Why that is so, I explain in a moment. Now, here is this length growth indicated. 8 meter, here you have triggered the flow. This is now the turbulent region. Here you close, not you close, here the flow leaves the pipe, and of course the flow afterwards is then laminar again. Very structured turbulent flows. It's very repeatable. This flow has about 20 trials, so 20 slugs, very precisely generated, very precisely observed, and they lie over each other. What you can also see is here, the front part of the pipe grows faster. The back part grows smaller, and this velocity difference is the reason for this growth of slug growth. So you can study turbulent flows in a well-controlled manner. Now, let us have a look at some other situation. In this case, we have used the mass flow control system like this blower. And we obtained the kind of flows we knew from our pipe flow, but well controlled. In the other case now, which I would like to study, I use now here the fast change possibility of our air supply device. And I look now, in this particular case, at a plenum chamber. These plenum chambers have a tendency to oscillate. I've taken the results of Maurer. I've written the results of Maurer, and I've looked at the oscillations he measured. These plenum chambers with pipes going out behave like Helmholtz resonators. So they oscillate, as indicated here. And this oscillation depends on the length of the pipe, on the pipe diameter, on the shape of the plenum chamber. Everything influences it. If that frequency agrees with the mean If you run the flow now with this fast change in flow rate device, you get a completely different critical Reynolds number distribution than if you run it in terms of high pressure with a high pressure device. So this explains why you can have different results as you have them in the literature. Nevertheless, all literature uses blowers, or they use mass flow control systems, but the mass control systems are used very similar to the blower. So that's why all the data in the literature look alike. The highest critical Reynolds number we found is that of Fedinger. He used about 50 millimeter pipe, and the critical Reynolds number was measured to be about 1,000. In our case, when we run now the mass flow controller by that small should get 100,000 if you run it with a fast control. But apparently at this Reynolds number, we already trigger some other device. So we could get this 100,000, but for some reasons, sometime later, it jumped down to a smaller value. It never it would not go back. Nevertheless, it is interesting that you can manipulate the laminar to turbulent transition, the critical Reynolds number, by changing the blower, if you want, in this particular way. What do you now get? Here you see we have a critical Reynolds number of 7,000. That's what you get if you run this test rig with the pressure device to control the flow rate. If you now increase the flow rate, it jumps up and you get puffs and slugs. If you now use this ball bearing to encross the ball to control the flow rate, you get now oscillations. And these oscillations are fantastic, but the flow never turns turbulent. It oscillates and it stays turbulent until it catches sometimes another mechanism that turns the device turbulent. Look also at the Reynolds numbers. Before we had Reynolds numbers of 5,000 to 8,000. Now we have Reynolds numbers here of 53,000 to 41,000. And you see, sometimes you can drive that flow in a laminar oscillating manner into up to Reynolds number of 60,000. And then when you try to adjust it again, coming from the upper side, it only goes to 53,000. Nevertheless, with these fast changes, you can keep flows laminar, but oscillating, of course, up to 50,000. Let me now come to an end. I started out by explaining that the Navier-Stokes equations, the Navier-Stokes equations, the continuity equation, and the energy equation have a defect. This defect comes from the mass transport equation. There you can see 0, 0 on the right-hand side. On this case, you have on the right-hand side a molecular transport of momentum, a molecular transport of energy, but we have no molecular transport of mass. This is also the reasons that you can see in some of the textbooks on heat and mass transfer, that the heat transfer section has, let's say, 400 pages, and the mass transfer section has 50 pages. Why? There is no mass transfer. And this is, I think, a defect that we need to eliminate. I've done this for the extended Navier-Stokes equations, and I could see that discrepancies for microchannel flows can be eliminated. Discrepancies for shock waves can be discriminated. And discrepancies, or if you want, problems for heat transfer in turbulent pipe flows could be at least improved. Here are now, for these conventional equations, conventional form of the basic equation of fluid mechanics, the diffusion terms, no mass diffusion. The Fourier term represents the heat transport, and this is the Newton, the molecular transport term for momentum for Newtonian fluids. This is wrong, at least for this is wrong for ideal gas flows. If you take ideal gas flows, you can derive these terms. And this MI is now introduced on the continuity equation, where on the right-hand side it was 0. This term also influences the heat transport. It influences the momentum transport. And if you put these diffusion terms into the basic fluid mechanics equations and you solve them, some of these equations that cause problems these days, the problems are eliminated. If you now look at microchannel flows, which I started out with, you can now see that the world is more perfect now. Down here, above Knudsen number 1, we have molecular dimensions in our flow cases. Down here, we are quite some distance away from molecular dimensions. And we are still using nowadays the, let's say, methods of modeling in order to get agreement, although molecular dimensions are not in place yet. This is not the case if you use here the extended Navier-Stokes equations, and as I have shown, you can get a good agreement. So my suggestion is to use extended Navier-Stokes equations, at least in those cases where you have high pressure and high temperature gradients. I hope I could show you that the Navier-Stokes equations require extensions and to use them when necessary and get good results. Thank you very much. Good morning, everybody.
Thank you, Professor Drust. It's quite an interesting discussions of extended Navier-Stokes equation. Basically, to summarize, you have considered three different things. One is like the flow through microchannel, where conventional Navier-Stokes equation doesn't work. Then when there is a transition from laminar to turbulent flow, then also the Navier-Stokes doesn't work. And of course, with the shock wave. So before, and of course, there is one interesting thing is that in application, in books of heat transfer, as you were mentioning, that if there are 400 pages, there are only 20 pages for mass transfer. Even in our lectures also, we do the same thing. We have 40 lectures in heat transfer and finally 2 lectures in mass transfer. So that tradition still continues now also. I think before I ask you something, I'll take it to the audience because there will be more enthusiastic people in the audience to ask you a few questions. Please go ahead if somebody have any questions to Professor Drust.
Hi, I'm Shraman here. I have a question. The extended Navier-Stokes equation for the mass diffusion, you have a term for temperature. So how does that play a role? Density, I can imagine something, but for the temperature, how does that play a role in terms of mass diffusion?
You know that the molecular motion, the velocity of the molecules depend on the temperature. So what you have, if you have a temperature gradient, you have on one side of that checked surface I have shown, you have a higher velocity, because the temperature is in the velocity term, and you have a lower velocity just on the top of that checked surface, and that gives you differences in the velocities in the molecules, and if you enter that into the equations, you get this temperature term. This temperature term is the reason why you have Sorry heat transport in fluids.
Okay, so is that equation derived from kinematic theory of molecules, kind of?
I started out with the Boltzmann equations, and I integrated and did all the kind of situations or all the kind of derivations, and at the end I did not understand what physically happens. Then I went back and I used mean velocity, molecular velocity considerations, and I got the same results. So what I have shown you is not the treatment of each individual molecule, but the treatment of the mean motion of the molecules, and it comes out perfectly. You get all the terms right. If you look at the equations for Sorey, you also see you get the Sorey diffusion coefficient, which is amazing.
Yeah, thanks. It has been a very nice to go through your presentation. Thank you so much, Professor.
Good afternoon, sir. My name is Saroj Kumar Panda. I am a researcher in Department of Atomic Energy, Government of India. So we used to talk, my supervisor used to talk about you and your work many times during my PhD in IIT Delhi. So so it's a dream come true seeing you, listening you in a live session. So my query is, many times we generate experimental results, and also we generate predictor results from simulations. So sometimes we call it, it's a good result. Agreement is very good, and sometimes we call it as agreement is poor. So my query is, what basis we are judging it actually? Is there any parameter to judging it actually? Because that question is there in my mind since years. And what percentage error is acceptable, sir?
You see, the situation, if you do numerical calculations, presumably that's what you have done. Yeah. Now you get some additional things in. That is the accuracy of your numerical computation. So you get numerical errors coming in addition. So you first have to make sure that you get good numerical results with sufficient agreement, let's see, with the sufficient or accepted errors. And now what is accepted, that's very much depending on yourself. If you have a lot of money at a time, you can get very precise computations. If that is not the case, sometimes in industrial computations that's the case, then you have to accept somewhat less good results. Now, there are two things. One thing is definitely the case, you can look at these n dots, which I have given here in the equations, and then what you can put in is your numerical results because you know your gradients. And if n dot comes out to be small, then you're sure you're not having these effects I was talking about. So that's possibly one way to see how good your computational results are in comparison to the real solution using the extended Navier-Stokes equations.
Okay, sir. Thank you, sir.
But you see that sometimes when I came out with these extended Navier-Stokes equations, I got very much criticized. And I took the attitude, well, criticize, I know that these derivations are right, and if you don't accept them, then that's your business and not mine. Then I find out, however, that we have a lot of very good students doing their PhD with us in fluid mechanics, and we should point out this shortcoming of the existing Navier-Stokes equations and ask them to look into it. And I'm sure then people will find out that possibly, or clever people will then contribute to this and get this topic further. Okay. Important to me is also the second case, the laminar to turbulent transition. Basically, what I've shown there, it cannot be that we have the Navier-Stokes equations and let's say a set parabolic velocity profile, and we predict inherent stability.
Okay.
And then in the experimental case, we get turbulence. Now, why is that so? The turbulence comes from the equipment and not from the laminar profile in the pipe. I think this is also a topic one should put some clever students on it and see what comes out.
Okay, sir. Thank you so much, sir. Thank you.
Is there any more questions from audience? Professor Biswas.
Good morning, Professor Durst. It was really, a delight to meet you again, although not physically through virtual media. I think Professor Wang is also present in the audience, Anbang Wang. This is really not a question, maybe in the form of discussion. This formation of slugs and plugs in transition, this is a very well-known classical problem started with Professor Rota, and probably it was concluded by you through your students and through very good publications. My point is that this slug formation and plug formation and this part of transition, this has really the paradigm where inherent disturbances come from ambience. Like this happened in the case of, if we go by the classical experiment of Professor Reynolds, Osborne Reynolds, that in the Cavendish lab, when he used to do experiments in the night, he used to get transition around 3,000, 4,000 Reynolds number, and in the day, and in the night, the transition used to take place. Flow used to be stable even for number of 8,000 or 10,000. He got once 10,000. So basically, the disturbances that come from instruments, that come from surface, that comes from disturbances that come from surroundings, those disturbances can create a difference, but finally, that transition again. We get back to the laminar regime if the kinetic energy is not sufficient to support the disturbances, and this was very nicely done through this, almost like a super pipe you used, and I know all the equipment used there. Even this disturbance was created by this aperture controlling this aperture of the disturbances. Fraction of a second, it created disturbances and it went out. But with all this, I'm just, what I'm trying to say that probably this has no apparent connection with the modification of Navier-Stokes equations that is proposed.
I agree with you. The second problem has nothing to do with the first part. So I did not use the extended Navier-Stokes equations because I had felt what we are studying there has nothing to do with strong pressure gradients and strong temperature gradients, but it has to do with the equipment we apply. And we should be clear, I always didn't say this, turbulence is a question of the equipment we use and not so much of the jet we are studying or of the pipe flow we are studying. It is the equipment we have to drive the flow cannot do what the transition requires. That's basically the message of the second part. Right. So turbulence, we are trying to look at the local phenomena in a pipe, and it is driven by the blower in the back. This is, in my opinion, something we should look closer at in future investigations.
Absolutely correct. And probably I can add something that the pipe which you used is really a super pipe. Its manufacturing accuracy is absolutely amazing. And that is why the elimination of creation, puffs and slugs were possible, and it could be shown that it comes from the artificial disturbance that was created at the entry.
Yes, yes. I should mention Professor Pishwas was also involved in some of these investigations. Quite a number of people I did not mention here. I had one slide where I had all given them, but to get this lecture here recorded was quite something. And at the end, we had to take it out because even in the third trial to get a good presentation going, it didn't work.
No, that is not the point. But point is really, having such accurate equipment like the pipe you used and your historical experiment of this backward-facing step. They are also the accuracy of the positional accuracy, dimensional accuracy is really amazing, and it is to be appreciated for the years to come. Creating such absolutely accurate test facility, it is probably not possible anywhere and everywhere. It was only possible in, under your tutelage in LSTM. I mean, I do not know whether, such equipment can be given to, or, this are being used by others, or it should be continued, such accurate equipment.
Yeah. Now it is standing around doing nothing, which is a pity. Yeah.
Thank you, Professor Durst. Thank you.
Thank you also. Thanks for the last word.
And let me also tell to the audience that Professor Durst, all of us can wish him for belated happy birthday. No.
Thank you.
Belated happy birthday.
Happy birthday, Professor Durst.
Thank you.
Professor Dalal, you have some question.
I don't have any question. Just thank you, Professor Durst, for the wonderful lecture. I would request Professor Biswas to switch on the video, so it will be nice.
Okay.
Sir.
I thought that I know the bandwidth problem. Okay.
Yes, yes. Now it is looking fine. And also, I request Professor Wang to switch on the video. Then it will be very good.
You are muted.
Professor Talukdar, you please go ahead. Professor Talukdar.
Yeah. No, I have a simple question because I work in heat transfer. So by using extended Navier-Stokes equation, will there be a change in Nusselt number at the fully developed regime?
As you again, you are using the extended equation, and in which case you are asking you get the same results?
For example, in a microcell, if I apply an extended Navier-Stokes equation where you have a mass diffusion, so will it increase the Nusselt number compared to a conventional Navier-Stokes equation?
It depends. It will, because what you have is now you have also let's say if you do not have any strong temperature gradients, then it will only through the pressure term increase the transport. If you have now the temperature and you have, let's say, if you have a high pressure gradient but a small temperature difference, you will have a higher number because of but it's driven by the pressure gradient. If you now have a very strong temperature gradient, you get an additional term coming from the temperature gradient.
Okay.
If you do this kind of work, take these equations in, and it is very amazing what you can see that come out. And you could see by comparison with Maya's data that you get agreement with the experimental results, and this shows that the numerical or analytical expressions allow you to get an insight what you observe experimentally.
Okay. Thank you.
Let me say one thing. I just realized now, in the turbulent case of the laminar turbulent transition, the planar general results were by Messmer, and I said Maurer. This was a mistake.
Okay. I think there is no more question from the audience. Amresh, we can close this session by thanking Professor Durst.
Okay, thank you, Professor Talukdar, and thank you, Professor Durst, and all other audience here. And Professor Biswas, if you want to continue, means the session, it is open for us, means just to discuss in any topic. So we can go ahead with that. And Professor Wang, if you also if you can participate, it will be very nice.
I mean, I'm not really prepared for this impromptu discussion, but having Professor Durst among us is really amazing and absolute delight, because we can get ourselves enriched with his knowledge, with his suggestions, with his advice, and especially people who are planning for newer experiments, or who are thinking about converting some paradigm into correct experimental paradigm, from where the real conclusions of long-lasting value can be drawn. They can probably get in touch with Professor Durst and discuss their problems, and I'm sure they will benefit a lot. Professor Wang is also here, so I will leave the podium for Professor Wang. Professor Wang.
Thank you very much for the response.
Yeah, Professor Durst.
Hello.
It's nice to see you, although not physically.
Yeah, thank you very much for coming to this meeting, and at least it gives me an opportunity to see you through television once again.
Yeah, it's really nice talk. I heard. Yeah. But it's only a pity. Here is a little bit in Taiwan. My system, I have some echo to disturb my hearing about this. But in any case, I saw from the slides, and to enhance the hearing program, I cannot catch quite of that. And have you any suggestion for the future, especially for the young generation, when they are making, for instance, they are making microfluidic and so? And have you any suggestion, direction for them?
One of the things is, sometimes we get annoyed if we get two different results for one solution of a let's say of a flow phenomena. And we should not. We should think about the difference and see where does it come from. This was basically the message I was trying to get over. Let's say if we're doing fluid mechanics, the following, let's set up properties of a particular flow, and we solve results. Definitely this is also necessary, because we have now these fantastic methods, and we can use them to solve tasks in fluid mechanics. And if we do this as an only let's say, way to deal with fluid mechanics, then we will have no progress. We need this progress that we say it's impossible that people who did not have the numerical methods available, also some of the analytical means or the means, that they have obtained all results of basic results of fluid mechanics in the 18th century. That I don't believe. We should look at these equations, the background of these equations, and see that we can use them, use the differences to find out where we can put in place and get improved equations, improved methods for the measurements, for the investigations.
Okay. Yes, thank you. I think this will be a very delightful for the young generation to think about and progress further in the future. Yeah. And I heard you have birthday in this December, and happy birthday for that. And
thank you.
And it's really nice to see you are still so healthy as before, without any change.
Well, you see, I have, I have learned that if you want to become old, then you must have a lot of birthdays. So that's, if you want to stay healthy, you must do some activities, and possibly the best activities you can have is free mechanics.
Okay, yeah. And sorry, I have a meeting in 3:30, and I need to leave. And I thank all of the organizer and all participants. And I hope you could have still a very interesting talk with Professor Durst. Professor Durst, I need to leave and say goodbye to you.
Thank you for coming to this presentation. Yeah.
Yeah. Thank you. Goodbye.
Goodbye.
Thank you, Professor Wang.
Yeah.
Any discussion or any from audience? I think there are no questions. Professor Talukdar, so please go ahead.
Yeah, Professor Bruce, hopefully we'll see you very soon. When pandemic is over, definitely we'll see in Germany for sure if you are not coming here.
Yeah, I would have really come to this meeting because, as I said at the initial part of my lecture, this would have been an excellent opportunity to meet you all. And I also hope it happens once more somewhere in the world.
Sure, yeah, it was exciting for me also. And and in the morning at home, I told I am going to, sharing a session for Professor Drust, which is a good news for my family too, because being here.
How's your family? Is it fine?
All good. My son is working now. He is a mechanical engineer working for a startup company in Bangalore. And my daughter is in class 11 now.
Oh, wow, they're good, huh?
Yeah, we are going out.
Say hello to your wife and also to the children. My wife is also sitting there, so she also says hello to all of you. And also Professor Bishwas, hello from myself and from my wife.
Yes, my heartfelt greetings to you, Frau Durst, and the entire family. It is, as I said, absolute delight to see you even from distance, and I look forward to meet you personally, whether in India or in Germany or elsewhere. I'm looking forward for the next opportunity to meet you.
Thank you very much. Thank you. And thanks for coming to this presentation.
Okay, then otherwise we'll close this session here.
Professor Dalal.
Yeah.
Yes, thank you. So I would like to thank the speaker, Professor Drust, for accepting our invitation and means delivering this wonderful lecture. And also I would like to thank Professor Bishwas for attending this lecture, and Professor Wang. And I thank Professor Talukdar for chairing this session. And I thank all the participants who attended this lecture. So thank you very much. So we are now again we will meet at 1:30 for the keynote lectures. Thank you very much. Bye bye.
Thank you very much, and have a nice conference. Yeah. Thank you. Bye.
Have a nice day. Bye.
Thank you.
introduce the problem and its background and where we currently stand. Tea leaves, paper curds, they actually fall under their own weight. However, when the density ratio between the object and the surrounding fluid is near about 1, then the trajectories through which the object falls becomes complicated, and it's a subject of fluid mechanical studies. It involves complex fluid structure interaction, stability of the trajectories. In stable trajectories, the established regions are mainly three: flutter, which tumble, and the chaotic to universally obtain different states are unified. We find later on in the right here, tumble, sorry, the flutter. The tumble proceeds from point 4 to 3, which gives us an impression of complete rotation, and the flutter to tumble transition occurs generally near about point 4, which is generally known as chaotic region. It shows the signs of both flutter and tumble. In the current study, we have added multiple plates to see the effect of the proximity of each plate on the stability of the trajectories and the role of complex velocity dynamics in deciding their trajectories. As the current study involves multiple plates, it is essential that we
Tu es trop grand pour comprendre des choses aussi belles. Tu es trop grand pour comprendre des choses aussi petites. Tu es trop grand. On prend.
I'm in the correct room, right?
Yes, sir. Hello.
Yeah, I am in the correct room, right? This is Shabda
Yes, sir. Yes,
Srivastava.
sir.
Okay.
Yes, sir. You are in correct room.
Okay. Fine.
Hello, welcome, Professor Basu.
Hello. Hello.
Hello.
Hi. Hello.
Professor Basu.
Yeah, am I audible?
Yes, yes. Hello, Professor Basu.
Yeah. Am I audible?
Yes, yes. You are audible. Yes.
Okay, great.
Video is coming, Professor Basu.
Sorry, video,
Okay.
yeah.
Yeah, it is coming. Yes. So let us for few and also few more participants will get. And always we see that Pranav Mandal will be joining soon, and also few more participants will get. At the same time, always we see that participants are listening from YouTube.
afternoon all. I welcome you all to this session. Pranab Kumar. All. I welcome you all to this session, and this session will be chaired by Professor Pranab Kumar Mandal from IIT.
Good afternoon, all the participants. Third by Professor Saptor, DRDO Chair Professor in the Department. Professor Basu primarily works on multi-phase system, especially droplets at multiple length and time scales. He is a fellow in National Academy and Institute of Physics. Professor Basu is the fellowship in engineering. Professor Basu has authored many papers.
Okay, so let me share my presentation. Is the presentation visible?
Yes, please go ahead with screen. Yeah, thank you.
Okay. So I guess thanks to Amoresh for the invitation to FMFP for this talk. So my title of the talk is basically droplets and aerosols in the context of COVID-19. So this is a new area. The COVID-19 part is new. And we have tried to look at some of the phenomena from the droplet perspective in the context of COVID-19. And in this talk, we are going to cover maybe 3 of these areas. Okay, so some of the areas which are still pending, we will cover maybe in some other time. This is the team. Basically, it's a team of 3 people. Me, Professor Shetoprabha Chaudhary of University of Toronto, and Professor Abhishek Shah, who was my ex-PhD student, now in University of California, San Diego. So this was the team who basically did all this work, sitting at 3 different locations across the globe. So let us talk about that, how basically COVID actually spreads. So as you can see that obviously you have if you can watch my cursor. So if there is an infected person in the middle of all these non-infected person, with time, you see that the number of infected persons grow. And how fast the question that normally people try to answer from an epidemiology point of view is how fast this disease actually spread. Now, the pandemic models are in general very complex, and they have very large uncertainty because of the different socioeconomic structures of the society and different other uncertain parameters. What we try to do is that, can we look at the small scale interactions, that is basically look at the droplet level scale and derive an appropriate pandemic model from the first principle. And let us see that how this actually works. So how does the person, infected person affect a healthy individual? So an infected person either through cough, sneeze, or breathing, talking, exhales a cloud of droplets, which basically migrates. It basically grows in size, as you can see, and migrates. And as the healthy individual breathes in the cloud, he can get infected. So this is how the infection actually works. So basically the respiratory events, as you can see, is obviously influenced by the ambient conditions, and we will see how. It also depends on whether you are wearing a face cover or not. The droplet clouds are basically transported and dissipated, and it depends on what is the ejection velocity, what is the ambient flow field, if there is a wind or not, all these factors. Then these droplets obviously do not remain of similar size, they actually shrink. And as they shrink, they also precipitate and leads to something called aerosolization. This happens due to the ambient weather conditions, temperature and relative humidity. So now, after all these cases, when the healthy subjects actually inhales these droplets, depending on what is the viral load and the biology and the immunity of that particular person, he can get infected. So basically, what is the respiratory or an expiratory? Depending on what is the viral load and the biology and the immunity of that particular person, he can get infected. So basically, what is the respiratory or an expiratory droplets? They are basically multi-component in nature, the major component being water. Then of course you have salt, you have mucus, and you have the virions, basically the virus. And what are the phenomena or the key physics that are involved in this particular process? Obviously it is evaporation, as you know. There is also dispersion because droplets are exhaled in the form of a cloud. There is also settling because of the larger droplets can actually undergo gravimetric settling. There is also evaporative cooling. That means when it's the same phenomena like the way that your skin actually cools. And then of course, because it has salt, it can undergo crystallization depending on what is the relative humidity conditions. So the lifetime of the droplet is a very complicated functions of all of these. So that exhaled droplets therefore should suffer three fates. First one is that it can infect, it can remain as droplets, and that means somebody sneezes in close proximity to you, you can actually inhale the droplets. It can transform to a nuclei, which is basically the desiccated droplets, and that also is what you call aerosolization. Then it can settle on surfaces, and this we call fomites. This is why we basically sanitize the Amazon boxes and the items that are received from Big Basket and so on and so forth. All three modes can actually cause infections. Obviously, the droplet mode remains the most dominant one. So the goal is to basically analyze the droplet physics and the methodology that we are going to follow. And these are the three works that we are going to present. First one is experiments with an isolated respiratory drop. Then looking at the modeling process of the transport and subsequent epidemiology. And if we have face masks on, what happens on the droplet transport? So let's look at these three phenomena from a very unique perspective. So basically what we want to know by experimenting with isolated droplets is to understand first the evaporation pattern, the precipitation dynamics, and the fate of the virus in the precipitates. And this also serves as an input or validation for the computational models. So what we did was we considered and 1 wet % aqueous NaCl solution as a surrogate respiratory liquid. We also did, by the way, experiments with real saliva. I'm not going to mention the subject that was used, but the subject was a non-COVID person. And the transport and fluid mechanical aspect of the virus can be simulated using nanoparticles. These are called virus-like particles, hence the word VLP. So these are basically 100 nanometer fluorescent particles which are used as virus substitute. Because of the non-motility of the virus, this can serve as a good analogy to see how the viral loading actually, how the virus is actually distributed in the final desiccated samples. So the interesting part of the setup is that how do you generate a contact-free droplet? You use a levitator. So levitator here, it is an ultrasonic levitator, or basically what we call an acoustic levitator. The droplet size is about 500 microns. We can go higher and lower. We have done with both. And these are some of the literature that are available on the levitator work, so not going to go into the details. And there was a bunch of diagnostics that were performed like laser imaging and high-speed shadowgraphy to see what is going on. So this is exactly what the levitator looks like, and this is what the droplet looks like. So what happens? The global morphology, the droplet undergoes evaporation. Basically, it shrinks in size. After reaching a time of about Ti, basically what happens is that precipitation is triggered. That means the salt starts to come out of the solution. And the precipitation is begins at this particular time scale. Then it, depending on what is the nanoparticle concentration, or basically the viral loading, it can form different types of end products. But morphologically, they look more or less similar to each other. Now look at the d by d naught plot. That means basically the diameter regression of the particles. What we see is that this particular graph shows pure water. So pure water just goes down. Okay, and if you just square it, it will represent a linear line consistent with the d square law. But whenever you start adding, and this is actually human saliva, actual human saliva, and this is salt water and nanoparticles. So these are mixed here. As you can see, this is the desiccation curve. So water obviously evaporates the fastest. That is because it doesn't have any salt loading. So the vapor pressure is no longer depressed. so the water finishes off pretty fast. The salt water with nanoparticles, basically with and without nanoparticles, they show very similar trajectory because the nanoparticle loading is rather small. And they kind of mimic a very similar characteristics as a human saliva as well. Human saliva is, of course, a little bit more complicated. It has got a lot of other stuff as well. However, one key important thing that you should note over here, that the knee of this curves, that means where the precipitation is triggered, happens at around 0.2 to 0.3 of the initial droplet diameter. This is valid for all droplets across all size ranges. So it doesn't matter whether you start with a 20 micron droplet or a 300 micron droplet. The precipitation starts to happen, or the droplet diameter basically freezes around 20% of the time scale. This is also validated by experiments with different droplet sizes. Now, so if we look at the precipitation, as I told you earlier, it is basically independent of whatever is a nanoparticle loading. So it doesn't make much of a difference at what nanoparticle loading you are using. So within the error, experimental error, they are more or less the same. It's not valid if you actually increase the nanoparticle concentration to quite a bit. But viral loading is not that much anyways. So what happens is that this is how the droplet actually precipitates. So as you can see, there is a clear morphological change that actually happens. Interesting to note is that the solidification or the crystallization doesn't occur from the surface necessarily. It is from across everywhere in the crystal, and this is the final morphology of the crystal as it forms. This is because the salt homogenization rate and the evaporation time are very comparable. So basically you have a Peckley number which is very comparable, and as a result of that you don't have the salt crystal preferentially coming out from the surface. So what we did after that was that we collected the precipitate, and then we did what we call a fluorescence microscopy on the sample. So as you can see that these are basically the viral loading that are within the crystal. So it almost looks like a fossil in which this is a crystal, and all the virions are basically embedded within the crystal. So they are distributed almost throughout the crystal. There is no preference basically between inner and outer, but for the most part they are inside the crystal. And if you do an SEM, you can see the appearance of some of these nanoparticles at certain points on the crystal surface. So this basically shows that what we get is basically a viral virion-laden crystal that actually forms in the desiccated nuclei. And as we breathe this particular nuclei in, depending on our immunity and our physiological conditions, this is actually what leads to the viral outbreak. So this is the kind of the summary, in between summary. So the nanoparticles obviously do not affect the evaporation, precipitation, or crystallization, but apparently it actually resides within the crystal mostly, but also we see evidence of these virions outside the crystal as well. So this is an important finding because the virologists are very concerned about the distribution of the virions, because they obviously cannot see in a droplet cloud how the virus is distributed. So this gives a very logical outcome, and they can study the viability of these viruses inside a salt matrix essentially. So now that we know all these things, now we are in a position to do a physics-based model of this entire phenomena, which basically includes the effect of the coughing or the breathing exercises that we do, because there is an air puff that also comes out of our mouth, and not just the droplets. And it should be simple enough that it can be scaled up in a large-scale pandemic model. So the same solution was used. No need to model the virus because it is insignificant effect on the transport and lifetime at least. So what happens, as I said already earlier, so this is the famous, the regime diagram where you can see that some droplets, bigger droplets settle, smaller droplets actually aerosolize, and in between the droplets there is a very critical range, okay, where they remain as droplets for a certain amount of time. And this is one such picture which shows basically the droplet spread from the experiments of Vidya et al. So what is most important over here is that from a pandemic vantage point of view, and this is where our little background in combustion comes into the picture, this is very similar to a chemical kinetics based reaction mechanism model. In a reaction mechanism, commonly you have thousands of elemental reactions. So the chemical reaction, as we know, is all about this rate constants, that how fast the reaction goes. So in COVID-19, can one such rate constant be K, which is basically a very strong function of the droplet lifetime? So if K is a function of the droplet lifetime, then what is this particular function? That is the question that we need to ask. So we modeled it like this. For example, if P is a COVID positive person and he exhales, and this is the droplet cloud, and H is basically a healthy person. Okay, so this healthy person therefore breathes in air which is given by that hemispherical volume. Now, what happens is that the number of collisions between this healthy person and the droplet cloud that is ejected by this COVID positive person will give rise to the number of infections per unit volume, where NP and NH is basically the number of P and H respectively in that unit volume. And this is what the equation is. And depending on the number of collisions that actually happens, we have conversion of a healthy person to an infected one. So this is given by this equation. And therefore, this can be also cast in the form of a reaction rate, which is given as omega, where reaction rate which is dependent on NP by N total, where N total is the total population per that unit volume. So if you take all these equations and now you cast it into a reaction mechanism problem, you get these set of these three equations. So P and H gets converted into a susceptible person, which is a person in contact with the virus but not yet infectious. This person therefore gets converted to a COVID positive person in due course, and the COVID positive person either recovers or basically dies, with given a 3% mortality rate, which is taken from the literature. So as you can see that K1 must be greater than K3 for a rapid outbreak to happen, because you need more persons to get converted into COVID positive than the persons actually recovering. That's why in the newspapers you read that the rate of infection and the rate of recovery is so important. Okay, and then there are some incubation times in the meantime. So as you know, K3 is about 1/14 day. So this comes from the general guidelines of WHO. And K1 is basically the infection rate constant, which is the most important one. So you convert this to a system of ODEs, not going into the mathematical details. You solve P as an eigenvalue problem, and therefore you get the lambda 1 and 2. And as you can see that lambda 1 and 2 basically is dependent on this guy K1, where K1, if you cast it like this, basically depends on the droplet cloud diameter and the diameter of the breathable air. Both of these two things are determined by the aerodynamics and the heat and mass transfer of the droplets. So this is where we are getting at. Okay, so how to determine K1? So in order to do this, first you solve the aerodynamics of the droplet. So this is rather easy because the human cough is basically a puff, a jet initially, then it transitions into a cough. So you can cast this equation. So one is a jet equation and one is a corresponding puff equation with matching boundaries. So this will give you the velocity and the radial spread of the air surrounding the droplets. And the average duration of the cough is somewhere close to about a second. Actually, it's lower than a second, of the order of a second. But you look at the time scales, it scales as t to the power of half and then t to the power of 1/4 during the jet to puff transitions. Now what you do is that you basically solve for each droplet, assume that the droplet lifetime is tau, so the average velocity of the droplet cloud is basically xp by tau. So therefore what you do is that you first solve the dispersion equation, basically the drag equation, and then you try to find out what will be the evaporation or the settling time tau for these particular droplets. So therefore this tau is basically a key parameter, and it is not trivial, as we know, because of the multi-component nature of the saliva drop. And we have already shown this picture to show that this is how the drop transforms into a crystal. So what we do in order to understand the droplet lifetime, this is the quest for the droplet lifetime. It can be solved in 1D or 2D. So the 1D is basically a quasi-steady model. It is given by the two limits, heat transfer limit and the mass transfer limit. Many of you are familiar with this particular formulation. Bm and Bt are the Spalding heat and mass transfer numbers. These are the corresponding mass fractions. These are actually corrected for the Raoult's law due to the presence of the salt concentration at the droplet air interface. So what you do after that is basically you solve for the instantaneous transport equation, okay? And this also takes into account the part of the heat basically goes towards raising the temperature of the droplet and towards the latent heat of vaporization. So this is the equation. Then actually after a certain amount of time, as you know that evaporative water loss leads to an increase in salt concentration, This is modeled therefore by a species balance equation. So what happens is that what is the amount of salt, if that is Y3, how fast does it actually come out of the solution to go into the crystal? This is triggered, this equation is only triggered when the concentration of Y3, basically the salt concentration, is greater than 0.393, which is basically the supersaturation limit. And the growth of the crystal is basically given by this kinetic formulation, which suspiciously looks like an Arrhenius form of an equation. And this is how we calculate what will be the crystal dimension. So packing all these things together, now if we do the modeling, you will find that we get a very close match with the experimental data. So this is model and this is experiment. And we also get the knee quite accurately. It also happens at 0.2, okay? And we also get the crystal size to the same order. So these crystal sizes, as you can see, are 60 micron or 120 micron. We get similar order size scales for the crystal size. Okay, now if you pack all these things together and you start calculating that what is the, for example, the droplet lifetime, you will find that the desiccation time, which is the total time for the droplet to become a nuclei, essentially is maximum for very high humidity and low temperature. So high humidity means if you have a Calcutta or a Guwahati type of a high relative humidity, the desiccation time will be rather long. This is not surprising because, yeah, things take a lot of time to evaporate. Okay, and low temperature is also for similar reasons. So cold and humid environment is a strict no-no for these kind of disease spreading. You can also do the same thing using a 2D model, not going to go into the details. It's a little bit more complicated because you solve now for the 2 dimensions inside the droplet. And so these are some of the equations, not going to go into the details. Here what you can do is that you can actually see what is the salt concentration inside the crystal, red being high and blue being low, and they almost match with the 1D code and with the experimental data to the same effect. So what happens is that now if we pack up everything, now if we determine the infection rate constant K1, which was what we were looking at, you will find that the infection rate, looking at these particular plots, you will find that the infection rate is therefore the highest for high relative humidity and low temperature. And the rate ratio, which is basically the cumulative number of positive cases on a given day to the cumulative number of cases 7 days prior, this is very, very high for high relative humidity. So as you can see, therefore, cold temperature and especially the monsoon seasons were not good for this pandemic, and which has been proven to be kind of correct, because that's where we got those peaks. And we are getting a second peak in the US and other places because of the cold environment. Okay, so this is essentially a rough summary where you can see that we have tried to understand, and of course we have a second model which is available where it takes into account the aerodynamics in the droplet in a little bit more details. This is the new paper that was published in just like a few days back. Now I'm going to end this talk with a very nice little story on the mask. So as we know that we all wear masks to reduce the distance traveled by their respiratory jets. Face mask also reduces the droplet count. So everybody says that it is very nice. But you know, in India, we also use different types of things like handkerchiefs, like many other types of bandana, for example. So this we use. How safe are those? So let us look at what happens to individual droplets when they actually impinge a mask. And this is very different from these type of studies, which looks at the total flow. We are looking at a very different mechanism right now. So this is an experimental setup. What we have is that we have a mask and then we have a drop generator, which basically impinges droplet in the range of 2 to 10 meters per second. This is the range in which a human being actually coughs. And the diameter of the droplet is of the order of about 500 to 600 microns. So as you can see, the larger droplets carry the most volume, and therefore this is very essential to see what happens. These are the masks, so medical grade mask and locally supplied masks. These are the masks that we commonly use. These are the pore sizes of the mask. So you know, a single layer mask has got about a 30 micron type of a pore, and double layer it reduces, and then triple layer it basically becomes even lower. So let's see what happens when a droplet impinges a single layer mask, and just you can enjoy the. So what happens is that you cough, the droplet lands on the mask, and what comes out on the other side is much smaller droplets. This is amazing. You do that for a double layer mask, you still get a lot of droplets coming out, a significantly large number of droplets, and you see that they are also very small in size. For a triple layer mask, once you do that, there are almost next to none, except that one droplet once in a while that actually comes out. So what happens is that, depending on the type of mask that you are using and depending on the impingement velocity, right, you have a lot of penetration versus very low penetration. So our cuff actually covers this entire range. So with a single layer mask, you have a lot of atomization that actually happens. Is it detrimental? But before that, if you can calculate the criteria for the droplet penetration just by taking a simple scaling argument, the initial kinetic energy of the droplet and the energy that is dissipated. The criterion, the penetration criteria is rather simple. Your kinetic energy has to be much, much greater than the dissipation mode. You can cast it in terms of Reynolds number essentially. So in other words, your Reynolds number versus this, which is basically the thickness and the porosity of the mask, has to be much, much greater than 1. And indeed, in the experiments, we see something very similar when the Reynolds number is high, which is the case for a single layer mask because the porosity is rather high in these cases. So you get penetration. So green signifies penetration, red signifies little to no penetration. So it kind of agrees with this nice little scaling that we have. So what happens is that as the droplets, however, comes out of the mask, you see these ligaments and you see this, formation of these ligaments. So it can be explained by a typical dispersion relationship by taking the relative instability criteria. And if you plug them in without going into too much details, you can predict the breakup time and the droplet diameter that comes out of the ligaments quite accurately with the experimental data. Now, this is perhaps the most important slide that you will ever see. So what happens is that when you actually have an initial size of the order of 500 microns, a single layer mask or a double layer mask for both types, what it does is that it leads to a significantly large number of droplets in the aerosolization regime. That means less than 100 microns. So less than 100 microns, you have a significantly large number of droplets. So all it does is that the mask shifts the PDF of the droplet distribution towards a smaller droplet size. Now that is very detrimental because the smaller droplets, as we showed in the earlier part of the talk, they don't settle. They actually evaporate, they desiccate, they aerosolize, and they can actually travel very large distances because they are small, and they can actually have a high potential of infection. So basically what I mean to say over here, the moment you put a bandana or you put a handkerchief, which is a single layer, what you basically are doing, you are causing more harm than good. That is because you are basically causing secondary atomization of the larger droplets in your cuff to very fine mists, which can travel longer distances and can hurt. So that is the point that I wanted to emphasize over here, and this is a rather important finding, and this is valid across a very large number of experiments that we did. So this is not the typical, how much air or cuff velocity, the cuff profile that people normally do and see that where there is leakage from all sides across your mask. This is not that. This is direct secondary atomization, which can lead to aerosolization. So that is a rather important thing. Okay, so now the last part of the thing is that, okay, these are the stories that I have not told some other time. So we also did a lot of work with Narayana Netralaya on atomization and aerosolization in the case of eye surgeries, and this is one of the eye surgeries. This is not a surgery actually. This is if any one of you have got what we call a glaucoma issue, you basically go to a doctor, they do an invasive procedure in which it involves an air puff hitting your tear film. And as it does that, you get a lot of secondary atomization of the droplets, which basically can contain the COVID virus. So that is a big no-no in these cases, okay, especially in these times. So it's coming from the eye, not from the respiratory tract. Similarly, we also did a lot of work on fomites. These are the two sample images that you can see. The red colored things that you see are all the virions, and the crystals and other things are basically the salts. So this is how a fomite actually is distributed, or a viral load in a fomite is actually distributed when your cough or breathe, the droplets that you breathe out, they actually settle on the ground. So with this, I basically end my talk, and I hope that I'm keeping the time. So I would be ready to take any questions that you might have. Thank you.
Thank you, Professor Basu, for the nice talk. And I should say this is, a talk which covers state-of-the-art research topic. Now I can take a few questions from the audience.
Sure.
Someone raised his hand. I do not know. Any question from the audience?
I can see a hand raised. So.
Yeah. Mr. Sachin, can you please unmute your mic?
Sorry, actually, sir, this is hall 4, right? I have presentation number 177.
Sorry?
No. Okay. So now, the keynote lecture is going on. Please wait. Any questions from the participants? I guess there is no questions.
Hello, Professor Pitambar Randev.
Yeah, can you hear me?
Yeah, we can hear you.
Yeah. So, may I know your good name? Are you volunteer for this session?
Yes. My name is Shantanu Das.
Shantanu, okay. So, shall we start for this session?
Yes, sure, sir. Okay.
So, in the present session, we have around 8 papers.
Yes, sir.
Paper ID number 149.
Yes, sir.
152, 158, 161, 163, 165, 166, and 167. I request volunteer whether to check whether they are available.
Okay, sir. If all the participants are present, then we can start the presentation.
Yeah. So I welcome you all in this session. Now I request Shantanu to play the presentation by Chinu Rota and Akhilesh Kumar Sahu. Paper ID number 149.
Hello everyone, I am Chinu Raut, pursuing PhD in Chemical Engineering at NIT Rourkela under the supervision of Dr. Akhilesh Kumar Sahu, and I am working in the field of multi-phase flow problems. And today I am going to discuss about the topic numerical study on thin film flow of shear thinning fluid over a horizontal cylinder. The contents I am going to discuss about. So the thin film flow has a numerous number of applications in many manufacturing industry. These are like contact lenses, chocolate technology, paint industry, automobiles, drug-eluting stents, and in many other cases like microfluids and nanofluids. So the main aim of providing coating to any non-flat discrete object is to get a smooth, uniform, defect-free product of the specified film thickness range. So definitely it's going to be a challenging task to obtain a defect-free uniform coating over a non-flat discrete objects due to the presence of surface curvature and rotation rate of the object. So there are a number of literatures available on the flow of Newtonian and non-Newtonian fluid over an inclined plate, horizontal plate or vertical cylinder. So in the year 1974, Poknachev has studied one numerical model where a thin liquid film is flowing over a horizontal cylinder, and they tried to find a steady state solutions to the Navier-Stokes equation. So inspired by Puknachev, Moffat has considered a model that includes the effect of gravity and cylinder rotation. They got the results like without providing any rotational speed to the cylinder, simply due to the effect of gravity, the liquid will drain off, and by providing a non-zero rotational speed, the liquid bulge will be formed at the underside of the cylinder. In the year 1992, Rissfield and Benkoff has considered one model where a thin liquid film is flowing over a rotating cylinder, and they include the effect of surface tensions. They have solved the problem by using lubrication approximation theory, and they got the results like when intermolecular forces were included, then rupture occurs. So in the year 2004, Evans has presented a model for the evolution of coating film around a rotating cylinder, and they have concluded like with increasing the rotational speed, the size of the drop. Villanueva et al. Numerically investigated the flow of thin film of power law fluid down an inclined plate, and they got the conclusion like for shear thinning liquid, the highest wave amplitude is larger than the Newtonian fluid, and for shear thickening fluid, the highest wave amplitude is smaller than the Newtonian fluid. So in the year 2006, P. Chang and K. Louis have analyzed the stability of thin film or power law fluid over a vertical cylinder, and they got the results like on increasing the cylinder radius and flow index, the liquid film is more stable. In the year 2012, Brown et al. Has studied the tear film dynamics by using Ellis model, and Ganguly et al. Has studied the flow of thin film of power law fluid which is flowing down an inclined plane, and then they got the results like the noise of the bulb decreases as the value of the n increases. So from the above discussed literature, it can be concluded that non-Newtonian liquid film flow over a non-flat or stationary and rotating object is not yet explored. Hence, here an effort has been taken to develop a theoretical model to study the effect of shear thinning behavior on the evolution of thin film around a cylinder. This mathematical formulation. The problem consists of a solid cylinder around which a thin film of shear thinning fluid will be flowing, and the thickness of the film is very much smaller than compared to the radius of the cylinder. Here attention will be given to the evolution of thin film. Here two phases are involved. Phase 1 is air, phase 2 is thin film of shear thinning fluid, and is this is a multi-phase problem, so there is a need to track the interface present between these two phases, and this sharp interface can be tracked by using volume of fluid method. The assumptions considered here are incompressible flow and two-dimensional flow, and this problem is numerically simulated by using the commercial software code ANSYS. While solving the problem numerically using ANSYS software, first of all, we need to draw the geometry of the problem by using ANSYS design modeler. Then we need to divide the whole computational domain into smaller control volumes. That can be done by using meshing technique. As the film thickness is very much smaller, so in order to track the sharp interface present between the two phases, here structured meshing technique has been taken. So next is boundary condition. Here no slip boundary condition is considered near the cylinder wall. These are the governing equations that are needed to solve the problem. First one is equation of continuity, that is conservation of mass. Second is equation of motion, that is conservation of momentum, which says that the sum of all the forces will be balanced by inertial forces, where rho is the density of the fluid, mu is the viscosity of the fluid, and F is the external force, and V is the velocity vector. Next is power law model. So for better understanding the behavior of the shear thinning fluid, power law model has been considered, and the viscosity of the power law fluid can be given by this expression, where mu stands for the viscosity, m is the consistency index which measures the consistency of the flow, epsilon ij is the components of the rate of deformation tensor, I2 is the second order invariant of the rate of deformation tensor, and n is the power law index. Depending upon the value of power law index, the fluid can be categorized into different types. Like if the value of n is less than 1, then we can say that the fluid is shear thinning fluid, and for shear thinning fluid, the viscosity of the fluid decreases by increasing the rate of shearing. And the examples of these shear thinning fluids are like paint, glycerin, and blood. And for n equal to 1, the fluid is Newtonian fluid, and example is like water. And if the value of n is greater than 1, then the fluid is shear thickening fluid, and for shear thickening fluid the viscosity will be increases by increasing the rate of shearing. And the examples are like wet sand and confluent in water. Next is volume of fluid method. This method is used to track the sharp interface present between two immiscible fluids, and this method has a state function that is known as volume fraction, and this volume fraction can be represented by the symbol alpha. And if the value of alpha is 1, then we can say that liquid is present. If the value of alpha is 0, then we can say that other fluid is present. And if the value of alpha lies in between 0 to 1, then we can say that interface is there. So for a given computational domain, first of all the volume fraction value will be computed to each cell, then the interface will be reconstructed by using different approach like slick and plick. Slick is the simple line interface capturing approach which reconstruct the interface as a set of horizontal or vertical segment. And plick is the piecewise linear interface capturing method which is widely used for simulating the multiphase flow problems for accurately calculating the curvature uh, to reconstruct the sharp interface present between the two phases. In case of plick approach, the interface reconstruction is done by calculating the normal vectors in each cell faces and cell centers. Is volume fraction equations. So this is the advection equations which is derived from conservation of mass, and the value of density and viscosity will be found out by using this formula. And there is a force at the interface which creates a jump in energy and density at the interface, and in order to capture this jump condition at the interface, one model has been derived. That model is known as continuum surface force model, which has been derived by Blackwell in the year 1992. According to this model, the surface tension force will be added as a source term to the momentum equations, and then the momentum equations to solve. So the following equation shows the addition of surface tension force to the momentum equation. Next is numerical methodology. Here the solver used, that is transient solver, and the model used, that is volume of fluid method. And the material used here are like primary is the air and the secondary is the shear thinning fluid, and the pressure velocity coupling algorithm is piezo. Momentum equations are solved by using quick scheme, that is quadratic upwind interpolation of kinetic kinetics, and volume fraction equations are solved by using geo-reconstruct method, and time step is fixed. Next is validation. To check the authenticity and reliability of the numerical procedure followed here, the present results are compared with the existing numerical results presented by Receifold and Bankoff. They have considered a thin liquid film which is flowing over a horizontal cylinder, and initially they have given a uniform coating to the cylinder. Physically, due to the presence of gravity, the liquid film tries to drain up, but due to the presence of viscous force and surface force, it opposes the draining process. And at steady state, the extra amount of liquid flows downward and forms a liquid bulge near the bottom of the cylinder. So here the figure 4 shows a comparison of steady state film profile around the cylinder at bond number 100, and from this figure 4 we can conclude it that our results are matching well with the results presented by Bankoff and Receifold. Figure 5 shows the initial uniform coating profile at bond number 100. The blue contour shows that air is present, and red contour shows that liquid is present. This is the result obtained by using volume of fluid method, and figure 6 shows the steady state profile of the model at bond number 100. The blue contour line shows that phase 1 air is present, and red contour line shows that liquid is present. Next is shear thinning fluid. So for the shear thinning fluid, the calculations are done by varying the value of power law index from 0.6 to 1, and the calculations are started with a initial condition, that is uniform coating will be provided around the cylinder, and the liquid extra amount of liquid will flows downward and forms a drop like structure at the bottom side of the cylinder. The size of the drop depends upon the value of power law index, and here the size of the drop that is formed for n equal to 0.6, that is quite larger than the drop formed for n equal to 0.8 and 1. This behavior can be explained by the fact that for shear thinning fluid, the viscosity of shear thinning fluid will decreases with increasing the shear rate. That means the shear thinning fluid will get thinner and thinner when with increasing the shear rate. So this is the reason why a larger drop is formed in case of n equal to 0.6. The figure 8 shows the steady state volume fraction contour of the model at n equal to 0.6, n equal to 0.8 and n equal to 1. Conclusion. Here the numerical simulations has been carried out using volume of fluid method to see the effect of shear thinning behavior on the evolution of thin film flowing over a horizontal cylinder. For shear thinning fluid, the viscosity of the fluid decreases with increasing the shear rate, and the size of the drop formed for n equal to 0.6 is comparatively larger than the size of the bulge that is formed for n equal to 0.8 and 1. These are the references.
Hello. Thank you, Chinu,
thank you
for your nice presentation. Now it is open for questions to the audience. We can take 2 or 3 questions.
Okay, sir.
Any questions from audience? Shantanu, you allow them, huh?
Yes, sir, they are allowed. They can ask questions.
Oh, okay. Okay, if there are no questions, I have 1 or 2 small questions.
Okay,
like this is for shear thinning, right? Fluid.
Yes, sir. Yes, sir.
So I just want to know whether if the shear thickening fluid is used, then
Yes,
will
sir.
these observations hold, or there will be some deviations? I just want your
No, sir.
comment.
Yes, sir. We have calculated for shear thickening fluid like n equal to 1.2, and we got to know that if the fluid will be shear thickening, then the size of the drop will be decreases.
Okay, okay. One more thing I have seen in your presentation that there was no comparison or validations, you can say. Like you could have whatever solver you have used. I think
Okay,
you
sir.
have used some commercial software.
Yes, sir. ANSYS Fluent has been used.
ANSYS Fluent. Okay.
Yes.
So you could have validated that with some experimental result or some benchmark result available in the literature.
Yes, sir. That work is going on.
So that should have been first, because unless you validate your approach, methodology,
Yes,
then how can we be very sure about the results we get? So that is
Okay,
highly
sir.
essential in my opinion.
Yes, sir.
Okay, what was the motivation of using this shear thinning fluid?
Sorry, sir. Motivation of using this shear thinning fluid.
Yeah, where you find like this is very much important.
Sir, in case of while coating the in case of paint industry, we may get shear thinning fluid, na. So the main aim of providing coating to any of the substrate, if it is a complex substrate, then if we are providing a coating to that substrate, then we need to understand the physics behind that one.
Okay, okay, okay. And what about that interface profile? How did you determine that?
Sir, actually, for tracking the interface present between two phases, we are taking this volume of fluid method. This
Yeah,
volume
that's
of
okay.
Yes, sir.
Okay,
In that volume of fluid method, there is a advection equation that will be solved by using geo-reconstruct method. That geo-reconstruct method, they are using the Plick formulation, that is piecewise linear interface capturing method. In that method, at each cell, the normal vectors will be calculated, and after that, by taking the neighboring cells, the interface will be reconstructed.
Okay, thank you very much for your nice presentation. If there are no questions, then we can switch to the next candidate.
Thank you so much.
I just request Ashley Melvin and Janani Sri Murlidharan, right? Next speaker. Yeah, I just request Santanu to run this presentation by for paper number 152, right?
Sure.
Yeah, please.
Good afternoon, everyone. Today I'll be talking about numerical analysis of plasma extraction in a backward-facing step microchannel using OpenFOAM. The convalescent plasma therapy, or most commonly known as plasma therapy, uses the blood from a person who has recovered from an illness to treat others. Since the antibodies are present in the blood plasma, there is a need to extract pure plasma from whole blood, and this process is called plasmapheresis. As you know, plasma therapy has been one of the major weapons in our current battle against COVID-19. Once a COVID-19 patient recovers, his blood is extracted. Plasma is then separated from whole blood and is used to treat an active COVID-19 patient. This process of separation of plasma from whole blood is usually done using a centrifuge. Typically, centrifuges are large and it requires patients to have assays performed at the hospital or laboratory where the separation facility is located. With the help of the research in microfluidics chips are developed to replace the classic centrifuge. These microfluidic chips use biophysical effects such as the plasma skimming effect and various geometry effects induced by the microchannel design to extract plasma from whole blood. The plasma skimming effect causes the lateral migration of plasma particles, resulting in a plasma layer formation adjacent to the channel wall. However, this layer is too thin to extract plasma from the blood sample through conventional extraction techniques such as a basic bifurcation structure. Therefore, subtle geometry effects are relied on to extract plasma in such cases. The fabrication of microchannel is an expensive process and hence CFV analysis is mostly relied on to study these effects. Choosing the appropriate CFD method is the next big challenge. In literature, there are several studies using a variety of blood flow models. When the goal is to compare how well different microchannel structures perform against each other, researchers have largely considered blood flow models to resemble single-phase Newtonian fluids. For example, a 2010 study by Morimoto uses a single-phase model with spatially varying viscosity, while another study by Huang in the same year uses a constant viscosity single-phase model and assumes the fluid to have properties of water. The study by Huang also verified the trends observed in the single-phase simulations using experiments. There are several multi-phase studies as well, and one of them is by Zhang, who uses a two-phase model for the simulation using fluid. The CFD techniques used to study the plasma extraction process vary in fidelity. While high-resolution techniques, as in the study by Zhang, can predict concentration of RBCs in the extract based on the inlet blood hematocrit, low-fidelity techniques used in the study by Huang can only establish whether one microchannel design is more efficient than the other. It cannot actually give the amount of plasma being extracted. Having said that, the results from the single-phase simulations in the study by Huang as well as Morimoto were verified experimentally. The main objective of our current study was to analyze the plasma extraction process using a two-fluid model in an open source CFD software, OpenFOAM. While this model might not be as sophisticated as the two-phase model used in the study by Zhang, it models plasma extraction process much better than the single-phase model. Since the parameters used to quantify the extraction efficiency is dependent on the fluid model used, we expected a better quantification of the plasma extraction process in our multi-phase simulations. In this study, we have also proposed a new microchannel design and have compared it against two of the micro designs proposed by Huang in his study. We started with the single-phase simulations to validate two of the backward phasing step microchannels proposed in the study by Huang. We then analyzed the newly proposed microchannel design using the same parameters and techniques used in the study by Huang. The three microchannels were further analyzed in the multi-phase simulation to see if their performance could be quantified better than the single-phase simulation. In a backward-phasing step microchannel, the geometrical effects such as recirculation and development of separated flows aid in extracting the thin plasma layers. The figure shows the schematic of the plasma extraction process. In the streamline plot, all the streamlines below the dashed line will go into the side channel through which the plasma is extracted. Any particle whose size is more than R will not be extracted through the side channel. Also, the ratio of the flow rate in the side channel to that at the inlet given by alpha is a measure of the efficiency of the extraction process. We have used 3 microchannel designs in our study. Type 1 microchannel has a straight inlet and has the same dimensions as that used in the study by Wang. Type 2 microchannel has a bent inlet and again has the same dimensions as that used in the study by Wang. In the study, we have also proposed a novel microchannel design, type 3, which is both bent as well as converging at the inlet. In our study, we have used the single-phase model, just like the study by Wang, by considering a Newtonian fluid having the properties of water. The results from the single-phase simulations performed using OpenFOAM matched fairly well with the results from the study used for validation. The errors can be attributed to the reduced mesh size and other computational constraints in our simulation. More importantly, it was observed that the newly proposed model had the highest flow rate ratio amongst all the designs. Now, to measure the minimum radius R of the particles which can be excluded from the side channel, the distance of the last streamline entering the side channel from the inlet wall was measured as shown in this figure. The minimum radius R of the particles which can be excluded from the side channel was also observed to be the least in the newly proposed model. Since the goal was to identify the model with the highest flow rate ratio and the least R, the newly proposed model was found to be the most effective of the 3 models. We then moved to the multiphase simulations by solving the 2 fluid model equations for plasma and blood. We expected to capture the plasma extraction process more accurately in our multiphase simulations. The 2 fluid model assumes both plasma and blood to be Newtonian fluids, and the OpenFOAM solver used in our study employed an additional interface sharpening methodology. For the multiphase simulations, the plasma and RBCs were assumed to be separated and stratified as they entered the microchannel. This assumption is based on the plasma scaling effect, resulting in the formation of a plasma layer adjacent to the bottom wall at the inlet as shown in the figure. Further, we've assumed that the plasma layer has a thickness of 10 micrometers. The thickness was chosen keeping in mind the particle size R from the single-phase simulation results. To quantify the efficiency of plasma extraction process, we examined 2 properties. The first parameter is the plasma flow rate ratio, which, unlike the flow rate ratio from the single-phase simulation, measures the ratio of volumetric flow rate of plasma leaving the side channel to that entering the microchannel. The other parameter is the measure of fraction of plasma in the extracted mixture. This parameter determines how pure the extracted mixture is in the plasma extraction process. We've normalized the plasma fraction using the highest value of the plasma fraction amongst the 3 microids studied. The results from the multiphase simulations show that model 3 has the highest plasma flow rate ratio, just as was observed in the single-phase simulations. In addition, for the chosen plasma layer thickness, the plasma percentage in the extracted mixture was found to be the highest in the newly proposed model. The first goal of this study was to validate the single-phase simulation results in the literature using OpenFOAM. While the results deviated slightly due to computational constraints, the trend in results were verified. We then repeated the simulations using a 2-fluid model. The 2-fluid model gave a better understanding of the plasma content in the extracted mixture. While the results from the single-phase simulations assumed that for a given model, all the plasma within R will be extracted through the side channel. Multi-phase simulations showed that that isn't the case. While accurate modeling of plasma extraction process requires high fidelity methods, qualitative analysis of extraction efficiency can be done using the low resolution models used in the study. Additionally, we also observed that the newly proposed design performed the best among the three macro channels in both the single phase and the multi-phase simulations. Due to computational constraints, the effect of plasma layer thickness on the extraction efficiency, especially the plasma percentage in the side channel of various models, could not be analyzed. This is one parameter we would like to examine much more in detail in our future studies. We would also like to carry our present work forward for more microchannel design as well as for different rheological models. Finally, we would like to thank everyone who helped put this conference together for giving us an opportunity to show our work to this esteemed group of people.
Thank you, Ashley, for a nice presentation.
Thank you, sir.
Now it is open for questions to the audience. We can take 2-3 questions. Okay, I have 1 or 2 queries actually. Like okay, in the figure 2 in your paper, there is a bend you have shown. So how have you decided for meshing? Because is there some refinement or not, and how did you choose in the block mesh?
Yes, sir. So for refinement, we had refined along the inner curves because we had plasma there and we had fixed a plasma layer. So we refined it more there, and the plasma layer thickness was also less. So when we considered the block itself, we considered plasma to enter through the bottom block, which is the more refined block. So we have considered the same blocking structure for all three meshes, wherein the plasma inlet is through one of the bottom block, which is a smaller block.
Okay, okay. So block wise, you have done the grading, right? Different grading?
Yes, sir.
Yeah, okay, okay. That is okay. And what was the value of Courant number you have? Was it adjustable or you have given?
For the single phase simulation, I mean, it was a steady state simulation, so we didn't really bother about that. But for the two phase simulation, we had kept up Courant number of around 0.9, and time step was adjustable.
Okay, time step was adjustable. But I have one query. Very fundamentally means, like you have taken some domain. So is it you have followed some paper or some reality you have seen on that?
So for the model number 1 and model number 2, we had taken from this paper by Huang from 2010, where they did a single phase simulation and compared it with pig blood simulations, and they compared it to see how the particles were moving using fluorescent some dispersion, and they validated against that. So our idea was to just move ahead with a new model, model 3, and also to see how two-phase models work in this situation.
But this paper is about, I think, multi-phase flow, right?
This paper is about multi-phase flow, so yes.
Yeah, and as per your presentation, it can be seen like you have considered water to represent blood plasma, right? Single phase simulation, right?
Yes, sir.
And water air for multi-phase simulation kind of thing, right?
No, sir. Plasma. It was plasma red blood cell, but we didn't consider the non-Newtonian.
Yeah, that was my point actually. You have assumed there is viscosity constant, so I think it is oversimplification, right?
So the idea was to see how what do you say, how effective it is. I mean, people who did the single phase simulation, their goal was to establish how relatively efficient these models were. And when they validated with the big blood simulation experiments also, so we thought we would take it a next step by considering a little bit more sophisticated method in two phase, but still it's simplified compared to a
Yeah.
realistic model.
And also, I think your plasma fraction values that you have obtained are at an arbitrary time instant, or is there any logic in deciding
So
time
that is the
instant?
time average. So after it reached a pseudo steady state, we ran it for some more time, and we averaged it over the pseudo steady state only.
So can you justify that these are your steady state solutions or what? Like,
So these are time averaged values from the pseudo state solutions. So they were fluctuating through time, but with pattern. So we averaged it over that time only. Initially, there were a lot of fluctuations, so we waited it to become a steady fluctuation, and then we averaged it over only that time.
okay, I have one query again.
Yes, sir.
Why do you have used like multi-phase Euler form instead of interform? Because interform is very widely used for this kind of simulations.
Yes, sir. So first thing we wanted to see was how the because two-phase models were which was mostly used in when they were studying even for in Fluent two-phase Euler form, either the uh, Fluent version of the two-phase Euler form was what was being used in most of the study when they had to study centrifugal effects and external forces on particles. So we wanted to see how an interface capturing added to that can help. So multi-phase Euler form has that additional artificial compression term which helps in capturing interfaces better, and we wanted to see how that will help us analyze this better. And yes,
Yeah, please go ahead.
no, so yeah, that was the main motivation behind it, to see how a two-phase model plus an interface capturing technique can help see this phenomenon better.
Okay, and the plasma factor is 1 somewhere in the type 3 microchannel. So what was
That
that indicate
is,
actually?
it was we had normalized it with the maximum value, sir. So just to show how relatively better our model was.
So it is a normalized value, right?
Normalized value, sir.
So thank you, Ashley, for such a wonderful presentation and the explanations. So thank you very much.
Thank you, sir.
Now I request Shantanu to verify whether this Sangram Kumar Samal, the paper ID 158 is available.
Yes, sir, he is present. I'll start the presentation.
Yeah, please run the presentation.
Everyone, I am Sangram Kumar Samal. Today I am going to present seminar on numerical investigation on thermohydraulic performance of water oil to water nanofluid in recharging and simple microchannels, a comparative study. First of all, what is microchannel? So microchannel is a channel with a hydraulic diameter in the range of 1 micrometer to 1000 micrometer, and it is engraved on a solid substrate through which fluid will flow. Compared to conventional channel, microchannel having larger surface area to volume ratio, due to which the microchannel can able to dissipate large amount of heat flux compared to conventional channel. Due to the compact design, lightweight and larger surface area to volume ratio, microchannel is widely used for electronics cooling applications in the form of microchannel heatsink. These are the literatures. Tucker and Pease first developed the first microchannel heatsink, which is able to dissipate large amount of heat. After that, many researchers used some heat transfer enhancement techniques by using ribs and cavities, or by using the concept of breaking and redeveloping thermal and hydraulic boundary layers like interrupted microchannel, hybrid microchannel, slot jet model, recharging microchannel. Some researchers used nanofluid for heat transfer enhancement. From this literature, it is observed that heat transfer can be enhanced by breaking and redeveloping the hydraulic and thermal boundary layer, and it also augmented by adding solid nanoparticles in the working fluid. Based on these conclusions, the objective of present work is to numerically investigate the effects of nanoparticle volume concentration and Reynolds number on the fluid flow and heat transfer performance of water L2O3 nanofluid in recharging and simple microchannel. These are the schematics of simple microchannel and recharging microchannel. Recharging microchannel divides the simple microchannels into multiple number of divisions by placing transverse wall and equal intervals. Each divisions will have its own inlet and outlet through the top cover plate. Due to independent inlet and outlet, both thermal and hydraulic boundary layers develop in each smaller channels, and flow remains mostly developing in nature across the substrate length. This reduces the fully developed region length and thus likely to enhance the heat transfer performance. By assuming the fluid flow is steady, single-phase laminar incompressible flow with constant thermophysical properties, and there is no internal heat generation in solid domain, these are the governing differential equations used for the simulation. For the numerical simulation, the nanofluid is considered as a single-phase fluid by assuming that there is negligible motion slip between the solid particles and the base fluid, and both the base fluid and solid particles are in thermal equilibrium. And these are the these formulas are used for calculating the effective properties like density, specific heat, thermal conductivity, and dynamic viscosity. Nanofluid enters through the inlet with constant inlet velocity and constant temperature of 300 Kelvin. Outlet are subjected to the zero pressure outlet boundary conditions, and constant heat flux of 40 watt per centimeter square is applied on the bottom surface of the substrate. Outside walls and symmetry planes are insulated. Fluid solid interface are subjected to conjugate heat transfer and no slip condition. To choose optimum grid size, a standard grids independent test procedure is carried out for both the recharging and simple microchannel. For this purpose, grid size of 0.02 to 0.05 is considered, and for all the grid size, pressure to be calculated for both the channels. From this table, it is observed that when the grid size changes from 0.025 to 0.02, there is very negligible change in the negligible difference in the pressure drop in both the channels. Therefore, the grid size of 0.025 is considered as optimum grid size for the simulations. To check the accuracy of present numerical model, the validation is done by comparing the present numerical model with the experimental data of Lee and Mudawar, and the results of the substrate wall temperature at different locations along the flow direction for water as well as 1% and 2% L2O3 nanofluid are evaluated using the present numerical model and compared with the experimental data and represented in this figure. From this figure, it is observed that the present numerical model is validated with experimental data with a maximum percentage difference below 5%. This is the temperature distribution in both the channels for different nanofluid volume concentration at Reynolds number 100. From this, it is observed that as the nanofluid concentration increases, the substrate temperature decreases. This is because the thermal conductivity of nanofluid increases with nanofluid volume concentration, which increases the heat removing capacity of fluid and leads to decrease in substrate temperature. It is also observed that the maximum substrate temperature is very less in the recharging microchannel compared to simple microchannel. This is because in recharging microchannel, the fresh fluid enters through the inlet of each small channels simultaneously and travels a small distance, carries heat, and exits through outlets. Whereas in simple microchannel, as the hot fluid travels longer distance, its heat carrying capacity decreases. Therefore, the substrate temperature is higher compared to recharging microchannel. Here is the variation of average heat transfer coefficient with Reynolds number for different nanofluid volume concentration in both the microchannels, and the average heat transfer coefficient calculated using the formula using this formula. From this figure, it is observed that As the Reynolds number increases, the convective heat transport, average heat transport coefficient increases. This is because as the Reynolds number increases, the boundary layer becomes thinner, which increases the heat carrying capacity of the fluid. It is also observed that the nanofluid with higher nanoparticle concentration shows higher average heat transport coefficient in both the microchannels. This is because the effective thermal conductivity of nanofluid increases with increasing volume concentration, which enhances the convective heat transfer in the fluid. In addition, the recharging microchannel shows higher average heat transfer coefficient compared to simple microchannel. Cooling uniformity is used to check the temperature distribution uniformity on the substrate bottom surface or heated surface. The temperature distribution will be more uniform with a lower value of cooling uniformity. The cooling uniformity is calculated using the formula, whereas Tmax is the maximum substrate temperature, Tmin is the minimum substrate temperature. From this figure, it is observed that the cooling uniformity decreases with both increasing both Reynolds number and volume concentration. This indicates that the temperature on the substrate bottom surface can be distributed uniformly for higher volume concentration and higher Reynolds number. It is also observed that recharging microchannel shows lower cooling uniformity value compared to simple microchannel. This indicates that the temperature distribution is more uniform in recharging microchannel compared to simple microchannel. This is due to the heat removal by the fluid at periodic interval in recharging microchannel. Thermal resistance is evaluated using this formula, whereas Tmax is the maximum substrate temperature, Tin is the inlet fluid temperature. And here from this figure, it is observed that with increasing both Reynolds number, the thermal resistance decreases. This is because as the Reynolds number increases, the convective heat transport by the fluid increases, which enhances the convective heat transfer coefficient. As the convective heat transfer coefficient increases, the convective thermal resistance decreases, which leads to lower thermal resistance. It is also observed that with increasing nanoparticle volume concentration, the thermal resistance decreases. This is because addition of nanoparticle increases the fluid thermal conductivity, due to which convective heat transfer coefficient increases and convective thermal resistance decreases. It can also be noticed that the recharging microchannel shows reduced thermal resistance compared to simple microchannel. Pressure drop. In simple microchannel, the pressure drop is calculated as the difference between the inlet pressure and outlet pressure, whereas in recharging microchannel, it is calculated as the cumulative pressure drop in each small channels. From this figure, it can be observed that the pressure drop increases with increasing both Reynolds number and nanoparticle volume concentration. This is because fluid velocity increases with Reynolds number, which increases velocity gradient near the wall, leads to enhanced wall shear stress, which concurrently increases the pressure drop. Additionally, with increasing nanoparticle volume concentration, nanofluid viscosity increases, which results in increased pressure drop. It is also observed that the recharging microchannel shows higher pressure drop compared to simple microchannel. This is due to the presence of multiple inlets and outlets, along with multiple bends near the inlet and outlet in recharging microchannel. From both the thermal and hydraulic analysis, it is observed that using nanofluid, heat transfer coefficient is enhanced, whereas pressure drop also increases. Thus, it is important to analyze the overall performance of nanofluid over base fluid by evaluating the performance factor. The variation of performance factor of nanofluid over base fluid with Reynolds number for different nanoparticle volume concentration is depicted in this figure. From this figure, it is observed that the performance factor of nanofluid decreases with increasing volume concentration. This is because of higher volume concentration. This is because at higher volume concentration, chances of particle accumulation increases, which increases the pressure drop and decreases the overall performance. It is also observed that the performance factor value is below unity for both the recharging and simple microchannel. This indicates that the overall performance of water-based nanofluid is lower as compared to the pure water. In brief, the thermal performance of both the microchannel enhances by using nanofluid, but At the same time, pressure drop and pumping power requirement increases. Therefore, it can be said that the use of nanofluid is beneficial for heat transfer enhancement only when there is no constraint on pumping power requirement. The variation of performance factor of recharging microchannel over simple microchannel with Reynolds number for different nanoparticle volume concentration is shown here. It can be observed that the recharging microchannel shows better thermohydraulic performance compared to simple microchannel with a maximum performance factor of 1.65. These are the following conclusions drawn from this work. From this work, it is observed that utilization of nanofluid is beneficial for heat transfer enhancement where pumping power is not a constraint, and the recharging microchannel shows better thermohydraulic performance compared to simple microchannel with a maximum performance factor value of 1.65. Thank you.
So, thank you, Sangram Kumar.
Thank you. Yes, sir.
Now it is open for questions. We can take some 2 or 3 questions from the audience. Okay, I have just 2-3 queries. That what was the motivation of the study?
So, the motivation of study is to use the nanofluid in recharging microchannel. Which one is proposed by us, and compare that with the conventional straight microchannels. This is simple microchannels.
Okay. So this can be used for like electronic chip cooling, as you have written in your paper.
Yeah. Yes, sir. In the form of heat sink, sir.
Yeah. But you see, the nanoparticles are very costly. Yeah. So how is your model cost effective from the perspective of employing nanofluid?
Sir, actually, we found that by using nanofluid, the heat transfer enhanced, but as well as the pressure drop also increases, due to which the overall performance factor is decreases. So, for the application, practical application, I think it may be not beneficial. So,
yeah. Anyway, how do you justify the nanofluid effective property evaluation formulas that you have employed? Are valid?
That we have. We have taken from the book, one book written by Bianco et al.
Okay. But you should know.
That is the thought. Yes, sir.
So you have referred to that or what?
Yes, sir. From that book, there is some models, different models for thermal conductivity, density. For thermal conductivity, it is Hamilton-Crosser model is used.
You could have used
equations.
You could have some reputed journal papers. No, you could have referred for that. No? Is it not?
Yes, sir.
Okay. Okay.
Yes, sir.
Okay. Anyway, just a thought that came to my mind. Now you tell me how many boundary conditions are required at the solid fluid conjugate interface? Like you have used no conjugate solid fluid conjugate.
Conjugate heat transfer and no slip boundary conditions.
Okay, those are required. Now
at the solid fluid interface.
Yeah, please go ahead.
So at the solid fluid interface, 2 boundary conditions required. One is no slip boundary condition, and another is conjugate heat transfer boundary condition.
I have seen your in your conclusion that you are suggesting that on the basis of thermal resistance, whether using nanoparticle is recommended or not. Like, I don't understand this. That how the thermal
actually,
yeah.
Sir, from our observation, it is observed that nanoparticle enhance the thermal performance, but hydraulic performance is also increases. Hydraulic performance is degraded. That means pumping power requirement increases. So
Okay.
that is our.
No, I was talking about thermal resistance. You have written in your conclusion.
So thermal resistance decreases.
So you are saying that thermal resistance, from the thermal resistance, we can recommend the use of nanoparticle, right?
Yes, sir. From the thermal performance, because it also enhance the heat transfer coefficient also, and
Okay.
also enhance the cooling temperature distribution uniformity also.
Okay. So just last question to you.
Yes.
Like, can SMC be better alternative than RMC, especially at higher Reynolds number and higher nanofluid concentrations?
Sorry, sir, I didn't get you.
Can SMC be a better alternative as compared to RMC, especially at
No,
higher?
sir. At a higher nanos number, also the recharging microchannels gives better performance. Sir.
Okay. Okay.
Yes,
If anybody has any questions, they can still put. Shantanu, please allow them.
Sure, sir. Sure, sir.
Okay.
Can we move on to the next?
Yeah. Please go ahead. Thank you, Sandra.
Thank you, sir. Thank you, sir.
So next candidate is, I think, Subhanshu Rai. No, Kapil Kumar.
Hello everyone, I will appreciate your patience and attention for a few moments. My name is Kapil Kumar and I am a master's student at Indian Institute of Technology, Jodhpur, India. The topic for my presentation is a CFD investigation of turbulent mixing in horizontal T-joint. So here is the content of my presentation. I am going to discuss introduction, motivation of the study, objectives of the study, computational model, methodology, results, conclusion, and future work. The first thing I would like to discuss is the pipe system. Pipe systems are used to convey the fluids from one location to another location. It is an essential element of processing plants and a distribution system. Pipe systems have several elements like valves, flow meters, elbows, angle joints, T-joints, etc. Here we can visualize a T-joint. T-joints are used for two purposes. First is mixing of two fluid streams, and second is to distribute main fluid stream into two fluid streams. In this study, turbulent flow across a horizontal T-joint is analyzed. Now the things which motivates to perform this kind of study are various industrial applications of T-joint like nuclear power plant, chemical plants, and many other cooling applications. This figure shows an industrial application of the T-joint. The another aspect is research and development on flow behavior across a T-joint, optimal parameters selection for effective mixing, mitigation of losses on failure of T-joint, and appropriate material selection. Objectives of the work presented here are analysis of flow across a T-joint to get average velocity, temperature, and pressure profiles during turbulent mixing and to investigate the region at which maximum mixing takes place. So the next thing is a computational model. The figure shows a 2D model of the T-joint. This geometry is created in ANSYS Fluent itself. Here is the section 1 through which the hot fluid enters. Here is the section 2 through which the cold fluid enters. And here is the section 3 which is outlet. Dimensions of this model are provided in this table. In this problem, steel is taken as the pipe material and water is taken as the working fluid. Now I would like to discuss the methodology used in this numerical investigation. Assumptions made in this work are incompressible fluid flow, constant fluid properties, uniform velocity profiles at both the inlets, and adiabatic pipe walls. CFD tool used for this simulation is ANSYS Fluent. In this work, the meshing has an skewness of 0.5 and its orthogonal quality is approaching to unity. This graph shows the mesh sensitivity test which is performed to ensure that solutions are independent of the meshing elements. As shown in the graph, the solutions become independent around at 1,10,000 of the meshing elements. So next, let me talk about the governing equations. This first equation is the mass conservation equation, which is a time averaged continuity equation. Equation 2 and equation 3 are the time averaged momentum equations. Fourth equation is the energy conservation equations. And equation 5 and equation 6 are the transport equation for the turbulent kinetic energy and turbulent dissipation rate. The boundary conditions applied in this model are provided in this table. So here are the results obtained in this numerical investigation. This figure shows the temperature distribution across the T-joint. Here the temperature is varying from some 300 Kelvin to 351 Kelvin. And here is the graphical representation of axial variation of temperature of central streamlines. As we can see that the temperature of both the streamlines remains constant before mixing, but as the mixing starts, the temperature of hot steam decreases and the temperature of cold steam increases. Thus, the temperature difference between these water streams keeps on decreasing in the downstream direction. Now, this figure depicts the velocity distribution across the joint, in which velocity is varying from 0 to 0.078 meter per second. At walls, the velocity is 0 due to no slip boundary conditions. Axial variation of the velocity of the central streamlines is provided in this graph. Velocities acquire a maximum value just after the here the enlarged view of velocity vector is provided just after the mixing start. At this point, the vortex formation takes place, which is a region of minimum velocity. Pressure distribution in the system is shown in the figure, in which the pressure is varying from minus 1.77 Pascal to 2.18 Pascal. Before the mixing, the pressure is higher, which acquires a negative value just after the mixing starts, which is further increases to zero gauge pressure at the outlet. Now the graph provided here represents the axial variation of the turbulent kinetic energy. Basically, the turbulent kinetic energy is an index of the turbulent mixing intensity. As we can see in the figure that before the mixing, the turbulent kinetic energy has a low value which is increased as the mixing starts. It has a maximum value around at 0.5 meter from the inlet of the hot fluid stream. So at this location, the mixing is maximum. Conclusions of this research work are the temperature difference between the water streams decreases in the downstream direction, and the outlet velocity of both the water streams calculated at the central stream lines has approximately similar values. Pressure in the system acquires a negative value just after the mixing starts. And turbulent kinetic energy is used as an index of turbulent mixing intensity, which helps in locating areas of maximum turbulent mixing. The future aspects of this work are first, the validation of the developed model and development of a 3D model to affirm the accuracy of the developed 2D model. And the material should be selected such that it can bear the maximum thermal stresses generated. And I will also perform some parametric study by varying the variables such as temperature, velocity, pressure to optimize the mixing for a given application. So that's all from my side. Thank you so much for your attention.
So thank you. We would like to have 2-3 questions on this.
Okay, sir.
Kapil Kumar.
Sir, am I audible, sir?
Yeah, you are audible. Huh? So Shantanu, just allow the participants to ask questions.
Yes, sir. The participants may ask questions now.
Anyway, for want of time, I will ask some 2-3 questions.
Okay, sir.
Yeah. So you have used, I suppose, K epsilon model, turbulent model.
Yes, sir.
Why not other models you have preferred?
Sir, for turbulent flow, we have another model like K omega model, and all, but the K epsilon model is simple to implement, and the computational cost is also lesser than the other models. So because in this work mainly the results I emphasize on the results away from the walls, so I think K epsilon model is better than any other model.
No, I thought because it is a T junction kind of thing, no? Pipe bending, right?
Yes, sir.
Flow through pipe bends, something like that, no?
Yes,
So
sir.
I thought there is a sudden change in the direction of flow, leading to the tendency of separation. So
yes, sir.
I thought in such kind of flow, people use K omega model.
Sir,
yes,
sir.
There are several studies where they have used K omega model preferably.
Yes,
so
sir.
Model, because that is suitable, I think.
Yes, sir. K omega model is suitable for the problems in which flow separation takes place.
Yeah.
But another a disadvantage of the K omega model is that it will take more time to converge the solution. So
that is okay. Time is okay, but as long as the physical situation demands a particular choice of turbulent model, we should go for that. Anyway,
yes, sir. Definitely, I will do further work on that.
Such kind of flow situation demands, I think K omega model would be more preferable.
Yes, sir. Sure, sir.
Right?
Yes, sir.
Okay. If there are no more questions, then we can proceed to the next candidate. Next speaker. Next
Thank you,
speaker
sir.
is, I think, thank you, Kapil Kumar, and next speaker will be like Subhanshu Rai.
Thank you, sir. Thanks, sir.
Yeah. So, Subhanshu, you can start. Huh?
Hello everyone, I am Subhanshu Rai, Master's student from IIT Jodhpur. The topic of my presentation is numerical investigation of natural convection in an enclosure with bottom heating. These are the contents. I will be going through these points as the time progresses. Natural convection. In this mode of heat transfer, the fluid motion occurs by natural means, that is, by buoyancy force, which arises due to change in the density of the fluid. If we consider this hot horizontal plate, which is at higher temperature than the surrounding fluid, then the temperature of the adjacent air to this plate will rise. Consequently, the plate is surrounded with thin layer of warmer air. Since the temperature of air adjacent to the plate is high, thus its density is lower. As a result, heated air will rise and this movement is called natural convection current. In a similar way, when the surface is vertical, the flow of air around the surface will occur accordingly. In internal natural convection, the fluid is confined within the enclosure and there is a thermal communication with all the walls that confine it. As you can see from this figure that the fluid is confined within an enclosure and the movement and the heat transfer of the fluid within the enclosure will occur according to the boundary conditions provided at the different phases of the enclosure. Internal natural convection has many practical applications. So their study is important to optimize the fluid flow, heat transfer, and temperature distribution in different regions. These are the few practical applications of the internal natural convection phenomena, that is solar collectors, double wall insulation, electronic and room cooling or heating. So for designing such kind of system, the understanding of natural internal convection is required. As you can see from this figure that this is a flat plate solar collector and natural convection occurs in the air gap between the glazing cover and the absorber plate, and it plays an important role in determining the thermal losses of the solar collector and its efficiency. This is the problem statement of our study. The analysis is two-dimensional and the enclosure is of squared shape having dimension of 0.15 meter. Atmospheric air is taken as fluid, having uniform heat source located at the bottom of the enclosure. For the CFD modeling, following assumptions are made. Thermophysical properties are taken as constant. Flow is assumed to be incompressible, and the wall temperature are constant. Business approximation is applied in the present work. For the detailed analysis of the business approximation, please refer to our paper or see the last slide of this presentation. The governing equation used to simulate the incompressible laminar flow are conservation of mass, momentum, and energy. This first equation represents conservation of mass. The second and third equation represent conservation of momentum in x and y direction respectively, while the last equation represents conservation of energy. As you can see from these four equations that it does not contain any variable term of density. It has this term of rho naught, which is a density at initial temperature and is constant. If I talk about meshing, meshing is done by using block mesh utility offered by OpenFOAM. 400 hexahedral cells are used in each direction. The elements are defined close to the wall by using simple grading tool. The hexahedral cells are chosen over other cell shape because it can be further divided anisotropically without compromising the element quality. It is the best cell suited for this application and for this geometry. The walls of the enclosure are subjected to different temperature. The left and right wall is at 295 Kelvin. The bottom wall is at 305 Kelvin, while the fluid temperature is 300 Kelvin. And all the thermophysical properties of fluid is calculated at this 300 Kelvin temperature. For doing this simulation, OpenFOAM version 7 is used. Buoyant pimple foam solver is used to simulate this case. Buoyant pimple foam is a transient solver suited for both compressible as well as for incompressible flow. And the residual factor used for each variable is of the order of 10 raised to power minus 5. To do the simulation, OpenFOAM is chosen due to its capability to simulate the dynamic behavior of the system. Furthermore, it's freeware, that is, no licensing cost is required. And most importantly, it is as powerful as any other commercial software. Grid independence test is conducted by varying the number of elements from 625 to 1,60,000. The change in two critical variables, namely mean temperature at the center line of the enclosure in the y direction and the average Nusselt number, are observed to test their sensitivity with respect to the meshing element. The percentage error obtained in the mean temperature value between 10,000 elements and 1,22,500 elements is 0.019%. Similarly, the percentage error in the value of average Nusselt number between the same number of elements is found to be 0.86%. These errors are very nominal, so simulation can be performed using lesser number of cells having any values greater than 10,000. But in this work, a large number of cells is used to reduce the error to minimum possible limit by taking advantage of computational capacity that we have. This section presents the result obtained from the numerical model and discusses the convective phenomena observed. Following figure shows temperature variation inside the enclosure at t is equal to 10 seconds and 100 seconds. This first figure represents the temperature distribution at t is equal to 10 seconds. As you can see from this figure, that fluid at the bottom face is being heated while fluid at these two vertical faces is being cooled. So as the time progresses, fluid start moving in downward direction from these two vertical faces, while fluid will start rising up from the bottom face due to the buoyancy effect. Following figure represents temperature distribution at 500 and 1652 seconds. As the time progresses, fluid will get heated from the bottom face and cooled from the left and right faces simultaneously. Air rises from the bottom due to heating and reaches top wall of the enclosure, and then finally splits up into two parts and moves toward left and right faces, which leads to the cooling of the air from left and right faces, which is maintained at lower temperature. So it moves in a downward direction due to the buoyancy effect, and this process goes on in this cyclic manner until the system achieves steady state condition, as shown by this figure. Following figure shows magnitude of velocity distribution in an enclosure, and it is observed that the magnitude of velocity is maximum near to the wall surfaces and also at the center line of the enclosure. Air on the left hand side of the enclosure will move in a circular manner having an anti-clockwise direction, while on the right hand side of the enclosure, air will circulate in clockwise direction. Variation of average Nusselt number with time is also plotted. As you can see from this figure, that as the time progresses, the value of average Nusselt number increases, and at steady state condition, it achieves a value of 15.98. Local Nusselt number is calculated on the heated bottom face at steady state condition. Variation of local Nusselt number is studied with x varying from 0.01 to 0.14 meter, as shown in the following figure. Regions very close to vertical walls are neglected due to error change in the boundary conditions. Local Nusselt number has very high value close to the vertical wall, which implies that there is a larger temperature gradient in that region, while at the center of the enclosure, temperature gradient possesses minimum value. Please refer to our paper for the mathematical formulation of the local Nusselt number and also for the average Nusselt number. These are concluding remarks of our study. We have developed 2D numerical model to investigate natural convection phenomena in a square enclosure with bottom heating. And the result shows that the air on the left hand side of the enclosure circulates in anti-clockwise direction, while on the right hand side of the enclosure, air will circulate in the clockwise direction. The local Nusselt number is maximum at the edges while minimum at the corner. And we have observed that the system has achieved a steady state condition after 1600 seconds. The data that we have obtained from literature show good agreement with the obtained result, which validates our model. These are limitations and future work plan of our study. The study is limited to simple geometry at fixed orientation, subjected to constant wall temperature boundary condition, and also the effect of entropy generation is not considered in this work. The present model that we have developed and later verified it will help us to simulate other practical application problem like room heating, cooling, solar collectors, double wall insulation, air circulation through a room within a building, etc. Thank you. Any questions?
Hello. Yes, sir.
Thank you very much for your nice presentation. Now it is open for questions. We can have at least 2-3 questions from the audience. Hello.
Yes, sir.
Shantanu, you allow them to speak, huh?
Yes, sir. They are all allowed.
Yeah, yeah. Okay, I have 1 or 2 questions. See, Shubhanshu, you have done in open form, which basically takes a 3D geometry, right? So your problem was 2D. So how did you manage that?
So by applying empty bounding condition.
Okay. So how much width was taken there?
Width was around it was minimal. It was around 0.01 meter.
Okay. So that doesn't make any difference, right?
Yeah.
Okay. 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 Anyway, and one more question: like, have you done any changes in like FV scheme and FV solutions for your problem?
No, sir. I have used for transient term Euler scheme, while for gradient scheme I have used Gauss linear, and for various divergence scheme I have used Gauss occult. I haven't played with various schemes.
Okay. And what about Courant number?
Courant number was around 0.4.
0.4. So it was adjustable or it was fixed, like from your side?
It was fixed.
So what is the logic behind that?
To get the stable solution, Courant number must be below 0.5.
Okay. Yeah.
Yeah.
So, but I fail to understand the novelty of this work in the sense like cavity, you will see 100 and 1,000 papers almost.
Yes. Yeah. And in this paper we have just developed one dynamic model, and later we have verified it citing various research paper. Later on we will simulate various practical applications like room heating, cooling, or the flow of air within a building that is intended for future work.
Okay. Okay. If anyone has any questions, he can still ask. Otherwise, we will move to the next candidate. So next is, thank you, Shubhanshu, for nice presentation. Now we will move to next speaker, Nidhi Singh, paper ID 165.
Good morning to all. I am Nidhi Singh, research scholar in the Department of Mathematics, IGNTU, Amarkantak, Madhya Pradesh. I am here to present stability of mixed convection flow in a differentially heated vertical channel under transverse magnetic field with internal heat sources. What is hydrodynamic stability? Hydrodynamic stability is the leading branch of CFD. It concerned with the response of laminar flow to a disturbance of a small or moderate level. What is stable flow? If certain disturbance is inserted into the flow and flow returns to its initial state, then flow is said to be stable. And if disturbance grows and convert the flow to another state, then flow is said to be unstable. This is the simple concept of stable and unstable system. If we slightly disturb the ball and ball returns to its initial state, then system is said to be stable. And if ball never returns to its initial state, then system is unstable. And if ball lies in fixed band, then system is neutral stable. In fourth case, the behavior of the flow is depend on magnitude of the disturbance. If magnitude of the disturbance is larger, then system is unstable, and if magnitude is small, then system is stable. In 1883, Reynolds performed an experiment. He injected a dye on pipe flow and observed the flow behavior and found that the flow is laminar for small velocity and the flow is transitional for intermediate velocity, and flow is turbulent for large velocity. Procedure of linear stability analysis. There are various ways to examine the stability of the flow. We are using linear stability analysis, in which we find instability point. After that point, the flow is unstable. For this, first we consider basic flow and apply infinitesimal disturbance into basic flow, which is in periodic form and given by equation number 1. Then substitute this in governing equation and dropping non-linear terms, we get linear disturbance equation of the form Ax equal to Cbx, where C is eigenvalue of the system. The behavior of the flow depends on the sign of Ci. If Ci is less than 0, then flow is stable. If Ci equal to 0, then flow is neutral stable. If Ci is greater than 0, then flow is unstable. Physical problem and application. In present problem, we consider fully developed flow in a vertical channel. Both walls of the channel are kept on constant but different temperature T1 and T2. That's why this problem is called differentially heated. A heat source is situated in the system and the magnetic field B is applied in perpendicular direction of the flow. Some basic application of mixed convective fluid with a magnetic field are fusion reactor, blanket laboratory experiment, electronic equipment, and many more. These are the governing equation of the present problem. To examine the linear stability analysis, first we consider basic flow. For basic flow, we assume the flow is steady, unidirectional, and fully developed flow. Using above three conditions, the governing equation reduces to equation number 8 and 9. After that, an infinitesimal disturbance imposed on basic flow. Using the normal mode analysis, the linear disturbance equation are given by equation number 10 to 14. These linear disturbance equation forms the generalized eigenvalue Ax equal to Cbx. To solve these linear disturbance equation, we require a high accurate numerical method. In present study, we are using a spectral collocation method that uses a Chebyshev polynomial as a base polynomial. Using spectral collocation method, we discretize the governing equation in y direction. The governing equation are collocated at Gauss-Lyabatov point. These Gauss-Lyabatov point are given by j equal to cos pi j by n, where n is order of base polynomial. The main concern is in spectral collocation method is to construct a differential operator, which is constructed in the form of djk. To obtain second order differential operator, we multiply d 2 times. After getting d and d squared, to solve these linear disturbance equation, we write equation in the form of these three equations in terms of d and d square, and these linear disturbance equation form the generalized eigenvalue problem of the Ax equal to Cb. To validate our code, we compare our obtained result with published result of Sankar et al. They examined stability of mixed convective flow in differentially heated channel with internal heat source, and table 1 indicates that the results are found to be good agreement. Results and discussion. The results are examined for electrically conducting fluid liquid mercury, that means PR equal to 0.02. The results are performed for various set of parameters. Some of them are presented here. First is basic flow results. The basic velocity profile contains point of inflection and backflow near the cold wall of the channel. Here it is observed that the point of inflection as well as backflow is smoothed out on increasing the strength of magnetic field. For example, from figure 2a, for q equal to 5 and gr by r equal to 100, the velocity profile free from point of inflection as well as backflow, when h equal to 14.6, after that value of h, we get a smooth velocity profile. Figure 2b demonstrates that on enhancement in thermal buoyancy, forces due to gr by ra also invites point of inflection as well as backflow in the velocity profile. In figure 3, we examine the effect of heat source parameter on basic velocity and basic temperature. Here it is observed that the velocity profile contains point of inflection as well as backflow on increasing the strength of heat source parameter. The thermal waves increases on increasing the strength of heat source parameter, that that causes the point of inflection as well as backflow. in the velocity profile. We know that the temperature is free from HA, but it depends on heat source parameter, and temperature increases on increasing the strength of heat source parameter. For example, from figure 3b, we see for Q equal to 0, we get a straight line for temperature, and on increasing the value of Q, we get parabolic profile for temperature. In concluding, we can say HA stabilize the flow, whereas Q destabilize it. Here it will confirm through linear stability analysis. Before linear stability analysis, we check the least stable mode of instability in terms of critical parameter is 2-dimensional or 3-dimensional. Several numerical tests are performed and found that the least stable mode of instability is 2-dimensional. That means beta equal to 0. From table 2, we can say the least stable mode of instability in terms of critical parameter GR by RE is obtained at beta equal to 0 for different value of RE. The instability, to examine the effect of heat source parameter and magnetic field, the instability boundaries are plotted in figure 4 and 5 for different value of HA and Q. The instability boundary shows that the critical value of GR by RE decreases on increasing the strength of heat source parameter. The thermal waves increases on increasing the strength of heat source parameter, which are responsible to create instability in the flow. That means Q destabilize the flow. Figure 5 shows that the critical value of GR by RE increases on increasing the strength of magnetic field. That means linear stability criteria increases on increasing the strength of a magnetic field. That means HA stabilize the flow. To get better picture, growth rate profile with respect to wave number is also plotted in figure 6. The positive value of growth rate represents the destabilizing behavior of growth disturbance, whereas the negative value of growth rate indicates the stabilizing characteristic of the disturbance. Both figure 6a and b shows the positive and negative characteristic of the growth rate, which indicates that the flow has an instability point in the flow. The main conclusion made in this study are the point of inflection and backflow are appeared or disappeared in the basic flow on increasing the strength of heat source or magnetic field. From linear stability analysis results, we can conclude the stability of the flow increases on increasing the strength of magnetic field, whereas the stability decreases on increasing the strength of heat source parameter. Growth rate profile also reports that HA stabilize the basic flow and Q destabilize. These are some references. Thank you.
Thank you very much.
Yes, sir.
Yeah. So, Nidhi Singh, right?
Yes, sir.
Yeah. In the conclusion, you have written like point of inflection. It is inflection
Yes,
or
sir.
inflection? I think it is typo error.
Inflection, sir.
Huh?
Inflection, sir.
Yeah.
Inflection.
Typo error is there. Because it will carry different meaning.
Yes, sir. Yes, sir. Sorry.
So have you developed the code or you have used some commercial software?
Sir, I developed the code in MATLAB.
Okay, very good. Okay. So suppose I want to apply the wettability in the vertical channel. Will it give other effect than other thermal factors?
So please repeat the question.
Suppose I want to apply the wettability in the vertical channel. Will it give any effect rather than thermal factors? Like thermal factors, buoyant force is generated and then it is moving up like that, right?
Sir, yes, sir. Sir, actually, the flow is generated by buoyancy force and magnetic field, and matlab, flow is mainly generated by buoyancy force and magnetic field.
Okay. Okay. Anyway, so suppose
Yes.
if I want to couple these two phenomena like magnetic field and electric field, is it possible to reduce the backflow by coupling?
Electric field. Sir, sir, magnetic field will reduce point of inflection, sir. Smooth out point of inflection and as well as backflow. Magnetic, yes, sir.
Okay. Okay. Are there any questions from audience? Shantanu?
Audience can ask questions if there are any.
Yeah.
Else we'll move to the next.
Yeah. Please start the next presentation. I think it is by Dr. K. Srinivasan, right?
Yes, sir.
Yes, sir. Welcome, sir. I'm available. Good day to everybody. I am K. Srinivasan, working as a scientist in Combat Vehicles Research and Development Establishment, CVRD. CVRD is one of the constant laboratories of Defense Research and Development Organization, DRDO, under Ministry of Defense. I sincerely thank the reviewers for reviewing and accepting our manuscript, and also I thank the organizers for giving me an opportunity to present the work carried out on optimal shape design of circular to square transition duct using CFD. The broad outline of the presentation will be introduction, problem definition, followed by design methodology, response surface optimization, and finally conclusions. Introduction. Transition duct refers to a class of ducts wherein the cross-sectional shape of the internal flow configuration changes along the flow direction. The present work considers circular to square transition duct, where the shape of the cross-section at the inlet will be circular and shape of the cross-section at the outlet will be square. Transition ducts are ubiquitously present in applications ranging from ventilation systems, aircraft propulsion systems, wind tunnels, and exhaust systems. More specifically, in an internal combustion engine system, it is used as an inlet duct to a turbocharger unit. The turbocharger performance depends on the flow at the inlet and is expected to have a minimum flow distortion and maximum pressure. Accordingly, the objective of the present study is to develop a systematic methodology to optimally design a diverging circular to square transition duct using CFD and optimization. Problem definition. As shown in the previous view graph, the present study considers a duct which is circular at the inlet and square at the outlet. Such a transition from circle to square can be represented conveniently by lamé curve x by a whole power p plus y by a whole power p is equal to 1. The figure shows the shape of the cross section for different values of p. Obviously, p equal to represent a circle, and as the value of p increases from 2 to a higher number, the shape undergoes transition from circle to near square. In the present study, the value of p is restricted to 10, which represents a square with rounded corners. As suppose this is satisfactory. Transition from circle to square along the streamwise direction implies the axial variation of the exponent p from 2 at the inlet to represent a circle to 10 at the outlet to represent a square with rounded corners. Literature shows that the performance of transition duct is affected by the axial variation of p. Now the challenge before us is how to vary the p. That is, how to vary the transition from circle to square along the duct axis. Intuitively, we may say p can increase monotonicity from 2 to 10 to have a flow-friendly geometry, and this will yield a continuously increasing curve along the length, which starts with p equal to 2 and ends with p 10 along the duct axis. There exists an acceleration of p which can generate a transition duct with reduced total pressure losses. So Bezier curve is preferred in the present study for curve definition, so that a curve shape may be controlled in a predictable way by changing only few parameters. This present view graph briefly describes what a Bezier curve is. Proposed 1960s for intuitive shape design, Bezier curves are characterized by a set of control points P0, P1, P2, P3 are control points. The Bezier curve passes the first control point and the last control points and is tangent to the control polygon at endpoints. P0, P1, P2, P3 forms an open control polygon, and the Bezier curve mimics the control polygon. Different shapes are obtained by moving the control points. For example, if we keep P0, P3 are fixed control points, just by moving the P1 and P2 to any location, we can produce different shape of the Bezier curve. This is the equation of the Bezier curve. This equation is similar to center of mass of a set of point masses equation. Now the challenge before us is how to vary the P from 2 to 10 along the duct axis. The P variation curve is represented by a quadratic Bezier in the present study with 3 control points, of which 2 are fixed to mark the sections near inlet and outlet. One control point is movable to derive different geometries that vary with exponent P along the axis. By moving the control point, different Bezier curves can be obtained which corresponds to different transition geometry. Description of geometry. Transition considered in the study has a circular inlet with 25.4 mm diameter, a square outlet of the side 38.1 mm, and the axial of the duct is 100 mm. In the present study, a diverging duct is selected in order to demonstrate that the proposed method is generic. It is not restricted to constant cross-section area or converging and diverging. It can handle anything. The exponent of the Lamé curve, that is the P, in our present study, at the inlet and outlet are constrained to 2 and 10 to represent circle and square outlet respectively. For further analysis, the dimensions of axial length of transition duct as well as the exponent of the Lamé curve. Exponent is P, which varies from 2 to 10, or normalized between -1 and +1. Design methodology. Present study uses DOE technique to select different initial geometries to initiate the optimization process. The selected initial geometries are numerically simulated using CFD to obtain total pressure loss. Based on the results of CFD simulation, a quadratic response surface is built between the pressure loss coefficient and the location of the Bezier control point. Optimization is then performed on the response surface to find out optimal location of the Bezier curve control point. That in turn will produce a geometry with reduced total pressure losses. Design of experiment. 3-level central composite design method is used to select initial geometries. The span of the duct between 5 mm and 95 mm are normalized as between -1 and +1. -1 correspond to 5 mm, 0 correspond to 50 mm, and +1 correspond to 95 mm respectively. Similarly, the Lamé curve exponent P, which varies from 2 to 10, again normalized between -1 and +1. -1 corresponds to 2, 0 corresponds to 6, and +1 corresponds to 10 respectively. So the first figure, a top figure, shows the location of the control point of the initial geometries in normalized coordinates. Say for example, CP let us take. It is a normalized coordinate located at -1, +1, which corresponds to 5 mm and the Lamé exponent of 10. So such a control point will produce a Bezier curve like this. This Bezier curve represents the variation of P along the duct axis. So at the inlet it has to be circular, so it starts at 2. At the outlet, after 100 mm, it should have a square cross section which corresponds to the Lamé curve exponent of P is equal to 10. In between, this is the way cross section varies. So these are some, to get a feel, we have put some isometric view of the some few geometries 1, 2 and 8. Total there are 9 geometries. We have put 1, 2 and 8 to get a feel how a transition duct will look like. Optimization problem. Now we will formally formulate the optimization problem. Here a definition of pressure loss coefficient K is made as the ratio of total pressure drop across the transition duct to the inlet dynamic pressure. A design optimization problem is now posed as minimization of the pressure loss coefficient K. Now we want to minimize K. How? What are design variables? Design variables are location of the control point of the Bezier curve. So by doing variety of CFD simulations of the initial selected geometry, a response surface is built And the optimization of this response surface is carried out using constrained multivariable optimization algorithm. Response surface optimization. Response surface is constructed based on the results of COD simulation to estimate linear, interaction and quadratic effects. This is the pressure loss coefficient, which is a function of the control point of the Bezier curve. K is the pressure loss coefficient and A is the coefficient of the quadratic regression model, and x1 is the distance from transition duct inlet, and x2 is exponent of the superellipse equation. So we saw in previous view graph there were 9 geometries. So these are the locations of the control points of the 9 geometries, and if we make a transition duct for geometry 1, 2, 3, 4 up to 9, that gives a pressure loss coefficient like this. So it shows significant variation. The significant variation in pressure loss coefficient validates assertion that the axial variation of the exponent of the superellipse equation does really affect the performance of transition duct, because the way we vary the P along the duct axis really matters. And this is the response surface obtained based on the CFD simulation. Now we do optimization of the response surface using any multivariable constraint optimization algorithm, and such a optimization yields the optimal location control point as 0.9999 and minus 0.99, which approximated as 1, minus 1 in normalized coordinates. If this is in normalized coordinates, if we translate to our general coordinates and reproduce the geometry, this is the optimal transition duct, and again it is circular the inlet and square the outlet, which corresponds to 2 and 10, and this is the way we should vary the cross section duct length. Conclusions. The present study, a systematic methodology for the optimal shape design of circular to square transition duct using CFD is developed. The axial variation of the exponent of the Lamé curve defines the shape of duct cross section and is represented using Bezier curve with its control point as the optimization design variable. The design optimization problem is solved by constructing a meta model between pressure loss coefficient and the Bezier control point using DOE related geometries. The proposed method determined the optimal variation of the Lamé curve exponent so that the resulting circular to square transition duct has reduced total pressure losses. Focus of the present work is not on the optimal solution itself, but on the process of achieving the optimal solution. Thank you for patient listening. Thank you.
Thank you. Hello.
Hello, sir. So can you hear me, sir? I'm Srinivasan. Yes, sir. Can you hear me, sir?
Yeah. We can have two to three questions from audience. Shantanu, please allow them.
Yes, audience, please ask questions if you have any.
Okay, so if there are no questions, I will ask one question. Like in your case, standard K epsilon turbulence model was used. So is it is there any specific reason of using that?
No. Actually, sir, our intention was to develop a systematic design methodology for a transition duct. So in that, to demonstrate this method, we just took a case where standard K epsilon is used. It's not that we should not use other models. It could have been tried, but here we demonstrate the methodology, not on very specific on the turbulence model. The methodology will still work even if you replace the standard K epsilon model with any other turbulence model also, sir. So depending upon the case, depending on the flow condition, if we feel that K epsilon model is not adequate, it can be replaced with some other method. Still, the methodology will still work. Yes, sir. That's the point we want to convey, sir.
Okay, if the transition is from circle to square, say in your case, so how you have chosen the mesh size of the duct? Means so that it will be mesh independent.
Again, sir, we took a mesh with a limited computational power, but we checked the 2-3 mesh sizes. We have not shown due to paucity of time, but the results were not significantly varying, sir.
Okay. No, my question was, sorry, my
Ah.
question was different. I was trying to know from you, like, what should be the correct methodology of choosing the mesh in such cases where the cross section is varying gradually in the axial direction, say. That was my
No,
question.
actually, actually, sir, we use the ANSYS Fluent software for simulating the case, and then we use the default ICMCFD meshing, and we checked after meshing, we check the mesh quality, the orthogonal quality, and if it is within the limit, then we proceed with the mesh, sir.
Okay, means
like
you have taken say number of elements, you keep increasing the elements, and finally you arrive at a optimum mesh, right?
Sir, exactly, sir. Yes, sir. Yes, sir.
Okay, thank you, Dr. Srinivasan. Thank you for your presentation. Now we will move to next presentation by Ravi Bala Patil. If there are no questions from anybody. Okay, Shantanu, you may run the presentation by Ravi Bala Patil. Hello, Shantanu, can you hear me?
Hello. Yes, sir.
Yeah, you run the presentation.
Okay, sir. I think, sir, there is some problem with the sound of the presentation. I'll reshare the presentation. Excuse me, sir.
Yeah,
Hello?
I can hear you. Please go ahead.
Sir, there is a problem with the video. The audio of the recorded video is very low.
So what we can do? You just ask to.
We can request Raviwala to resubmit the video for tomorrow's presentation.
You verify whether Ravi Bala is here, then we can make a request to him.
Hello, sir.
Hello.
Yes, sir. I am here. Yes, sir. I can send you tomorrow once again. No problem.
Yeah. That time you can, I think, possibly schedule your presentation.
Yes, sir. That would be better.
I think Shantanu, you help him to reschedule his presentation, right?
Sure, sir.
Okay.
Thank you, sir. Okay.
Thank you. If there are any, I think all presentations are over. I think.
Yes, sir. All are over. Thank you for your valuable time, sir.
Thank you very much, Shantanu.
Okay, thank you, sir.
Yeah, I can log out then now.
Yes, sir.
Thank you very much.
Thank you, sir.
Sir. Hello.
Yes, sir.
Sir, can you tell me the timing at which I can view the presentation? I will send you the video. No problem.
Okay, we'll let you know the timing within 5 or 10 minutes. Just give us 5-10 minutes and we'll let you know.
Okay.
So Shantanu, I shall be here or I can log out?
Yes, sir, you can log out, sir.
Yeah. Thank you very much.
Thank you, sir. Thank you, sir. Hello, Raviwala.
Hello, sir.
Can you present today online from
Online.
your side?
Yes, no problem. But shall I prepare the video? Yes or no?
No, you can share your video and present it online mode only.
Okay.
At around 5:30.
5:30.
Yeah.
Evening. Okay. Sir, tomorrow morning, I will send the video. If it is operating properly, then you can play. Otherwise, I will give the presentation directly. No problem.
Can you give the presentation today?
Today, no, tomorrow I will give, sir.
Okay.
Tomorrow, today at what timing?
Around 5:30.
5:30. Okay, no problem. I will give.
Okay, 5:30 at hall 2.
No, sir. Tomorrow or today? What you are asking? Tomorrow.
Today, 5:30 p.m.
5:30 p.m. No, sir. Tomorrow I will give.
Okay, then tomorrow you have to give it around 3:30 p.m.
Okay, no problem.
Okay. हाँ बोल.
Tu es trop grand pour comprendre des choses aussi petites.
Hello? Hello? Hello?
हेलो
हाँ सर में
व्हाट मैम
रवि
Vous allez cliquer à l'instant.
Tu es trop grand pour comprendre des choses aussi petites.
हेलो 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 हेलो
Yes, Sam.
सर रवि वाला बात कर रही हूँ मैं अभी मेरा प्रेजेंटेशन था ना वो हुआ नहीं
Okay, please tell. This is Dr.
sir told me that they will allow me that give the presentation actual today or tomorrow. I told him tomorrow, but at 5:30 I can give the presentation, no problem. I want to give the message, convey the message to organizer.
So I request Professor Paragmani Kalita.
Yes, Professor Dalal. Yeah.
So this presentation, this 167, paper number 167, please note down. Okay. So at the end of your session,
yes.
Okay, she will give live presentation. So she will share the PPT and give the presentation. Is it okay?
Fine.
Is it okay?
Okay.
Yeah. Today I will give you, sir, at 5:30.
Okay, around 5:30 means this at the end of session 6B. Session 6B.
Yeah.
Okay.
Yeah.
So please be present. Okay. Thank you, Professor Paragmani. Thank you, ma'am.
Yeah. You're welcome.
Please, Bharata, go outside.
You can start now.
Presentation
good. Look like
Good afternoon, everyone. The next session on computational fluid and gas dynamics will be chaired by Professor Paragmani Kalita from Tejpur University. Over to you, Professor Kalita.
Okay. Thank you, organizers. Very welcome to all the participants and the audience. So today's session we have. As per the original schedule, we had 6 papers, but now one more paper has been added to that. So these 6 papers and sequence are paper number 181, 188, 192, 194, 33, and 196.
Correct, sir.
So the first paper is by Anand Bharadwaj S. and Nikhil Das. It's on numerical investigation of the effects of varying membrane permeability on concentration polarization in membrane separation. So I request the presenters to be ready with the. I hope that their pre-recorded presentation will be played first, and then it will followed. It will be followed by the interaction session.
Exactly, sir.
Okay, so please start the presentation.
Okay, sir.
Hello everyone and welcome to this talk titled Numerical Investigation of the Effects of Varying Membrane Permeability on Concentration Polarization in Membrane Separation. This work is done by Anand Bharadwaj, which is myself, and my collaborator Nikhil Das. The outline of my presentation includes an introduction to membrane separation process, after which I'll talk about the numerical model that we have for the process. Subsequently, I'll talk about the computational details, the results, and the conclusions. Membrane separation is essentially a process that is used to separate certain solutes from the parent solution. Now, this mechanism can be pressure driven or it can be driven by gradients of concentration, electric potential, etc. The common membrane separation processes that we are aware of are reverse osmosis, ultrafiltration, dialysis, etc. And these are applied to various fields such as water treatment, food processing, pharmaceutical industry, and so on. When we talk about membrane separation process, an associated phenomenon is called the concentration polarization. Now, whenever membrane separation happens, it essentially leads to a buildup of the solute at the semi-permeable membrane. Now, this buildup is something that reduces the overall permeation of the flux, and therefore it has certain disadvantages associated with it, which is essentially to lower the process efficiency. It reduces the life of the semi-permeable membrane and also increases the operating cost. Now, let me move on to the model for the membrane separation process that we have. I would like to first mention that we are talking about a single solute system, which means that there is one solute and one solvent. So for the solvent, which is the fluid, the Navier-Stokes equations are solved. The first equation, dou ui by dou xi, is the continuity equation, and the second equation is the momentum equation. Now, this, of course, is represented in the tensor notation. For the solute, we have the convection diffusion equation, where C stands for the concentration of the solute and capital D stands for the diffusivity of the solute. Now, it's not just enough to have these two equations solved. It's also important to have a coupling between the two entities, which is the solvent and the solute. And this coupling is achieved in two ways. So the first one is the solvent, the effect of the solvent on the solute, which is directly seen in the equation for the solute, the convective diffusion equation, where the second term is essentially the convective term, where uj is the velocity of the solvent. So the solute locally moves at the speed of the solvent. This effect of the solute on the solvent is captured through the permeate velocity, which is VW equals A into delta P minus kappa CW. Here A is the membrane permeability of the semi-permeable membrane. Delta P is the transmembrane pressure, which is a very important aspect in processes such as reverse osmosis. So if we don't apply a sufficiently high transmembrane pressure, then we won't be able to achieve reverse osmosis and it would lead to osmosis. So if you look at this expression, delta P is actually what results in a positive VW. So delta P has to be greater than kappa CW in order to get a positive value for VW. And that is a case of reverse osmosis. If delta P was set to 0, then VW would be minus A kappa CW, which is a case of osmosis rather than reverse osmosis. Right, so kappa and CW contribute to the osmotic part of the process. Now coming to the solver attributes, the solver is essentially a finite volume solver for structured and staggered meshes. The spatial and the temporal derivatives are discretized using a second order discretization. The algorithm for solving the Navier-Stokes is the projection method. And the linear solver is the line by line TDMA approach. And finally, as already mentioned before, the equation for the solute is the convection diffusion equation. So this solver has been validated against some standard benchmark cases in literature. Here we present the V velocity profile compared with the values presented by Gia et al. For a Reynolds number of 1000 in a lid-driven cavity problem. And we see that there is a pretty good match with the results. Now here is how the domain looks. We have an inflow on the left and an outflow on the right, and the top and the bottom walls are essentially the semi-permeable membrane. The inflow carries in a parabolic velocity profile, which is the Poisson flow profile, and on the right, the outflow is essentially a convective boundary condition, which allows the flow to just pass through. At the top and the bottom, we have the semi-permeable wall, which essentially allows a permeate velocity given by this expression here. That's for the solvent. And as far as the solute is concerned, the convective velocity is set to 0 because the solute is not allowed to penetrate across the membrane. Now, these are some of the parameters that we've chosen from the work of Ali et al. And we've gone by that. So the Reynolds number is set to 400. The incoming concentration of the solute is 4 kg per meter cube. The transmembrane pressure is 1.25 megapascal. And the other membrane-related attributes, that is membrane permeability, and then the diffusivity of the solute, osmotic coefficient, etc., are mentioned in the table. Now, before I present the results, I would like to mention that we're looking at the disruption of the concentration polarization layer by modeling it as an increase in the membrane permeability. So we're not looking at specific mechanisms, but we're looking at, let's say we have a mechanism that can disrupt the concentration polarization layer, then what location along the membrane would be a good place to mount that mechanism? That's what we're trying to investigate through the study. So for that, we have two groups of simulations, group A and B. So let me first talk about group A. In group A, we're looking at a step variation in the membrane permeability. So as you see, A1 is a case of constant permeability. A2 has a step increase at the first 1/3 of the membrane. A3 shows a step increase in the second 1/3 of the membrane, and A4 has a step increase in the third 1/3 of the membrane. So this is also seen in the plots clearly on the right hand side. Now the second group of simulations, which is B, in this we look at the linear variation rather than a step variation. So just to be clear, the baseline case for A1 and B1 are essentially the same, which is a case of constant permeability. So so B2 here shows a linear variation of membrane permeability from 11A to A, and that's a linear decrease in the permeability. B3 we see a linearly increasing permeability close to the middle of the membrane, and then again it drops back to A. And in B4 we see a linearly increasing permeability from A to 11A. The simulation was the study was preceded by a grid independent study, and we see that with refinement there seems to be a grid convergence seen in the solution, and this of course was done on the baseline case. Now moving on to the results of the group A simulations, we see that the permeate velocity or the V velocity contours show an increase in A2, A3 and A4 in the regions where the permeability has been enhanced, which is sort of expected as per the model. Now, when we look at the concentration contours, we see that in comparison to A1 on the top left side, we see that the concentration boundary layer has dropped in thickness in A2, A3 and A4. And also it's important to note that there is this red band, which means that there is a high concentration accumulation happening at the wall in cases A2 to A4. Now, here we have the concentration profiles at 3 streamwise locations along the channel. X1 is closer to the left boundary, X2 is at the middle of the channel, and X3 is closer to the right boundary. And we see that in all these cases, the concentration boundary layer, as we saw in the previous slide, has become thinner in the cases of A2 to A4. And the accumulation of the solute at the wall has increased. If you look at A2 to A4, in almost all 3 cases, we see that the solute concentration is higher at the wall. But what's important to note is in case of A2, which is the green line, we see that the concentration at the wall is quite consistently high at all 3 streamwise locations. Now, we look at the permeate flux and we see that in comparison to A1, surely A2, A3 and A4 show an enhanced permeate flux. And A2 shows the highest permeate flux in comparison to A3 and A4. Now, let's look at the group B set of simulations. Here again, we see that there is an increase in the permeate velocity or the V velocity However, it's important to note that in case B2, we see that the region of high velocity is sort of longer in comparison to B3 and B4. And a similar observation in terms of concentration contours is seen here, where B2 to B4 show a thinner concentration boundary layer. Now, coming here, we see that the concentration profiles show a similar trend as in the Group A simulations, where the green line B2 shows a higher concentration at the wall in comparison to B1, and of course, in across all the three stream-wise locations. This is also reflected in the permeate flux. As we can see, B2 to B4 do show an enhancement in the permeate flux with respect to B1. However, B2 shows the highest permeation in flux. So just to conclude, increase in membrane permeability increases the permeate flux as expected from the model. The location of the permeability enhancement changes overall permeation. And in both the groups of simulations, we see that the permeate flux is highest when it is enhanced at the beginning. And in group A, the flux enhancement is higher when the mechanism is mounted at the end, and in group B, it's higher when it's mounted at the middle. So that's about it. Thank you so much for your attention.
Okay, thank you, Mr. Anand, for the nice presentation. Now, the session is open for discussion. Is any esteemed audience, if you want to ask anything? Okay, if there are no questions, I just wanted to have a few discussion. Am I audible?
Yes. Yeah, I can hear you, sir.
Okay, Mr. Anand, you have used the second order method for time integration also, right?
Yes, sir. Yeah, that's right.
Which one is it? Is it Crank-Nicholson or Adam-Bashford, or is it Ranga-Gupta method?
So for the convective term, it's Adams-Bashford, and for the viscous term, it's Crank-Nicholson.
Okay. And you also in the boundary condition for that membrane, near the membrane.
Right.
So you have used that term delta P. How is that? Does the delta P evolve with the solution itself, or we have to give it as a direct boundary condition there?
Yeah, so delta P is normally a fixed quantity. So like, let's say if you take reverse osmosis, that transmembrane pressure is something that we apply in order to drive the process. And normally it's set to a value that we need. So in the simulation also, we've just fixed it at a constant value of 1.25 megapascal.
Okay, is there any basis for that, or any reference or any rationale behind that?
Basically, that comes from how the process is actually done in practice. So whenever we have to separate salts from water, we exert a specific stipulated transmembrane pressure.
Yes.
That's the same logic that we've applied in the simulation as well. We've just taken those the value of the TMP, that is the transmembrane pressure, and we've kept that as a constant value for the simulation.
Okay, so there are industrial standards available for that, or something like this, or it's based on experience.
No. Yes, there are industrial standards depending on the process, which process it is. Like if it's reverse osmosis, there would be one TMP. If it's dialysis, there would be some other TMP. So what we've chosen here is from a reference paper which deals with reverse osmosis.
Okay. And my last question: the permeate flux, as you said, for the step permeability method, that scheme A. Okay, so what is happening with A1? It is the least. And then with A3, because when you increase the permeability in the beginning, as you have shown with your observations that permit flux increases. But in the table, although A1, A2, A2, A3, A4 all are higher than A1, but the trend, if you see, A3 was, for A3 it is less than A2, but it is also less than A4. Actually, A4 was that the permeate flux, as I could observe, was for A4 was slightly higher than that for A3. But that trend was not seen with the B scheme.
Yes.
Is there any?
Yeah. So basically, what you're saying is right, sir. So the trend that B2 and A2 are the highest is common in both the groups of simulations.
Yes.
But when it comes to A3 and A4, A3 is greater than A4, but B4 is greater than B3. So we're not exactly sure why that is the case. We've just reported what we found as of now. But the reasoning has not been done yet.
Okay, okay. Anyway, thank you for the nice presentation and wish you all the best. Now we will start the next presentation. It is by Snehasis Chaudhary and his team on assessment of various RANS-based turbulence models for predicting near wall flow and heat transfer quantities for a turbulent slot jet impingement. So we can please start the presentation now.
Hello, this is Snehasis Chaudhary. I am from IIT Shibpur and now I am going to present our work on assessment of various RANS-based turbulence model for predicting of near wall flow and heat transfer quantities for a turbulent slot jet impingement. So at first we should know that what is a jet impingement. It is a flow structure in which a stream of cold air strikes on a hot flat plate in order to control its temperature. Here in our current study, we have considered a confined slot jet configuration, in which the whole flow structure is confined between two parallel plates, named in the figure as the impingement plate and the confinement plate. This kind of flow structure is well known for its high heat transfer and mass transfer capabilities. So applications of this kind of flow structure can be seen in various cooling applications. We can find its applications in cooling of powered electronic components, in turbine cooling, turbine blade cooling, and there are various other applications. So scientists are studying this kind of flow structure and how we can enhance the capabilities of the heat transfer of this kind of flow. There are various experimental studies conducted on this topic and some numerical studies are also conducted, but very few of them focused in the near wall characteristics of this kind of flow. That's why in our current work we have studied the near wall turbulence with various available turbulent models. So the governing equations which are solved in this problem are the Reynolds averaged Navier-Stokes equation, which you can see that the continuity equation, momentum equation, and the energy equation. The equations are solved using these three commonly used turbulence models, that is the standard K epsilon model, standard K omega model, and SST K omega model. With standard K epsilon model, we have used the enhanced wall treatment for near wall modeling of the flow. So simulations are done considering the flow to be steady, incompressible, and two-dimensional. We have solved the flow only for the half domain, as we have seen that the whole flow structure is symmetric about the central axis of jet. So to reduce the computational cost, we have considered a half domain. And some previous papers have also confirmed that the using full domain and half domain are giving same results. So we have considered a half domain for our study. We have imposed the boundary conditions as the velocity inlet at the jet inlet, symmetry about the axis of symmetry, and wall at the confinement and impingement plate. Though in the impingement plate we have considered a isothermal wall, and in the confinement plate we have considered a adiabatic wall. At the outlet we have considered a fully developed outflow condition. This is a standard grid distribution we have considered for the simulation. Here starts our results and discussion section. Firstly, we have conducted a grid independent study to ensure that whatever results we have found are independent of the grid. So for that we have considered 4 different grid distributions for each turbulence model, and these are the distributions for k omega models, and these are the distributions considered for k epsilon model. We have compared the streamer's velocity profile at location of 9 times the slot width for a plate spacing of twice the slot width, and for all the models the velocity profiles for using all the grids match well, so you can say all the results are independent of the grid. So for ease of our calculations we have considered a moderate grid density, that is we have considered this grid distribution of 241 cross 101 for k omega model and 241 cross 61 for k epsilon model for our further calculations. Now to check the capabilities of the used turbulence model to predict the near wall turbulence, we have compared the near wall turbulent velocity profiles with experimental results as well as the curves of law of wall, that is these 3 equations, and we have shown here for 4 different x locations. As you can see that for the locations near the stagnation region there is a deviation of experimental results and numerical predictions, but as we go to the downstream the deviation reduces. This may be due to that the turbulence models are not capable of predicting the highly curved flow near the stagnation region. We have also compared the skin friction coefficient distributions along the impingement plate with experimental results available. We can see that the predictions of all the turbulence model are quite high compared to the experimental data. This may be due to the high prediction of the velocity gradient in off stagnation region. In that region the flow accelerates from a zero velocity, so the turbulence model may have over predicted the velocity gradient in that region, and as the CF is directly proportional with the velocity gradient, so we are seeing a over prediction of CF also. Now after comparing the fluid flow properties, we have also studied the heat transfer characteristics of this flow. You can see that the Nusselt number distribution over the flat plate are compared with experimental data. Here we have taken the plate spacing to be 4 and 9.2, and for comparison we have chosen the drop at the stagnation region, and you can see that the deviation of this drop is quite small for SST k omega model in comparison with the standard k epsilon model, which is quite large. This may be due to that k epsilon model uses a wall treatment to predict the near wall flow properties. And here you can see that the heat transfer coefficient distribution over the impingement plate are compared with experimental data. The plots are shown for the plate spacing 2 and 6. Here also same procedure of comparison are followed. The drop at the stagnation region are compared with the experimental drop. And here also you can see that the performance of SSTK omega model is good in comparison with the standard K epsilon and standard K omega models. And that's all with our results part. Now let's check what are the things we have found. So these are the points which you can infer from our study. Firstly, the near roll turbulent velocity profiles. The predictions match well with the experimental data, especially the standard K omega model have given a better performance compared to other models. But near the stagnation region, we see some deviation of numerical predictions with experimental data. That may be due to that in that region the flow is highly curved and the models which we have used is not capable of predicting that curvature. So we are seeing some deviation in that region. And for the CF distribution, the skin friction coefficient distribution, we have seen that all the models have overpredicted that. So that may be due to the overprediction of the velocity gradient in the off stagnation region, and so all the models have overpredicted that value, so we are seeing the deviation. Now coming to the heat transfer properties, we've seen that the performance of SSTK omega model is the best among all the models, and the standard K epsilon models doesn't perform well in that field. So that may be due to the use of enhanced wall treatment, which is not capable of predicting the heat transfer properly. So this is all we have found. These are some papers which we have referred in our study. That's all for now. Thank you.
Okay, Snehasis, thank you for the nice presentation. Now the session is open for discussion. Anyone present, if want to ask anything, please. I guess there is no question from the audience. If that is so, before Snehasis leaves this presentation, just I wanted to know, actually, in your governing equations, the energy equation, Snehasis, what is the parameter lambda on the right hand side of the equation?
Sir, can you please repeat?
In the energy equation.
Yes.
In the energy equation, you have shown your governing equations, right? So in the energy equation, what in the right hand side, on the right hand side of the equation, what is the parameter lambda? You are writing lambda upon Cp into del T upon del Xj. What is this parameter lambda?
Sir,
is it conductivity or thermal conductivity or diffusion?
Yeah, the conductivity of the fluid we are using. Actually, we are using here.
Okay, so lambda basically is the conductivity. Normally we use K, the symbol K for conductivity, but okay, perhaps you are not using because there will be confusion with the K epsilon term, then K. Okay, maybe that is the reason.
Yes.
Right?
Yes,
okay.
sir.
Okay. Then actually you have use the term. So like the turbulent kinetic energy is, say, like you have kept like 3/2 into, say, I, where I is the inlet turbulent intensity and Vj is the velocity at the nozzle exit.
Yes.
So has there been any study been carried out on the effect of turbulent kinetic energy as a function of this I and Vj, like say this function 3/2 I into Vj square whole square? So this term 3/2, is it empirical?
Yes, sir. Most probably it is empirical, but we have gone through some papers on this impinging jet only. So there, most of them are considered kind of. So we just referred to them only.
Okay.
But most probably it is empirical.
Then my actually last question was. Yeah, okay. So today
Professor Kalita, your voice is breaking. Hello? Hello? Hello, Snehasish? Hello?
okay, sorry, actually the connection got off.
Okay, sir.
Okay, Snehasis, you are there?
Hello, Snehasis? I think his connection is also.
Okay. Then we shall go to the next presentation.
Okay,
it's
sir.
paper number 192. It's by Vipul Kumar Gupta, Pradeep Kumar Jha, and Pramod Kumar Jain. The title of the paper is Effect of Submerged Entry Nozzle Port Angle on Fluid Flow and Solidification of Continuous Casting Bloom. So please, I request the volunteers to please start the presentation slides.
My name is Vipul Kumar Gupta. I am research scholar in the Department of Mechanical and Industrial Engineering, IIT Roorkee. My presentation topic is Effect of Submerged Entry Nozzle Port Angle on Fluid Flow and Solidification of Continuous Casting Bloom. Professor P.K. Jha and Professor P.K. Jain are my co-authors on this paper. Next is content. So these are the contents. So first I will go through the introduction, basic process of continuous casting, and then mathematical modeling, then solution procedure of simulation, and resultant discussion, and then conclusion. Next is introduction. The continuous casting machine has mainly 4 components. One is tundis, second is mold, third is water spray, and fourth is torch cutter. Tundis is a refractory vessel in which molten metal is stored. From tundis, molten metal comes to the mold through the submerged entry nozzle. Mold is place where primary cooling takes place using circulation of water repellent in the mold, and heat transfer occurs. And after solidify up to certain thickness, it goes down, and then spray cooling or secondary cooling take place using the water spray. After fully solidification, it cut in different length using the torch cutter. Here, the submerged entry nozzle plays significant role in determining the quality of the casting, because its shapes and size or geometry directly affect the flow field in the mold of molten metal. So it is important component to determine the quality of the casting. Next is advantage of the continuous casting. Because all steps occur simultaneously, so there is no need to make separate pattern and separate mold. So that's why the productivity is very high, and we can control the cooling. So we can control the mass flow rate of water in the mold as well as in water spray. So we can control the cooling, and that's why we can alter the mechanical properties. Because there is no wastage of material, so yield is very high, and we can obtain continuous slab and billet or bloom. Next is application of continuous casting. So continuous casting is used to manufacture the slab, billet, and bloom. And these are the primary component or primary product which are used to further for making the or manufacturing the component by giving the shape using the forming processes. Next is the mathematical modeling. So this is a geometry of bloom which I have taken for my study. So the length of this face or wide face is 0.42, and this face is named as narrow face, so its length is 0.32. The total length of the bloom is 1.25 meter. The depth of the SEN or submerged entry nozzle is 300 mm, and the diameter is of SEN is 50 mm. So 3 different cases of guiding angle are taken, or they are named as SN1, SN2 and SN3. So SN1 has the minus 15 degree, which is downward angle. SN2 is minus 30 degree, and the SN3 is plus 15 degree angle, which is upward. So mold oscillation, because to simplify the analysis, the certain assumptions are taken. So one assumption is mold oscillation is neglected. So mold oscillation is not considered in the study. Mold powder or the slag is also not included. Its modeling is also not included in this study. Still surface shape is fixed. So total the top surface is fixed surface, and its fluctuation is not considered or is ignored in this study. These are the governing equation which are used to solve the partial differential equation, and one is this is a continuity equation, this is momentum, and the K epsilon realizable model is used here, and this is the energy equation. Beta is a liquid fraction, so if T less than T solid as temperature, then beta will be 0. If T equal to 1, if beta is greater than T liquidus, and beta is equal to T minus T solidus upon T liquidus minus T solidus if T is between the T solidus and T liquidus. And these are the other terms. Next is boundary condition. So UDF or user defined function is used, and the spray heat transfer coefficient, this is a zone. At the inlet, initial kinetic energy and dissipation rate is calculated using this equation. And these are the process parameters. Next is solution procedure. So academic research CF 19.2 used for solving the governing equation. Transfer, the temperature will be higher at this location. In case of SN2, the lowermost temperature or lowest temperature location shift further away from the top surface or meniscus. It is due to the higher guiding angle. In case of SN3, this lowest temperature in the primary cooling zone, location is near to the top surface. It is due to the upper guiding angle of SN3. In case of graph 2, which is on the narrow phase x equal to 0 plane, the temperature continuously decrease. There is a sudden change in temperature here. It is due to the change in zone or cooling zone. It goes from primary cooling zone to the secondary cooling zone. So there is a sudden change in temperature rise here. Next is a solidification thickness contour for each cases on y is equal to 0 plane and x equal to 0 plane along axial direction. So solidification thickness first increase from upper surface, then comes to 0 or almost negligible, and then again start increasing in each case. But it is this solidification thickness is 0. It is due to the higher superheat transfer, which due to the incoming jet is directly strike at this point at this location. So due to higher superheat transfer, the temperature and the solidification thickness comes to 0. In case of SN2, this location shift downward. It is due to the higher guiding angle, downward guiding angle. And in case of SN3, it is up due to upward guiding angle. The solidification thickness in upper zone or upper side is almost 0, close to the top surface. And in case of x equal to 0 plane, the solidification is start increasing continuously from top surface. Next is the solidification thickness graph along on y equal to 0 plane on white phase. So we can see that solidification thickness continuously increase from 0 to maximum 35 mm. So next conclusion. So the surface fluctuation decrease from increasing the port angle minus 15 degree to minus 30 degree, and highest fluctuation observed in case of SN3 plus 15 degree, which leads to more chances of slag entrapment and inclusion removal. In primary cooling zone, the temperature near meniscus is much higher in case of SN3 compared to other cases. Bloom is more prone to break out in case of SN2 because jet strike location on a white face is bound to be close to the mold end.
Okay, thank you, Bipul, for the nice presentation with industrial relevance. Now the session is open for discussion. Any question from the audience? Okay, in that case, just Bipul, are you able to hear me?
Yes, sir.
Okay, I wanted to know, is there any rationale behind choosing the K epsilon realizable model out of so many turbulence models? Is there any rationale? What's the rationale behind that? Did you investigate the different models and then choose this one?
Actually, sir, in like last previous publication, most of the authors use the K epsilon realizable model. So that's why I took. Actually, I didn't investigate. Specifically.
That's for especially for your kind of applications like melting and solidification of metals, flows of molten metals, isn't it?
Yes,
for this kind of.
Maybe as per my understanding, because in a K epsilon realizable model, the viscosity term is different as compared to standard K epsilon model. So due to that, there is some correlation between the solidification and viscosity. So that's why.
Okay. Because final concern is to get accurate results. That was only the concern. So, and what is the Reynolds number, range of Reynolds number that can be attained through this flow, in this kind of flow? Do you have any idea?
Sorry, sir, but I didn't investigate that. Also means Reynolds number.
Actually, why I'm asking is, is there any actually real evidence that the flow is turbulent there through this one? Because if you want to apply a turbulence model, or you want to use a turbulence model into your computation, we have to be sure that the flow is turbulent, because it's such a highly viscous flow taking place there. So, yes, sir. Is there any evidence that the flow is turbulent in your case?
Yeah, means in that after incoming jet when strikes in the mold zone, so the velocity is so much higher that so that means the turbulence flow will be there, and other temperature is also very high. So fluctuations and temperature values
Okay. So actually, if that is the case, okay, if we want to solve a turbulent flow problem, we should actually start with the Reynolds average Navier-Stokes equations, RANS equations. In that case, that governing equation should also contain the eddy viscosity terms. Perhaps your solver is using that because you are anyway using a commercial software package. But in your slides, I think the Navier-Stokes equation that you have shown, they don't contain those eddy viscosity terms. These are not the RANS equations, perhaps what you are showing. Please just check once again.
Yes, right, sir.
Right? Okay,
Right.
okay. Yeah. So that has to be looked into. And just one question of maybe practical, importance. Like you are getting some temperature profile based on the nozzle angles and different configurations that you are getting.
Yes.
Can you comment on that? Say effect of a given temperature profile. Suppose you have attained one kind of temperature profile during cooling. So what is its effect on the residual stress behavior of the end product?
So that will need further investigation, means how that final cooling take place. So this is the initial study when we just power the this molten metal comes from SCN. So we need to further investigate. Otherwise, we cannot comment about residual stress based on these profiles.
Yes, because this study will finally lead could be useful because this study finally has to be extended into those kind of things, like it will be quite helpful. And only thing is that accuracy part, whatever model we are using, first of all, what is the flow? If we are sure that it is laminar or turbulent, then if it is turbulent, which model will give the most satisfactory results? And then we should be also knowing we should be sure that we are using the correct governing equations and proper boundary conditions. Right. So leading all these will actually affect our accuracy and then the conclusions that we'll draw from this kind of work. Anyway, thank you and wish you all the best. Now,
thank you, sir.
Okay. So we have our fourth paper for this session. It's by Tilekar N, Atre M and Gandhi P, parametric investigation of liquid-cooled fractal-like heat sink. So may I request volunteers to please start the video presentation.
Hello everyone, my name is Nihal Tilekar and my paper topic is parametric investigation of liquid-cooled fractal-like heat sink. This topic is guided by Professor Milind Atre and Professor Prasanna Gandhi. Motivation of the present topic is fractal-like network. In simple words, fractal means repetition of self-similar pattern. If repetition of self-similar pattern is occurring infinite number of times, then it is called fractal network, like this animation. And if self-similar pattern is occurring finite number of times, then it is called fractal-like network. Here one channel is splitting into two channels and it is repeating finite number of times, hence this network is called fractal-like network. Here more formal definition is given. In pumping power perspective, fractal-like channels are least resistance path for fluid to flow. And in heat transfer perspective, average heat transfer coefficient increases with increase in number of generations because of sudden increase in local heat transfer coefficient after each bifurcation. Objectives are to develop and validate a 1D numerical model for the investigation of thermal and fluid characteristics of the fractal-like heat sink, to investigate the effect of number of generations and terminal channel diameter on the benefit to cost ratio for the same physical space and heat supplied for two cases, which are given water flow rate case and optimized water flow rate case. Here fluid comes from the inlet and flows radially outward like this. This one. Here fluid comes at the inlet plenum and then pass through this, then flows through this zeroth level channel and then subsequent channels, and this is a first level, then second level, and this is third level, which is a terminal level of the channel, and it is represented by mth level. So this K is number of channel, K is a channel level, M is a number of generation, then D, K is diameter at kth level, L is a length, and beta is a diameter scale ratio, which is the ratio of diameter at K plus 1th level to the diameter at kth level, and similarly length scale ratio is defined. Here beta and gamma are taken as a 0.7937 and 0.7071, which comes from minimum energy required for blood circulation in mammalian circulatory system from this West et al. Paper, and with known values of parameter represented in blue color, diameter and length at each level can be explicitly calculated from literature number 5. In literature, Payne's reported feasibility of fractal-like flow network where fully developed flow is assumed and analytical calculations are made to show the feasibility. So here, after each bifurcation, cross-sectional flow area is increases by 26%, convective surface area is increases by 12%, heat transfer coefficient is increases by 26%, and convective thermal resistance is decreases by 30%. Also, pressure drop is decreases by 11% after each bifurcation. In the present work, numerical code reported in this literature is used with major modifications because in this literature, even though working fluid is water and cross-section of the channel is rectangular, corresponding Nusselt number correlation used in this literature is not valid for water. So in the present work, circular cross-section is used because corresponding Nusselt number correlation is available, which is valid for water. Assumptions in the present model are: at steady state, heat supplied to the walls of the channel is equal to the heat absorbed by the water and heat loss to the surrounding is neglected. Flow rate is assumed to be equally divided after each bifurcation. Pressure loss at the inlet, outlet, and at each bifurcation is neglected, and constant heat flux boundary condition is assumed. Here, inlet water temperature is specified, inlet flow rate is specified, outlet pressure boundary condition is specified, and heat flux which is applied on the walls of the channel is specified. To this numerical model, geometric parameters and boundary conditions are given as an input. From geometric parameters, diameter and length of the channel are calculated. At each level, these are calculated. Then enthalpy is calculated at each node from increase in specific heat of water. Then fluid temperature and thermophysical properties are calculated. Then local coefficient of friction is calculated from this correlation, and then pressure distribution is calculated from frictional pressure drop. Then by using Nusselt number correlation, local heat transfer coefficient is calculated, and from Newton's law of cooling, wall temperature is calculated at each node. Then a temperature constraint is applied and maximum wall temperature is limited by this constraint. And after that, benefit to cost ratio is calculated, which is heat dissipated divided by pumping power. So this is for this algorithm is for given water flow rate case, and for optimized water flow rate case, this here flow rate is decreased till this wall temperature constraint is gets just valid. So this flow rate is optimized and this benefit to cost ratio is maximized. So this is the algorithm for optimized water flow rate case. For grid independent study, grid size is varied from 0.5 mm to 0.02 mm. Here pressure and wall temperature variation is less than 0.5% as grid size changes from 0.1 mm to 0.02 mm. Hence 0.1 mm grid size is selected. For validation, CFRE and local Nusselt number data is validated with numerical data available in literature, where maximum error in CFRE is 3.43% and in Nusselt number is 5.45%. So for fourth generation fractal like flow network, this axial pressure distribution is shown. So at each bifurcation, due to reinitiation of hydrodynamic boundary layer, this sudden change in pressure distribution, sudden change in slope of pressure distribution can be seen, and in wall temperature distribution also the sudden change in temperature can be seen due to reinitiation of thermal boundary layer. So this reinitiation of thermal boundary layer can be seen from this local Nusselt number and local heat transfer distributions, actual distributions. So in for this fourth generation case, pressure drop is 13.51 kPa and maximum wall temperature is 63 degrees centigrade. Here, effect of water flow rate and number of generations on the benefit to cost ratio is analyzed for given flow rate case. This is analytically derived expression of benefit to cost ratio, just to interpret the further results in a better way. This is plot of benefit to cost ratio versus flow rate, and on secondary y-axis maximum wall temperature is shown. These continuous lines represent benefit to cost ratio and dotted line represent maximum wall temperature. As flow rate increases, benefit to cost ratio decreases because this ratio is inversely proportional to the flow rate. Also, as flow rate increases, maximum wall temperature decreases because fluid temperature decreases as flow rate increases, and from Newton's law of cooling, wall temperature is also decreases. At particular flow rate, as number of generation increases, the term shown by green boxes, both the terms are actually decreases, but decrease in this summation term is more dominant than decrease in this numerator term. Hence, due to decrease of summation term, benefit to cost ratio increases as number of generation increases. Also, as number of generation increases at particular flow rate, maximum wall temperature decreases because average heat transfer coefficient increases. Here, all maximum wall temperature, in all cases, maximum wall temperature is less than wall temperature constraint. Hence, flow rate can be decreased so that maximum wall temperature constraint is just valid and benefit to cost ratio will get maximized. Here, effect of terminal channel diameter and number of generations on the benefit to cost ratio is analyzed for optimized water flow rate case where wall temperature constraint is just satisfied. This is a plot of benefit to cost ratio against terminal channel diameter, and corresponding optimized flow rate is shown on secondary y-axis. As the terminal channel diameter increases, in particular generation case, this benefit to cost ratio shows nonlinear behavior because of relative dominance of these two terms. So, in overall, benefit to cost ratio increases as number of generation increases. Here, effect of diameter and length scale ratios on the benefit to cost ratio is shown. This is analytically derived expression of benefit to cost ratio as a function of diameter and length scale ratios. From this plot of benefit to cost ratio, it can be seen that increase in length scale ratio has more advantage than diameter scale ratio to increase the benefit to cost ratio. So 1D numerical model is developed and validated for investigation of thermal and fluid characteristics of fractal like heat sink. Also, the effect of number of generation and terminal channel diameter is analyzed on the benefit to cost ratio. And thank you.
Thank you, Tilekar.
Thank you,
now
sir.
the session is open for question and discussion. Okay. Till if some of the audience come up with some question, till that time, I take the liberty to utilize this time. Lekar, you have done your analysis by ignoring the minor losses, isn't it?
Yes, yes. Only major losses, that is frictional losses, are considered.
Only major. Yes, yes. So frictional pressure drop only considered.
Yes.
So from that analysis, you see for a as you are increasing the number of generations,
Yes.
meeting the constraint on the wall maximum wall temperature, your benefit to cost ratio is increasing, right?
Yes. Yes.
Because your pumping power, because it's basically relatively like the relative benefit of how much heat transfer you get divided by how much pumping power you need to maintain
Yes.
that flow rate.
Yes.
Now, but if because since it's flow through very, I think it's micro channel, isn't it? The dimensions are of the channels are of the order of microns.
Yes, from
especially
200
in the
micron
lower
to 400 micron, they are varied.
Okay, so if we go on increasing our number of generations that way, as you can see, even if your temperature plot and Nusselt number, local Nusselt number plot, all these show sudden spike in at the locations wherever there is there are bifurcations, and you have rightly indicated that it is because of growth of fresh hydrodynamic boundary layer.
Yes.
This means all those points will correspond to locations where there is a sudden change in velocity, and we know that this can, especially in say small channel flows, this can play a significant role towards increasing the minor losses. So,
yes,
although you have not considered in this case, so what is your actually sort of comment on that? What could be the likely what could be your likely conclusions if you had considered the minor losses as well?
So means first of all, objective of this paper is to study parametrically the effect of number of this geometric parameter on the performance. And yes, there will be effect of minor losses on the benefit to cost ratio, and that is not included in the current model. But I think that if number of generation increases, that will increase number of bifurcations, and that will increase the minor loss. So that is again a one constraint will come.
Yes, because from your graph, you are able to, as you are going in on increasing the number of generations up to 6 generation, you are able to go meeting the temperature constraint. Means if had the temperature constraint be not been there, like not 90 degree, you could say 100 degree or 120 degree, you could have gone still to no, you have gone higher up for a given flow rate. You would have gone say to up to 7 generation or 8 generation.
Yes, sir,
but perhaps what my question was, had you considered minor losses, then the trend, that monotonic trend, what you are seeing, there could be a reversal of the trend somewhere before 6th generation or 4th generation or 3rd generation, or anywhere before, I mean 6th generation or 7th generation, like that, isn't it? So do you also think like that?
Yes, sir. Means there will be non-linear behavior, but means main objective was that to study parametrically, and
yes. You have done your studies based on the constraints and based on the assumptions that you have considered, and with that, what you are getting is it matches with your assumptions. Okay.
Yes.
But I was asking it from a different perspective, like from the physics point of view, or that. So that's why I was asking for your comment. Anyhow, thank you for the nice presentation. If there are no questions from the audience, then we can go to the next session quickly.
Thank you, sir.
Okay. Thank you. So the next paper is paper number 33 by Vikrant Chandrakar Gyanaranjan Senapati on computational study of natural convection with surface radiation from a vertical solid cylinder using various radiation models. So please start the presentation.
A very warm welcome to all the respected dignitaries. My name is Vikrant Chandrakar and I am from NIT Rourkela. Today I am going to give my presentation on computational study of natural convection with surface radiation from a vertical solid cylinder using various radiation models. This is my plan of talk which I will be covering in the coming few minutes. Introduction. Natural convection system. The mode of heat transfer which occurs due to the density differences is known as natural convection. It has many advantages like do not need any extra components, design is simple, cost effective, minimum maintenance is required and also produces less noise. And due to this advantages, its presence can be felt in applications like in cryogenic industries, manufacturing systems, crystal growing industries, and in the engineering field like chemical, mechanical, aeronautical, etc. However, dissipation of heat by natural convection is not able to get the desirable cooling rate so that it can be compared with the forced convection, and which is why this has encouraged different studies that aim in improving the heat transfer by natural convection. Motivation. When natural convection is used instead of forced convection, it enhances not only the performance but also the reliability of the parts by not using any external source for motion of fluid. Due to the involvement of low temperature, radiation effects are neglected. However, radiation effect is always present and is strongly coupled with the natural convection. Inclusion of radiation results in it transforms the temperature distribution in the domain. It affects the convection heat transfer and their combined effect is reflected on the overall heat transfer. Literature review. This is my literature review and here I have included some paper which are more related to my work. Research gap. From the available literature, it is quite clear that the problem of vertical solid cylinder for heat transfer due to the combined effect of natural convection and surface radiation has not been done so far. Also, till date, no study presented any comparison of different radiation models available in ANSYS Fluent. Geometry specification. In the present figure, left-hand side figure shows an axisymmetric geometry of the vertical solid cylinder and the computational domain around it, along with the boundary condition imposed on the domain. Uh, Whereas right-hand side figure shows the grid arrangement around the cylinder in the domain. Parameters. Various parameters used in the present study are Rayleigh number ranging from 10 to the power 3 to 10 to the power 6, which lie in the laminar range. Cylinder surface temperature, which varies from 300 Kelvin to 425 Kelvin. Cylinder surface emissivity ranges between 0 to 1. Specification of the solid cylinder. Here in the present study, the aspect ratio, which is L by T ratio, is fixed at 5 and the diameter of cylinder is taken as 10 mm. Air has been used as a working fluid and assumption is taken for the air is absorption, emission and scattering of the radiation is neglected from it, which makes the present problem as a non-participating media problem. Governing equations. The equations which govern the present problem are continuity equation, momentum equation, energy equation and radiative transport equation. Boundary conditions. At the axis, velocities are 0 while any variation along the y-axis is also 0. At the solid walls of the cylinder, constant temperature Tw has been given. At the computational domain, that is top surface, bottom surface and outer periphery, atmospheric pressure and temperature has been given. The important numbers which I have used in the present problem are Rayleigh number based on the length of the cylinder, Nusselt number due to the convection, Nusselt number due to the radiation, the total Nusselt number, which is addition of convective Nusselt number and radiative Nusselt number. Validations. Before starting the main work, validation of present numerical scheme has been performed. The present figure shows the comparison of present computation with the experimental work for radiation and natural convection on a cylindrical enclosure cross section with two radiation cells, where we found a good match which lies in the plus minus 2% of error range. After completing the validations, I started the main work on solid cylinder, and on which I started with grid and domain independence test. In grid independence test, we can see after in figure A, after 42,000 grids, the values are not changing. Similarly, in the domain test in figure B, after 6 times of the length of the cylinder, the change is very minor. So from this, I have taken the grid size around 42,984 grids and domain size of 6 times of length of the cylinder. Results. Present figure shows the variation of total heat transfer with Rayleigh number for different radiation model. It is found that total heat transfer rate increases with increase in Rayleigh number for DTRM, DO, S2S radiation models, whereas heat transfer rate shows an irregular behavior for the P1 radiation model. For Lend radiation model, heat transfer remains almost constant for any value of Rayleigh number, because this model takes the radiation intensity as a black body intensity at any temperature. Also, it does not solve any additional transport equation, while other models usually solve the transport equation. In this work, the fluid surrounding the air is non-participating, and this is why the optical thickness is very low. P1 model does not work accurately for the optically thin case, and that is why P1 model shows the arbitrary value of heat transfer for different Rayleigh number. DTRM, DO, and S2S model shows almost equal values for heat transfer for a given Rayleigh number. DTRM and DO radiation models are applicable for large range of optical thickness, and both the models provide almost same value of result for the problems related to the optically thin case. Similarly, S2S radiation model is mostly designed for the enclosure problem, but here this model shows the similar values like DTRM and DO model. So it is possible to use any one of the three models, that is DTRM, DO, and S2S model for computation of simple problem like this. The present figure shows variation of total Nusselt number with emissivity for different radiation model. It is seen that total Nusselt number increases monotonically with increase in surface emissivity for all models except P1 model, where it shows an irregular variation. For this particular case, the variation of Roslet model has not been included because this model is unaffected by the surface emissivity. As mentioned earlier, this particular work lies in optically thin case, which makes P1 radiation model inconsistent. Since the total Nusselt number is addition of convective Nusselt number and radiative Nusselt number, it increases with increase in emissivity for DTRM, DO, and S2S radiation model. Radiation intensity is directly proportional to the emissivity, and thus increase in emissivity leads to the increase in radiative Nusselt number. The present figure shows variation of Nusselt number with emissivity for convective, radiative, and total Nusselt number. It can be seen that as the emissivity increases from 0 to 1, radiative Nusselt number increases, while convective Nusselt number remains same. That is, it does not changes with increase in emissivity, which is obvious. Radiation is directly related to the emissivity by Stefan-Boltzmann law, and thus it is highly affected by the emissivity for radiative heat transfer. And this makes total Nusselt number to increase with increase in emissivity if surface radiation is considered. This figure shows variation of Nusselt number with surface temperature for convective, radiative, and total Nusselt number. It is evident from the figure that radiation Nusselt number increases with increase in surface temperature, while convective Nusselt number shows a marginal increase. The cause behind this is that the radiation heat transfer or radiation emittance is directly proportional to the temperature difference of the order of 4, while convective heat transfer is proportional to the temperature difference in the order of 1 only. Here contours of static temperature for without radiation effect and with radiation effect is shown over here. It is seen that thermal plumes moves in axially upward direction. It is also observed that the temperature is relatively high at the top surface of the cylinder in case of only natural convection, while it is low when natural convection is coupled with radiation. In case of only natural convection, heat is transferred due to the density differences. Whereas radiation heat in a radiation heat transfer, it does not need any medium to transfer the heat, and which is why it shows a faster transfer of heat from cylinder surface to the surroundings. The following important conclusions drawn from the present study are: total heat transfer and total Nusselt number increases with increase in Rayleigh number and emissivity for DTRM, DO, S2S and P1 radiation models. As the cylinder is optically thin, DTRM, DO and S2S model show almost the same heat transfer rate, while P1 model did not show the same trend. Rosalind model displays a constant value because it does not changes with the Rayleigh number as well as emissivity. For future studies similar to the present one, DTRM model can be chosen to study the radiation. It can also be concluded that combined natural convection with radiation transfers more quantity of heat as compared to the natural convection case alone. These are the references. Thank you.
Okay, thank you, Mr. Vikrant.
Yes, sir.
Now I leave the session open for discussion and question from the audience. Okay, Mr. Vikrant, I had a few questions.
Yes, sir.
Can you comment on, like, is there any quantitative criteria to decide, like, when the radiation heat transfer can be safely neglected without causing the erroneous results? Like you have said. Yeah.
Sir, in some cases, like in lower Rayleigh number, I found a very marginal increase in total heat transfer. In that cases, we can neglect the radiation heat transfer to combine with the natural convection. While in higher Rayleigh number, it is always preferable to include, and also in some cases, like in lower temperature, like in like nearly 325 Kelvin or 350 Kelvin, we can if we are getting very low transfer due to the radiation, we can neglect it. Otherwise, it is preferable to include with the natural convection, because it is always like in fluent, it solves both the convection and radiation radiation equation. So that is why it is.
Okay.
It can be included.
Okay. Okay. And your radiation heat transfer radiation RT radiation transfer equation, that
yes, sir.
There is a term that I as a function of vectors R and S, that is a vector quantity, is not it?
Yes, sir.
So that is multiplied with the symbol capital delta. What is that? What does this stand for? Is it, do you mean divergence, or it is as a difference of quantities across two points? So if we,
it's divergence, sir.
So then actually probably the symbol should have been inverted delta, right?
Inverted delta.
Yeah, that actually just happened to see your paper also, and then again in the presentation slide also, because otherwise you know the thing that, but to a reader it might be confusing. And like you have actually shown that this is the deciding on your, say, domain height, and also you have carried out a grid independent study. But actually both these studies are related to each other. For example, suppose as far as I could understand, suppose you want to decide the optimum or minimum domain height where you can get a like reliable solution subject to the boundary conditions that you are actually applying. You are applying, say, pressure outlet boundary condition everywhere. So for that your domain should be of sufficient size, right?
Yes, sir. Yes, sir.
Now now suppose if you have shown in figure 6 or somewhere that various different domain heights, then you have shown the Nusselt number or like that.
Yes,
then it
sir.
converts after a particular domain height. But while doing that, when you change the domain height, what was your grid structure? Did you keep the same
Sir,
number of nodes?
I firstly performed the grid independence test. At that time, I fixed the domain height to minimum one, like in 2 times of L, 2 times of the length of the cylinder.
Okay,
Thereafter,
okay.
once I am getting the grid size, thereafter I performed the domain height test, and thereafter I just decided that the domain height size.
But you what in your slide, what you showed is first you showed the study on domain height, then you showed the grid study. But in practice, what you did is first you carried out the grid study, then you
Yes,
for
sir.
that grid say mesh independent node, then you use that mesh independent node for different grid heights, isn't it?
Yes, sir. Yes, sir.
But when you did that, again there's a thing. Say suppose you obtained a grid independence solution for a say domain height of 1. Now you were using that number of nodes for a bigger domain size.
No,
so your
sir.
mesh
Actually,
will
your point is correct. But with like we are doing the problem, and with that, when increase the domain height, it also increases the grid size. So for representation purpose only, this is for just one case only. So for representation, I have shown in the paper, but I changes the grid also with the domain. So after doing some some calculations, thereafter I decided the grid and domain size.
Okay.
Yes.
Thank you, Vikram. Thank you.
Thank you.
So if there are no questions from the audience, can we move to the? I think we will move to the next session. I think this is the second last paper of this session. Okay, it's paper number 196 by Kalyan Deepak ji, Sujan Bithapa, Raja Mangalagiri, and Satyapi Jami on performance of various shock capturing schemes on CPUs and GPUs.
Hello, respected panel members. I, Kalyan, a fourth-year undergraduate student with my co-authors Sujan B. Thapa, Raja Mangalgiri, and Dr. Satya P. Jami from the Department of Mechanical Engineering, SRM University, AP Guntur, Andhra Pradesh, are thrilled to present our paper and share our work titled Performance of Various Shock Capturing Schemes on CPUs and GPUs. Our motive behind the project is the presented need for fast and reliable numerical simulations which are achievable on multi-core CPUs and GPUs. They're capable of reducing runtime by orders of magnitude compared to sequential versions. However, these require different code structures for implementation and is a challenging task to develop codes for every architecture present. Our work focuses on developing a future-proof version of structured finite volume method solver for compressible Navier-Stokes equations. This can be used for parallel simulations on CPUs and GPUs by automatic code generation. Our objective in this work is comparing the ability of various shock capturing schemes to capture the discontinuities in the flow field and analyzing the computational runtime of the schemes on different architectures. The schemes used in this work are AUSM family comprising AUSM, AUSM delta, AUSM plus, and Vanlier, which are flux vector splitting methods, and row with entropy fixed formulation, Hele with entropy, and positivity preserving formulation, which are flux difference splitting methods. The schemes are implemented in OpenSPLI FEM framework, which uses OpenSPLI and SIMPy as the building blocks. Auto-generated code from OpenSPLI FEM framework on translating to an executable parallel code using Oxford Parallel Library for structured mesh solvers can be compiled and run on various target architectures. In CPUs, it can be run on sequential message passing interface, OpenMP, hybrid MPI plus OpenMP versions, and GPUs, it can be run on CUDA, OpenCL, and MPI versions. In the present work, we have used sequential and MPI versions in CPU and CUDA in GPU. Methodology. The governing equations used in this work are the two-dimensional compressible Euler equations in the integral form. Here, W is the conservative vector and Fc is the conservative flux. The individual variables are defined as follows. UV is the velocity vector, rho is the density, P is the pressure, E is the internal energy, H is the enthalpy, Nx and Y are the unit normals, and V is the contravariant velocity defined as a dot product of velocity and unit normal vectors. The hyperbolic system is then solved numerically using FVM and Euler time integration. Schemes implementation. The FEA scheme advection upstream splitting method differentiates the convective and pressure fluxes. The scheme determines an interface Mach number based on the left and right cell values of a phase. The discretization is as shown below. Here, MNI is a normal Mach number at the phase I, FC is the convective terms without the pressure terms, A is the speed of sound, and pressure flux is the contribution of pressure terms at the phase I. AUSM delta differs from the AUSM scheme in the evaluation of advection Mach number to resolve the subsonic flows better. Vanley's scheme is based on decomposition of the convective fluxes with a positive and a negative part based on the interface Mach number. The FDA schemes solve the approximate Riemann solver at the interface based on the eigenvalues of the flux Jacobian. Validation and performance comparison of shock capturing schemes. To validate the implementation of different shock capturing schemes, we have incorporated various standard test cases for simulations. The test cases simulated are Short Shock Tube, Schuh-Osher test case, and Bose shock. The first two cases are standard test cases, whereas the third one is taken from the fifth higher order CFT workshop validation cases, which provides the grids and the criterion for the test case to be considered as validated. Short shock tube. Short shock tube is a Riemann problem used as a standard test case for the validation of the solver. The domain is taken as 1 by 0.125 non-dimensional units. Various grids have been generated, the lowest being 100 by 5 and the highest being 2000 by 5. As the problem is 1D nature, the length and grid points in Y are chosen to be small. The ratio of specific heats gamma is taken as 1.4. A shock wave at x is equal to 0.5 is initialized in the domain. The left and right values of the primitive variables are given as below. The graph shows the density profile for the grids studied using the AUSM delta scheme along with the theoretical calculation. It can be inferred from the figure that the solution with grid size 2000 by 5 points matches with the theory and the solution is bounded within the limits. For the other grids, the dissipation is high and the shock gets smeared. The figure here shows the capability of the various schemes to solve the test case on a grid of 100 by 5. It can be inferred from the figure that Vanley shows maximum resolvents while the ASM family of schemes predicts the properties similar to Van Leeuw. Helle's scheme is the least accurate. Schuh-Osher. Schuh-Osher test case is used to validate the capability of the solver to accurately capture the ridge structure behind the shock. The problem simulates the movement of the normal shock front in a 1D inviscid flow with density fluctuations. The domain is initialized by varying the density with respect to length. The left and right states are given as below. The graph shows grid independence results where specifically The 4000 by 4 grid was able to capture the shock location and the upstream disturbances close to the reference solution. There is, however, some deviation in the upstream disturbances, which is basically due to lower order accuracy of the solver used. From the recent results discussed, the best grid from the grid independence, that is 4000 by 4, was taken and ran for simulations with different schemes. The density profile along the length of the domain is shown in the corresponding graph. Here, we can conclude that similar to short tube case, the Hele schemes are found to be more diffusive compared to AUSM, Bandlier, and row schemes.
Please continue with the presentation.
(1.4). Here, we can conclude that, similar to short tube case, the Hele schemes are found to be more diffusive compared to AUSM, Bandlier, and row schemes. Bow shock. The bow shock, apart from the short shock tube and shoe washer cases, is a challenging case due to the presence of stagnation point and curvature in the shock. It becomes further challenging when the grid is aligned with the shock and the stagnation line. The test case is subjected to a Mach 4 inflow and the ratio of specific heats gamma is taken as 1.4. The simulations were run till L infinity norm of the density achieved at 5 into 10 power minus 9 for all the grid sizes. The performance of the AUSM delta scheme to capture the stagnation line shock for the grids considered is shown in the first graph, that is figure 6. As shown, the smallest grid generated oscillations around the shock and also at the stagnation point. Figure 7 shows the comparison between ASM family of schemes for the 590 by 186 grid size. As seen, all three schemes capture the discontinuity. The FDA schemes were unable to converge in this test case. This may be due to the carbuncle phenomenon as well as grid aligned shock structure and stagnation line. Computational time comparison on GPUs and CPUs. After validating the solver, the runtime on various architectures is analyzed. The computing architecture used here is a workstation with AMD Ryzen 7 2700 CPU having 8 cores, and the other is a virtual machine with NVIDIA Tesla K80 GPU on Google Cloud. Table 1 gives the MPI runtime for 1000 iterations of the shoe washer test case on 4000 by 400 grid size. We can see a significant speed up in 6 core compared to sequential. Table 2 shows the cumulative runtime for 1000 iterations of the shoe washer test case on 4000 by 400 grid size. AUSM takes the least time on GPU with a speed up of 40 times faster than sequential and 8.5 times faster than 6 core CPU. The runtimes are normalized with the sequential runtime, and the result is inverse to evaluate the speedup of the schemes on various architectures. As seen, for FES, AUSM has maximum speedup on GPU with Bandlier having least. For FTA schemes, the speedups on GPU is around 60 times faster and speedup on 6 core CPUs is 5 times faster. Concluding, in our work, the ability of the schemes to capture discontinuities in the flow were presented for test cases such as shoe washer, short shock tube, and bow shock. The schemes are implemented into the automatic code generation framework, which is capable of generating codes that can run simulations using CPUs and GPUs. The computational performance of various schemes listed in this work were investigated by running them on CPU and GPU with MPI and CUDA respectively. The performance of the solvers on GPU is impressive for all vector splitting schemes compared to sequential version. For the flux difference splitting schemes, the speed up on GPU is 60 times compared to sequential and 10 times compared with MPA respectively.
Sir, the presentation is over. Sorry for the glitch in the between.
Oh, yeah, no problem. There is one more presentation by Madam Raviwala.
Yes, sir. Yes.
Okay. She will actually, I think she will present live, is not it?
Yes, sir.
Okay, just before that, Kalyan's regarding Kalyan's presentation. Thank you, Kalyan.
Yes, sir.
Okay, so I would now request the audience if they have any question to ask. Okay, if not, Kalyan, my actually two comments, not exactly. First one is a comment sort of thing, or just want to discuss with you. Like you have compared different schemes in terms of by running on say MPI, sequential, and then GPU and the CPU. Do the performance in terms of the accuracy, do they differ?
No, sir. Performance in terms of accuracy doesn't differ, but only the speed up increases.
Yes. So basic essence of your actually this paper is basically a study of the computational time of using this different computational resources, isn't it? That is what is it. And then also side by side, you are also showing a relative performance of these schemes in terms of their accuracy for these three test cases.
Yes, sir.
Okay. This performance of this AUSM delta scheme in terms of accuracy, it will also depend on the value of user different parameter delta. Normally, it is set a value less than 0.5. I didn't see just in your slide. Did you mention about what value of delta did you choose for this for your case?
Yes, sir. Sorry, we didn't mention it in the slides, but we have used it to be 0.5 in our analysis.
0.5. We have used the maximum permitted value of delta or maximum prescribed value of delta of 0.5. Can you comment on the dissipative behavior of the USM delta scheme? Suppose when we use a higher value of delta, what will happen to the dissipation characteristic of the scheme?
I think going to the higher values, the dissipation will further decrease, sir.
Just actually, but had this been the case, the upper bound on delta would not have been actually fixed or prescribed delta equal to 0.5, right? People would have if you make it less dissipative, okay, we need some minimum dissipation, but then dissipation should be as low as possible so that you get accurate solution. Otherwise, your shock will be smeared, isn't it?
Yes.
So increasing delta, whether it increases or decreases the dissipation, that has to be looked into. Okay. Okay. Anyway, thank you. I wish you all the best for the future. Okay.
Sure.
So now we have the last presentation in this session by Madam Raviwala. I think she will be presenting live.
Yes, sir.
Yeah. So please share your slide and start presenting.
May I audible, sir?
Yes, you are clearly audible.
Okay, I will share the PPTs. PPTs are visible? Hello?
No, ma'am, we cannot see your PPT.
You are presenting from your mobile, perhaps, right?
Yeah.
Okay. Can there's no provision to show in the full screen mode?
Wait, sir, I will try. No, sir. Sorry.
Okay, then please. Yeah, please carry on. Please carry on.
Good evening, sir. Myself, Ravi Bala Patil. My presentation topic is thermal lattice Boltzmann method based force convection heat transfer from 6 inline heated square cylinder for various spacing ratio under the guidance of CM Sevatkar. Outline of presentation, literature, introduction, literature review, objective, problem statement, methodology, validation, result and discussion, and last point is the conclusion. Introduction. Study of fluid flow around large number of heated square cylinder is an important heat transfer problem. Study of fluid flow around single heated cylinder has been studied by many researchers and reported in the literature in terms of average Nusselt number. However, heat transfer process in case of large number of heated cylinder is highly transient in nature, which is rarely reported. Present work has been carried out for flow around 6 inline heated square cylinder and to understand the transient in heat transfer using temperature contours and Nusselt number signals. In this work, the spacing ratio has been varied from 0.5 to 2 and understand the effect of spacing in the transients occur in the heat transfer process. A brief literature review is presented here. Significant research work. Hello? Hello?
Yes, you are audible. Please continue.
Significant research work is available in the literature for a flow around single heated square cylinder. Flow around two heated cylinder is also widely reported, and some of the important outcomes for flow around two heated cylinders are presented here. The flow is steady for a Reynolds number less than 35 and it become unsteady for a Reynolds number greater than 40. The engineering parameters are always higher for upstream cylinder than the corresponding values for downstream cylinder. Flow around the large number of heated square cylinder is reported also, but the results are mostly available in terms of average Nusselt number, and the transient in heat transfer is not yet reported. So aim of present work is to understand the fluid flow and heat transfer around 6 inline heated square cylinder. 6 number of cylinders are finalized here because beyond the 6 number of cylinders, the results are repetitive in nature. Objective of present work is to understand the effect of spacing ratio on fluid flow and heat transfer parameters. The problem statement of present work is shown here. There are 6 square cylinders with the side D. The distance between any two cylinder is same, that is equal to S. So S by D is the spacing between the cylinder. All the cylinders, stationary cylinder, are exposed to a constant free stream velocity U infinity and temperature T infinity. The cylinders are heated and maintained at a constant temperature TW. The free slip boundary condition has been applied at the lateral edges of the computational domain. No slip boundary condition is used at the wall of the cylinder. Convective boundary condition is used at the outlet of the computational domain. A uniform velocity U infinity and the uniform temperature T infinity is described at the inlet. This problem has been solved by using a thermal lattice Boltzmann method. In thermal lattice Boltzmann method, instead of solving Navier-Stokes equation, the kinematic equation for velocity distribution function and energy distribution function has been solved. The basic principle of this method involves the movement of a large number of particles on a lattice. D2Q9 model has been used, which contain one stationary and 8 moving particles at each node. The two basic steps of these methods are collision and propagation. The particles are collide at each time steps and their velocity and temperature changes. During collision, the particle readjusts their state and mass, movement, and energy are conserved. In the propagation step, the particles move to the nearest neighbors along with the respective velocity and temperatures. These are some mathematical equations that are used in the thermal lattice Boltzmann method. Next, point is the validation. The thermal-lattice Boltzmann method-based in-house code for a single heated square cylinder has been validated first, and then the same code has been used for the flow around multiple heated square cylinder with certain modification. The validation results are presented here. The in-house code for a single heated square cylinder has been validated by comparing the average Nusselt number and the mean drag coefficient with the existing numerical and experimental results. The excellent agreement is observed between present data and published data. Vorticity contours. The instantaneous vorticity contours for S by D is equal to 1, 1.5 and 2 are shown here. It is observed that at low spacing ratio, a single wake is formed behind a cylinder as if flow is occurring over a single cylinder, and the vortices are shed from the last cylinder. Because of this reason, thus at low spacing ratio, that is at S by D is equal to 1.5 up to S by D is equal to 1.5, the flow is synchronous. At higher S by D ratio, means at S by D is equal to 2, the flow received from downstream cylinder is not uniform, and this lead to the transition of the flow from synchronous to quasi-periodic flow. The transitions of the flow from synchronous to quasi-periodic flow are also confirmed through the signals of leap coefficient and their corresponding power spectra. The leap coefficient signals for S by D is equal to 1 and for S by D is equal to 2 are presented here. From the signals for S by D is equal to 1, the leap coefficient signals are sinusoidal in nature, which suggests that the presence of only one frequency corresponds to vortex shading frequency. And for S by D is equal to 2, the leap coefficient signals are not sinusoidal in nature, rather these signals are modulated. This modulation suggests that the presence of two frequencies, primary frequency and secondary frequency. Similarly, the quasi-periodic nature of the flow is also confirmed through power spectra. The power spectra for the leap coefficient is presented here. From the power spectra, it is noticed that for S by D is equal to 1, there is only one peak corresponds to primary frequency, and for the power spectra, from the power spectra for S by D is equal to 2, there are two peaks corresponds to primary frequency and secondary frequency, that is STP and STS. STP means your primary frequency and STS is secondary frequency. The temperature contours for S by D is equal to 1, 1.5 and 2 are presented here, which again also suggests that the heat transfer process is also changes from synchronous to quasi-periodic heat transfer. At very low spacing ratio, both vorticity contours and the temperature contours have perfectly similar features, because vorticity and thermal energy are the transport by the flow itself. Hence, at low S by D ratio, means at up to S by D ratio 1.5, the heat transfer can also be termed as a synchronized heat transfer regime. As the gap between the cylinder increases, then not only flow will be altered, but the thermal field is also affected. Hence, at higher S by D ratio, the heat transfer regime is the quasi-periodic regime. Again, the transition of the heat transfer from synchronous to quasi-periodic is also confirmed through Nusselt number signals and the power spectrum. Nusselt number signals for S by D is equal to 1 are presented here. These signals are again sinusoidal in nature, which suggests the presence of only one frequency, that is equal to primary frequency. And for S by D is equal to 2, the Nusselt number signals are not sinusoidal in nature. Instead of that, they are modulated. These modulations suggest that the presence of two frequency, primary frequency and secondary frequency. In this figure, the Nusselt number signals for first cylinder and second cylinder for all S by D ratios are presented here. These signals are either sinusoidal or modulated in nature according to S by D ratio. The power spectra for Nusselt number are shown here. For S by D is equal to 1, there is only one peak from the power spectra, that is corresponds to primary, and for S by D is equal to 2, there are two peaks, that is which corresponds to primary and secondary frequency. STP means your primary frequency and STS your secondary frequency. Then the variation of average Nusselt number with S/D ratio is shown here. For first cylinder, the Nusselt number value is highest. For second cylinder, the Nusselt number value is lowest for all S/D ratio. And for third to sixth cylinder, the variation is Nusselt number is monochromatic. Here, the comparison of the flow and heat transfer regimes is presented here. For flow regime, synchronous regime occurs for S/D ratio less than 1.1 and heat transfer regimes occur for S/D ratio 1.5. The quasi-periodic 1 regime is not obtained in case of heat transfer regime. Quasi-periodic 2 regime is occur for flow regime in between 1.4 and 5, but quasi-periodic 2 regime for heat transfer occurs at S/D is equal to 2. Main conclusion of present work is that as S/D ratio increases, the drag coefficient and time average Nusselt number increases. Secondary cylinder has lowest value of the Nusselt number. The fluid flow and heat transfer process is also periodic and unsteady in nature due to unsteadiness of the fluid flow. The changes in transition in the flow regime occurs at lower S/D ratio. However, the heat transfer regimes occurs at higher S/D ratio. Thank you.
Okay, Madam Raviwala, thank you for your presentation amidst the crisis. Well, we have very few audience left. Still, if anyone wants to ask anything. Okay, in that case, just one question from my side, that you are solving transient flow, isn't it?
Yeah.
So for that, your time accuracy is also important, right? Order of time accuracy. So how are you, madam, ensuring that in your computation?
Order of time accuracy.
Yes.
Actually, sir, we are going to run the simulation for 5 to 6 lakhs up to that time steps, and when we are getting some stability in the results, according to that, we are going to initial readings we are going to change, because we are not getting the dynamic results. There will be so much fluctuation, and after that, whatever the results are remaining, we are going to plot the graphs or the signals, and according to that signals we will decide the regimes.
So that means are you using any convergence criteria sort of thing?
No, sir. I have developed a code, sir. I'm not using CFD software.
You are using your own code, fine. But even in your own code also, to terminate your computations, you need some criteria, no? So what is your criteria? Is it based on the certain number of iterations, or it is that, as you said, that there are certain fluctuations, and when you say that those fluctuations die out, then you stop your iteration? So that means you have some kind of termination criteria. Yeah.
After certain time period, if we are getting the same curvature or some same variation in the signals for leap coefficient, drag coefficient, or Nusselt number, after that we have stopped the simulations. Means same pattern.
Are you dynamically plotting your variation? It's not possible, no? Iterations go on running for one after the other. So say, suppose what you mean to say, that suppose you run it for, say, 1000 iterations, say, then you see your results, then you see there is high variation, then again you run your code for a higher number of iterations. Is it like that?
Yeah.
Okay. But you are, this kind of problem is unlikely to be at a steady state, isn't it?
Yeah, it is unsteady actually, sir.
So that's why if it is unsteady, then actually there's it is a time dependent problem. So that's why it is a highly transient problem. So for this, even the time accuracy is also important. That is what was my actually question in the beginning. Anyway, hopefully this will also be taken care of in the future. So okay, thank you for this presentation. Okay. And with this session comes to end. I thank the organizers of FMFP 2020 for giving me a chance to be a part of this prestigious conference as a session chair. Is there anything else from the FMFP team?
Thank you, everyone. Thank you, Professor Kalita, for your valuable time. We can conclude the session now. Professor Kalita, you can leave now.
Okay. Thank you.
Thank you, sir. Thank you, sir.
Thank you.
Thank you.